Yes, sir.
Good morning, Professor Agarwal. Can you hear us from here? You can unmute yourself. Just check box, security check box. Can you try to unmute yourself?
Are you able to hear me?
Yes, yes, very clear,
Okay.
very clear.
Yeah.
Yeah. So in the morning, I just came to know last week Mr. Thapre, he passed away,
Yeah, I know that.
and NCR is trying to organize a condolence meeting sometime later this week. Yashwant wrote me an email, so I will just mention that. And because he was involved in the 3.6 meter dot also, if I understand correctly.
He was a member of the project management board
Yes.
of 3.6 meter telescope and contributed significantly.
Right. So I thought, I will just mention that.
Yeah.
I will just mention that, there is a conference meeting coming over. अभी वेटिंग रूम एनेबल्ड है हमारा। अब सिक्योरिटी में जाओ, ज्यादा से ज्यादा कंट्रोल वो सिक्योरिटी का बटन से।
हाँ, यस सर।
तो अभी इनेबल वेटिंग रूम है, उसको हटा देंगे तो लोग सीधा आ जाएंगे।
ओके,
कर सकते हैं, बिल्कुल ज्यादा से ज्यादा वो कौन बार-बार।
हाँ, नहीं, एक्स्ट्रा लोग नहीं आएंगे, जो लोग हैं वही आएंगे।
आपको ये देखना है कि कोई अरेगेरा कोई आ गया तो उसको निकालना है।
यस।
वो उसको भी आप कर सकते हो, पार्टिसिपेंट लिस्ट में जाके जैसे मूव हिम आउट, रिमूव हिम, दिस आर सब ऑप्शन।
ओके, ये कंट्रोल यहीं से हो जाएगा। ठीक है सर, मैं कर लूंगा, कोई इशू नहीं।
दिस इज द मास्टर कंट्रोल ना।
हाँ, श्योर।
Ramsakar wants to just admit. You can also go to the waiting room का, हाँ उसमें भी admit कर सकते हैं।
Yeah, I think अब डिसेबल ही कर देते हैं। Okay, fine.
And यहाँ का माइक्रोफोन आपको म्यूट करके रखना है, बिकॉज यहाँ पर नॉइस नहीं पिकअप करेगा।
Yes, sir. Now you can.
Good morning, Ajit. Would you like to test your microphone?
Yes, please. Can you hear me?
Yes, yes, very well, very well.
Good. Thank you.
Yeah.
See, I would like to say one thing only, that in case the power goes off or something like that happens, okay, then I'll very quickly switch to other network in just a minute or so.
Sure, sure, no problem.
उधर बैठा उधर चेयर पे बैठना कंट्रोल कर सकूं ना फिर ऐसी चीज खड़ा है देखते नहीं रहता ना
हमारे तो कोड
नहीं सर यहीं से कंट्रोल कर रहा हूं
हाँ but क्या होता है कि suppose this machine suddenly goes out of the cloud ना
हाँ
then the other person who is there in the cloud because यहाँ के इसके ऊपर डिपेंड नहीं करता है
अच्छा
सब कुछ क्लाउड के ऊपर ही डिपेंड है क्लाउड में जो लॉगिन होगा वो कंट्रोल कर पाएगा
हाँ ठीक है कोई
नहीं तो उससे तो कोई दिक्कत नहीं होगी कितने भी नंबर ऑफ को होस्ट बना लीजिए
हाँ
दे देता हूँ उनको राइट अमर आर्यन मैं को होस्ट
रमेश चंद्र जी
गुड मॉर्निंग
थैंक्स फॉर ज्वाइनिंग मैं कल मेल लिखा उसके बाद मैं आप लोगों को कॉल नहीं कर पाया
नहीं वो तो मेल के अपने न्यूज़ भी आई है
आज नहीं मिला अच्छा अच्छा और लोग कुछ लोग आ रहे हैं
आएंगे क्यों नहीं
ये मल्टीपल कैमरे वाला सजेशन सब बहुत अच्छा है स्पीकर और वो पैरेलली हम लोग देख पाते हैं इनके ऐसे व्यूअर्स हैं हम सर नहीं सजेस्ट किया कैमरा को
Good morning, everyone. And on behalf of Scientific Organizing Committee of this National Workshop, titled Astrophysical Jets and Observational Facilities, a National Perspective, I welcome you all to this inaugural session of this National Workshop. And I would like to little brief that the idea behind hosting this National Workshop came somewhere around January, where we thought that since COVID situation is now improving, let us have a face-to-face meeting. Later we realized that probably it may not be possible. So let us have an online meeting. And the Scientific Organizing Committee is really overwhelmingly kind of happy to see the kind of response that we got from our senior astronomers to all the way to very young astronomers. And based on that, the Scientific Organizing Committee really thought about that how to go ahead with this thing. And then we realized that with Felix Mirabel's concept of astrophysical jets, where we understand that all the way from microquasars to quasars, these kind of jets do exist, and probably the unification of jets followed by the accretion processes might help understanding a large variety of astrophysical sources. So we thought that let us review this all the way from galactic to extra-galactic kiloparsec level jets and see that existing national facilities, how we can really contribute towards understanding these subject areas and collaborate internationally. And also that with the upcoming facilities, how well we are going to be equipped with to address these questions. So keeping these aspects in mind, the SOC invited and circulated the information to host this workshop, and based on that, the whole program was decided. Now that the COVID situation is not that improved, and we wish and hope that situation will be improving in due course of time, it's very, very nice to see very senior astronomers to very young astronomers who are participating to this workshop. And with this small address of mine, I would like to invite Director Aries, Professor Dipankar Banerjee, to kindly come up and have the welcome address before we proceed for further programs. Thank you very much.
Good morning. Thanks to Shashi and Alok for organizing this workshop. In fact, Alok's father is not well, so he had to rush to Gorakhpur. So I'm sorry to report that Alok may or may not be able to actively participate. But I must congratulate Shashi and Alok for really working hard to be able to put together a very nice program. These are difficult times, and again we are undergoing a again difficult week here. But with that restriction, we were hoping that we'll be able to have our own PhD students and some faculties in the auditorium, and in a more of a hybrid mode. But unfortunately, yesterday one of the students got positive, so that way we are not entertaining any students in this auditorium. So it will be completely on a virtual mode. So I think it's a very timely to have a national workshop on astrophysical jets and on observational facilities, the national perspective. And I'm happy to see the program is really has a good width with a combination of review talks and contributed talks. And in fact, the review talks will set the platform in terms of the current status. As you know that 3.6 meter dot is really working quite well now. So I think it's quite apt that we as a national community discuss about one subject at a time and have more focused workshops. So I'm very happy to note that this workshop is particularly looking at the jets, and thankfully we have some new faculties also who have joined at Aries. So it will give us a good opportunity to integrate them into the national community as well. So I would like to point out that this is going to be also one of the first in the series of events commemorating the monumental occasion of 75 years of independence, Azad Ki Amrit Mahotsav. So I'm really happy that Aries is able to organize a major national event, Azad Ki Amrit Mahotsav, starting this week. With a deep heart, I would also like to point out that we have lost one of our senior members, Sri S.C. Thapre, on 26th of March. There is going to be a condolence meeting which is being organized by NCRA TIFR, I think sometime later half of this week. But I would like to point out that Sri Thapre was actually a monumental figure. He has helped institute across the country, and I understand in the 3.6 meter dot, he was a very active member of the project management board, And since my roots are still in Institute of Astrophysics, Bangalore, I know before we joined, even as a PhD student, his enormous contributions in the Kavalur facilities, named the Vani Bapu telescope, which was the probably first of its kind indigenously built in India. And of course, later on, most of the people know him with his enormous contributions in GMRT, and more recently, even in the maze. So here is a personality who was involved with major projects which the country has seen probably last 50 years. So in this occasion of 75 years of independence, I think it's real one person where we can say that across the country he has helped in major projects. So I, from Aries family, I express my sincere condolences for this big loss. And I'll just remind you again, please, we'll announce it later on when this formal condolence meeting will be organized by NCRA. Yashwant, I think, will be contacting all of you. So with that, a few words, I wish all the best for this workshop, a big success. I'll be in attending few lectures to learn myself about astrophysical jets, but I'm looking forward to the success of this workshop. And I understand from Shashi that we're also planning for a proceedings of this workshop. So I think this would be also a good occasion to compile the results and also about the future perspective from using our national facilities and of course 3.6 meter dot. So again, all the best, Shashi, for you. Okay. So maybe I would request this session, the next I would request Professor Agarwal, who is joined virtually from TFR to give his opening remarks. Professor Agarwal, can you please unmute yourself and you can switch on your video also. So Professor Agarwal is, of course, currently the governing council chair, but it's just not that. I think with Aries, his connection has been again several decades, and even if I go back to read the governing council minutes of the past of this these organizations, I see always mention of Professor Agarwal and a number of committees, the projects. So we are very, very happy that we are getting his guidance in on a day-to-day basis almost in all activities in Aries. So I think he's the most apt person to give the inaugural remarks also. Professor Agarwal, can you please unmute yourself and
Are you able to hear me?
yes, sir, we can hear you.
Okay. Good morning to all of you. Professor Dipankar Banerjee, Director is, members of the scientific and local organizing committee of this workshop, all dear participants from all over India, members of various staff, ladies and gentlemen. It gives me immense pleasure to extend a warm welcome to you all on behalf of the Governing Council of Aries. And I hope that you will enjoy this virtual meeting. It is gratifying to note that the workshop has evoked wide interest in the Indian astronomy community, is reflected by the registration of more than 200 participants for the workshop. The organizers have devised a very interesting and exciting scientific program which encompasses the entire electromagnetic spectrum from radio to TV gamma rays. Though initially discovered in the radio images of radio galaxies like Centaurus A and Cygnus A, etc., the astrophysical jets have now been discovered in all classes of black hole objects, including not just the AGNs, but also the black hole binaries of galaxies like GRS 1915 plus 10.5, the neutron star binary SS 433, etc. So jet phenomena is pervasive over the wide spectrum of cosmic source objects, which include pre-main sequence T-Tauri stars, the binaries in our galaxy, extra-galactic objects like AGNs, which include BLS and blazars, and explosive events like gamma ray bursts and gravitational bursts. A highlight of the scientific program is a series of review talks by experts in different fields, summarizing the present status of knowledge about the phenomena in different types of cosmic objects, and the questions about the dynamics and origin of the jets which are still unanswered. The program also includes a description, a comprehensive description of the ground-based operational facilities like like my upgraded GMRT, 6.6 meter, the optical telescope, as well as space observatory like AstroSat and their capabilities. Several planned new facilities like square kilometer array, 30-meter telescope, the National Large Optical Telescope, LIGO India, the planned polarization satellite, ExpoSat, and infrared satellite, which are at various stages of development and realization, and their objectives and capability will also be discussed. I hope that young students and researchers from different institutions participating in this workshop will be inspired and motivated to use these facilities to unveil the mysteries of the jet phenomena in various classes of the cosmic objects. I hope that issue lectures and contribute papers on different aspects of the phenomena in cosmic sources will be illuminating and foster fruitful collaboration between the institutions as well as individuals. I wish the workshop a great success. Thank you.
Thank you, Professor Agarwal, for your very encouraging words. Okay. So I will take the pleasure of now inviting Professor Ajit Kimbhabi to give the keynote address of this workshop.
Thank you, Dipankar. I should be permitted screen sharing.
Yes, can you just share the screen? I think it is enabled, so you can try to share the screen.
Okay.
Yeah. So, Professor Ajit Kimbhabi do not need any introduction to this particular audience. Nonetheless, I will take this opportunity. I mean, it's been a pleasure to work with Ajit in the Astronomical Society of India for last 6 years, and he has motivated me to also come to Aries and Nainital here. So, Ajit, it's all yours. So I just made few announcements in terms of just handling the Zoom sessions. That the questions are requested to be put up in the chat box during the presentation. That's one possibility. And also there is a Slack channel, so one can use the Slack channel for posing questions. Also, you can raise your hands, and during the questionnaire sessions, based on the order at which you have raised your hand, the speaker from here, we will unmute yourself, and then you can raise your question. Of course, depending on the time availability, those questions will be addressed. So the chat box and the Slack channel is probably a preferred channel for interaction. And also, those things are recorded. But if time permits, we'll also have the questions online as well. So please use the raise hand option, which is available on the reactions icon at the bottom panel. So yes, Ajit, we can see your screen here. Please continue. Thank you.
All right. Thank you very much, Dipankar. And thanks also to Shashi and Alok for inviting me to give a talk here. So when they first asked me to give a talk, I was a little bit perplexed as to what I should be speaking on. And then I noticed that X-ray binaries is one of the important topics of this workshop, and we had written a paper using AI low mass X-ray binaries. So I thought that should make a good subject. So what I'm going to do in my talk is in the first half, maybe the first 2/3, just review various techniques in AI at a very quick pace and give some examples. And then in the remaining part of the talk, to explain the work, to describe the work on X-ray binaries. Now, of course, this kind of work has been done in collaboration with a very large number of people over the years. We're talking about a 20-year time frame, and I shall put up their names at the end of the talk. I also make some general remarks at that time. So, so now AI, as we all know, is used in this, the analysis of large astronomical databases. So what do we do in analysis like this when we have very large databases? So in general, we are looking for patterns in the data. We look for correlations. Is the X-ray luminosity correlated with the radial luminosity and so on? We are looking for classifications. And most importantly, we are looking for outliers in the data. Because once you discover one kind of an object, it's no longer interesting to discover many more like that. What we are looking for is deviations from the mean, where we get the outliers and the new phenomena. And needless to say, we need to find meaning in the data. I mean, what are these telling us about physical phenomena, about astrophysics and physics of the sources which are concerned? So the primary tools with which all astronomers are completely familiar are data mining, which has now become rather technical, okay, in the sense that it's very, very easy to get data, but also one needs to know a little bit about how to go about doing that. And the data visualization, where astronomers have been sort of leading the race for centuries, and we depend on visualization, and we use whatever techniques which are available to do the visualizing. So we have moved from beautiful pictures, handmade pictures, which the ancient astronomers used to do. Look at Galileo's pictures, for example, to the kind of wonderful visualization we have now. Then we, of course, need data analytics. So where it's very important to have domain knowledge. So if you're working in a subject, if you want to apply these data analytical techniques to some subject, one needs to know the subject well. And typically, the two things, like data analytics, AI, and domain knowledge don't go together. So you need a good team working together with specializations in different parts of it. And then one needs to be very good with mathematics and statistics, which are the basis of all this. Right, so of all the many data analytical techniques, I'm going to be concentrating today on machine learning and deep learning and their applications to astronomy. Now, machine learning has become very ubiquitous. It is used all over the place, quite often invisibly. It started off with simple tasks like character recognition, meaning if I write the numbers from 0 to 9 in different ways, can I teach a machine to recognize it? Then speech recognition, which again now is becoming commonplace. Facial recognition, so which is used and abused, and there are lots of problems with it, but it's just becoming an unavoidable part of our everyday existence. Then more complex image recognition. There are people, there are cars, there are cows, there's everything here in the picture, and we want to recognize it. And the big application of that would be autonomous driving. So where you've got a car moving with no driver, or rather it's a machine which is driving it. Okay, and the car has to recognize what is happening all over the place and take suitable actions and have suitable reactions. So it's quite clear that this will subsume all these other things that we have talked about here. But what is interesting is the kind of applications these techniques have in astronomy. So let me very quickly go through a couple of very basic techniques just to fix our minds. And first of all, what do we mean by learning? What is the schema for learning? Right. So the point here is that the fact here is that we begin with input data. Right. So what kind of input data do we have? Let us say that we want to distinguish between elliptical and spiral galaxies. So our input data will typically consist of images. In other applications, we could have spectra, for example, or time series. So we have lots of images of elliptical and spiral galaxies where we know the identity of the galaxies. That is the input. We have to feed it into a machine, which some decades ago would have been a very large physical machine which carried out certain very simple tasks. But now it's just an algorithm. You just feed the data to a code, and the code does the job. And then the model is trained. So what do you mean by, so training meaning we expect and we are able to show mathematically that the model is capable of distinguishing between elliptical galaxies and spiral galaxies. Right. So then, how do we know whether it is good enough to be used? And for that, you'll say we have test data, meaning quite different from the input data. We have test data of elliptical and spiral galaxies, where we know the identities, but we will not be passing those identities to the trained model. We just pass the image data, and then the trained model says how many ellipticals and how many spirals, and then we can define the accuracy. How accurate is the result? Meaning that if I've told 100 galaxies are elliptical, are 50 elliptical really elliptical, or 95 or 99? Okay, so that gives you the accuracy. And recall meaning, if I know that there are 150 ellipticals in this test data set, then what fraction of those are actually identified? And then recall or completeness of the problem. So these are fairly straightforward. Right, so then there's a little bit of distinction between the way you can train. What we are mostly used to is supervised learning, meaning that when I'm revealing, I give the images to the algorithm, and with that I reveal the identities of the objects, then it is supervised because I'm telling it what the data is all about. Okay, but on the other hand, there can be cases where there's unsupervised learning. Okay, meaning that I am wanting to, there's a whole set of galaxies which I may want to divide into different classes without knowing what classes I should be looking for. Okay, so then I would have unsupervised learning. Unsupervised learning also can be used as a first step in supervised learning when there's not sufficient data. I mean, I unfortunately will not have time to refer to that again. It's very interesting case. Then there are two main words phrases which are used. One is machine learning. In machine learning, what does is extracts features from the data. Okay, meaning that if I want to distinguish, say, between stars and compact galaxies, then I would define some features of the data like the full width and half maximum and shape and so forth of known galaxies and known stars, and feed that to the data. So it is my responsibility as a user and seeker to define what these features are and then to provide them to the machine. In deep learning, one just provides the data without providing any features. And that becomes very important when the data is very large, and then when it is difficult to define features. For example, let us suppose that I want to look at irregular galaxies. I clearly can't have any specific features that I can provide it. So that is where deep learning comes into the picture. And deep learning is quite fundamentally different from machine learning. The concepts are much broader, and I'll come to that in a moment. So I always like to begin with this example, okay, where the problem is to distinguish between two classes of objects. The colors and shapes are immaterial. The input values here are the coordinates x1 and x2. So there are two groups with these coordinates, and if I've given a new object, I should be able to say straight away which group it belongs to. Simple. The way we would do it intuitively would be to just place a straight line, not a unique solution, but place a straight line there. And say that anything to the right is blue, anything to the left is red. So how would I define the straight line? With a normal W and an equation W dot x plus b is equal to 0. So the idea is that I have to find adequate W values. Now that may seem trivial. I mean, I could do it here. I don't see why I need machine learning. But the problem can soon become complex if we have, instead of having just two dimensions, supposing I got a multi-dimensional problem. I got n coordinates. So what you do is that you start with a large number of objects with known coordinates and say that which of the two groups that they belong to. And then I feed that into something which is called an artificial neuron, which is just a program. And then the program learns the things. How does it learn the thing? The program has to determine the straight line for which it has to determine the vector W. So like in all such calculations, what we do is that we begin with some initial values of W, and then the x's are all the known values. So we consider W dot x And the thing will be that if W dot X is greater than 0, it is on one side. If it is less than 0, it is on the other side. Right? So then, so how do we do it? We start with all these objects, feed it to the program, and it says that it is plus or minus. But I know whether it is plus or minus. So I know what are the target values for each set of the X coordinates. I know what are the values that I'm getting. So I set up a loss function as a sum over squares, as one normally does. And the idea would be to minimize this loss function by varying W. And then one uses some usual technique like steepest descent to do that. And when you have it, so starting with just guessed values of W, we very quickly arrive at this separation. Right? So that establishes the technique. Then what do I do if I want to put a thing here like this? Now I want to separate these. So you see that I cannot separate that by a straight line. What I could do is try to separate it by a curved surface. A curved surface brings in non-linearities. So the non-linearity, the neurons need to have non-linear outputs. Also, a curved surface would involve a more complex equation. Therefore, clearly, one would require a more complex structure for the neural network, because we just had a single neuron. Now we have got a neural network. So what happens is that there are two input neurons here, x1 coordinate and x2 coordinate. And then this is the output. If the output is greater than 1, I got one answer, less than 1, I got the other answer. But in between, I need to put in another layer of neurons, which are called the hidden neurons, hidden nodes, because just to provide enough complexity for the network to work on. And when I do that, and then I have got also, at every stage, I have a non-linear output. So when I do that, with non-linearities are extremely simple, I'll not go into that. Then one can do the training, and one actually arrives at this surface which separates into things. So if you give me, once I have trained network, you give me any x1, x2 values, I'll immediately be able to tell you which side of the surface I have on. But the thing which I would like to emphasize here is that whereas when we had the straight line in mind, when we required the straight line, we had the locus, we had the equation for the locus, and we had to minimize W. In this case, the same steps are followed, except that we do not need to know what is the equation of the surface, what the shape of the surface which we tried, nor do we know what is the equation of the surface after the process is completed. All that you have got is a trained network. Right? So this is a completely new ballgame. Because, I mean, there have been very complex papers written, research papers written, where you start with where you have got a very large number of equations which you can fit to the data, choose between equations and so forth. There's nothing here. We just built the neural network, and then we gave it the trained observations, and then we have got the result. Right? So this one, the surface is drawn just to guide the eye. It doesn't exist. So as the networks, as the problem becomes more complex, the networks become more complex. So you can have a network like this, where you've got a number of input neurons, and then you've got hidden layers, and then you have got the output layers. There could be a 4-way classification rather than a 2-way classification that we are talking about. And then now, you must understand that each one of these nodes is connected to all the nodes which are there coming later. So which means that there's a very large number of W values. They are no longer one-dimensional because W1, 2. So node 1 connected to the node 2 here and so forth. So now imagine classifying a human face. So even if I take a very small image, 10 by 10, a 100 pixel image, then I would have got 100 here input values. And then there will be thousands and thousands of these connections, okay, to be able to classify the face into the classes that we want. And then the whole thing becomes completely unstable and untenable. And then we require a new network. So there, in anticipation, I should say that when we use a machine learning network, an artificial neural network like this, to classify human face, we would take the number of pixels. Now, of course, you have got a 100 megapixel camera and so forth. But even if you have got simply 1 megapixel, then what you do is that you'd start with the 1 billion pixels, so there'll be 1 billion nodes completely viewable. But each pixel there is treated as independent. Right? So whether a pixel comes from an eye or a nose, it is treated as independent. And therefore, it really is not the way to do, not the way our human mind thinks. Because when I'm looking at any one of you, which I'm unfortunately not doing at the present time, it would have been so wonderful to be in the nice fall in Aries, to look at you, to what are the reactions that your faces are showing me, and then I keep changing my talk so that maximum number of pleased at any given time, which is not possible here. But when I look at those faces, I'm not analyzing the faces pixel by pixel. What I'm doing is that I'm looking at overall features. I recognize Professor Agrawal by the overall shape of his face, which I've been familiar with for 50 years now. Okay, and then the nose, the eyebrows, the features which are important. And when we go from machine learning to deep learning, that is what changes. Rather than work on extracted features, then one actually works on the important features of the face, but which the machine itself decides what they are. So imagine trying to distinguish between a dog and a cat. First of all, it will be very difficult to parameterize them into a finite number of features. But like I said, the shape of a dog is very complex, but it is made up of horizontal edges, vertical edges, lines, shadows, curves, and so forth. So just imagine, as astronomers, we are always plagued by seeing. But to take care of seeing, we are aware of what is the meaning of convolution, image convolution. So just imagine that I take a filter, which is just a vertical filter, just some pixels across, and run it through the image of the dog. Then whenever I got a vertical line there of pixels, I will get a high signal. Otherwise, I'll not get high signal. If I run a horizontal filter, if I run a circular filter, if I run a feature-based filter, then I will get different signals. And that is what deep learning does. So it has got, it starts with a large number of filters, okay, which are convolved with the image, and then which extracts features with the image. Here, for example, edges, here are curves, here are textures, and so forth. Right? And then it reduces, and then what it does is that it selects at each stage the most important, it's called pooling. It just takes the most important features. And then it reduces the number of features to a manageable quantity, which can then be classified using the usual machine learning technique. Okay, so this is what happens in deep learning. So you see that here you have got a car. The idea is to be able to distinguish between a car, a truck, an airplane, a ship, and a horse. Right? So here you have got the train network. So when the image of a car is input to it, you will find that there are all these convolutional layers which are there, and there are pooling layers. So the convolutional layers takes a certain number of filters. And who's provided the filter? I have not provided them. Nobody has provided them. I just specify as a hyperparameter to the deep learning network the size of the filter. I'll just say use filters 4 by 4 in size, 4 pixels by 4 pixels, and to a maximum use 35 filters, okay, 75 filters, and that is all. The nature of the filter becomes a part of the learning process. So you have got different filters in 1D, different filters in 2D, different filters for different kinds of images. And as the filters are applied, the convolutions take place. What the pooling does is that it will take, for example, a 4 by 4 pixel set and pick out from that the maximum number. So what happens then is that you are retaining the nature of the convolved image, and yet you are downsizing the number of pixels. So the small little big images that you see are all the features which have been extracted, and finally the classification is made. And then the size of the bar gives you the probability, which is which is estimated internally by the network of it being a car. And clearly you see that probability is the maximum. So this is a case of correct identification. So when you have a network like this network, for example, is AlexNet CNN with 12 layers, was used by Shilu Abraham, who used to be a postdoc working with me, when we are trying to find bars in galaxies. So there are the convolution layer, ReLU, it goes on like this, and it is an art to decide what you want to do. But there is no complexity in the use, in the sense that there are very beautiful software packages available, which allow you to start using this quite soon. So if you hear about this, and if you go to a young student, that student can, in a couple of days, learn how to do these things and start doing the classification. It will, needless to say, it will take a couple of years to do the job correctly. Right? But the basic techniques are there. Using it is as easy as using LaTeX, for example. All right. Now, what I'm going to do is to provide you just a walk through a problem which we worked on for 20 years. Okay, meaning that we started working on the problem a very long time ago, when our knowledge was extremely poor. We, meaning it was Sajid Philip, with whom I worked for a very long time, Yogesh Vardekar, who used to be my student, and then somebody else too. And then our knowledge was very poor, the techniques were very poor, but it was work done in the early days. And so, and then I will show you how that work over a period of time has transformed from machine learning to deep learning. So you see that the problem is very simply defined. So this is a deep field survey, NOAO, and there are all these tiny little objects here. And the thing is to decide which one of these are stars and which one of these are galaxies. Very easily defined problem. Okay, because one is really not looking for a big galaxy like this, but a tiny galaxy like this. And because this is a high galactic latitude field, most of the objects here are galaxies rather than stars, however small they may look. Right, so we worked on it and to distinguish stars and images. So just look at this. This is a relatively bright galaxy, and this is the image of it. This is a faint galaxy, and this is the image, typical image. Right, and so you've got the 3D image with a 2D projection here. And this one is a star. Okay, the gorgeous Gaussian almost, and of course there'll be departures from it, it's very well defined. So the idea is to define parameters which allow us to distinguish between this and this. But for that, we need to know which are the galaxies. That Andromeda can be easily identified as a galaxy, but we are talking about objects which are barely larger than stars. So we chose a number of objects, 3 sets. So you see that there are 89 stars for 83 stars and 319 galaxies. These are laughable numbers. This only means that the whole thing was overfit, but we did not know all this at the time. So people sat down and actually looked at these individual objects and decided which are galaxies and which are stars. And all due care was taken in that. And a machine learning network called DBNN was set up. DBNN was developed by Sajid Philip and was set up. And then it was trained on these objects. And then we had 2 test sets on which we worked. And we looked at it. And then we got excellent accuracy. I believe that we got 98% accuracy. Now, for example, any high accuracy like that would mean that it is overfitted. It is like having 30 points for which you want the equation, but you take a very complex equation, high order polynomial, which passes to every point. So it is like that. But nevertheless, this was considered to be a fairly successful thing. So what we have done is that we have extracted 3 parameters at a magnitude and used that to train the system. 10 years after that, this work was done in 2001. 10 years after that, we looked at a similar problem. So here, this is a quasar and this is a star. Both look nearly the same. How do we distinguish between them? Right, so here's a color diagram. So here you got the U minus B color. I have to keep shifting around this panel. It's difficult to do. Here you got the U minus B color, and here you have got the B minus B color. So you see that these are the quasars, then you have got the white dwarfs which are red and the main sequence stars. You see that they're pretty well separated, but not fully separated. Right? So, but that's for 2 colors. But if you look at more colors, So because you see, we worked on the Sloan survey now, which has got 5 magnitudes, so you can make 5 colors. And so if you look at in 5-dimensional space, of which you are seeing 2D projections here, so you see that if you work on all 5 dimensions, then it is possible that you will be able to uniquely separate the objects. And so what we did was that now we are working in 2011, and so we had much better computing facilities and better knowledge about how to go about it. So we considered 100,000 stars and 100,000 quasars, spectroscopically identified quasars, and 154,000 stars. Then we see that with 5 magnitudes, we can make only 5 colors, but we use 10 colors. These are not very dependent, but as the quasars move over the redshift range, the colors keep changing, and so forth. So 10 colors and 1 magnitude was used to train a DBN. And then what we got was when we trained it, when we tested it, and so we found that look, stars could be predicted with 99% accuracy. Small number of galaxies were present, but that was not the point. And quasars also with 99% accuracy. So what we did was that we generated a catalog with about 1.5 billion quasars in them, and said that anybody who wants large catalogs of quasars could use this. And if the overall accuracy was like 99%, but for every quasar, we had an internal accuracy which came from the network, which said that what is the probability of it actually being quasars. So if you are going to choose quasars for some further observations, then you could choose those which are 80 or 90% individual probability. So this is again a machine learning application. But come to 2021, so where we are working with we meaning Vivek from IIA, Kaushal from Aries, and I, and we are working with 4 students from IITs and MIT and so forth. Okay, so the idea is again the same. Look for try to distinguish in stars and galaxies without first having to identify the galaxies manually and go to as compact galaxies as possible. That is the brief. So we have here bright galaxies, and here we have dim galaxies. The medium when you are dim, and here you've got a star. So it's going to be a big job to distinguish between this and this. Right? So what we do is, how do we first identify the galaxies for the training sample? That is done spectroscopic. Because the Sloan survey has got hundreds and thousands and billions of spectroscopic observations. So one picks out these kind of objects where one can say spectroscopically whether it is a star or a galaxy or a quasar. We can have all 3 objects now as a bonus. Right? And then what we do is that we use deep learning for this one. So this becomes a pretty complicated problem now. And then this is just one unit where you got all the convolutional layers and so forth, and there's a pooling layer, and the overall network is rather complicated. Okay, and we have got first cuts of the result, and we find that we can have 91% accuracy and nearly 91% completeness. So that is really very good, though we have to establish where to confirm these results and see how to improve them even further, and which is a problem which is going on at the present time. So you see that the transition from the from machine learning to deep learning provides its bonus, and it also makes better results, but it is more complex to use. But you must understand that it's completely inescapable. All right, now I come to the last part of my talk. So low mass X-ray binaries. So you see that this is a typical low mass X-ray binary where you got a compact object which is surrounded by an accretion disk, and there's a thing which is a low mass companion star. Low mass meaning lower than the mass of the compact object, and it could be a normal star, it could be a red giant or whatever, or it could be a white dwarf. All sorts of possibilities are there. And the idea is that this fills the Roche lobe and matter streams there, forms an accretion disk, and gradually accretes onto the compact object, releasing energy in the process. So what happens is that the X-rays from this come in from 2 different regions. One, they can come from the accretion disk, where there will be a combination thermal spectrum, which is a combination of black bodies at different temperatures, and they could also come from a corona where the spectrum from the accretion disk is reprocessed mainly through comptonization, let us say. Right? But this is just a very simplistic way of doing it. Now these go from a low state to a high state. They can lie dormant and suddenly they burst forth into it. And the important thing is that the compact object could either be a neutron star or a black hole. These are the only two sorts of objects. Now, it is very important for the modeling, for further observations and so forth, to know whether it's a neutron star or a black hole. How do we know whether it's a neutron star? So let's suppose that we have coherent pulsations from the object, X-ray pulsations, or whether we see X-ray bursts of radiation. Then we know that something is reaching the surface of the object, that the object is rotating, and we are able to see non-uniformities in the object, which means that it couldn't be a pristine black hole. It has got to be a neutron star. Now, if the mass of the object is small, enough that it's a neutron star. If the mass of the object is typically more than a few solar masses, then it couldn't be a neutron star because you are going over the neutron star mass limit, in which case it's a black hole. So people have very painfully, over many decades, have given pretty firm classifications for a certain number of binaries, black hole binaries and neutron star binaries. But this process is very expensive, and in terms of the number of years and the number of investigations that it takes, there are always uncertainties. So the question that we ask is, can we determine the nature of the compact object in low mass X-ray binaries, LMX from the spectra? Meaning that if I got just the energy spectra, and you see that here there's a spectra of a neutron star, black hole. The black hole and neutron star spectra are not too different from each other. Because you see that the resolution that one works is very poor. You must understand that. And that, therefore, it seems like a tall order. Can I look at the spectra and do it? So the idea is that we could use machine learning. And my answer is yes, we can do it using machine learning. And I'm going to very quickly tell you that. So use spectra of known black hole and neutron star sources and predict the nature of the compact object. And that is the order. So we worked with RXT spectra, the Rosy X-ray timing explorer, so which have got I think from a few kV, 1 or 2 kV to 60 kV, but we use the energy range 5 to 25 because below 5, the galactic absorption becomes important and introduces complexities. Above 25, the counts become fewer and the spectrum is not very well constrained from there. So we have got 28 known black hole systems and 33 known neutron star systems here. And what is, you see, a fact which I forgot to mention, the deep learning typically requires thousands and thousands of observations, 30,000, 40,000, like that minimum. Machine learning can do with fewer, but still in large numbers. Now I'm going to now do an application of machine learning, okay? But even there we require thousands of observations. And here there are only a handful of these systems. So how do we do that? As it turns out, each one of them has got multiple observations. So look at this. Okay, so here is the source name and here's the number of observations. The mean number is 244, but there are some with more than 1,000 observations. Each one of these observations could have been taken in a different state. So it is possible in principle that each one of these observations is treated as independent. There are many ways in which we check that, and our technique is tied to that system, which makes best use of this kind of data. Okay, so what we do is that the way we proceed here, we need a training set. So there are n spectra, which are n sources which are available. So we take n minus 1 source in the training and 1 source in the testing, but that 1 source has got multiple spectra. And we do that source by source by source and see what happens to each source. Now, the technique that we see here is known as random forest. I would absolutely love to explain that to you, but I got 6 minutes left and I unfortunately can't do that, including questions. So therefore, all that I will say is the following. There's a technique called decision trees. Okay, so this could is classified as a machine learning technique. In a decision tree, for example, I mean the classic example from which I understand it is where you have to decide whether you can go out and play tennis, and you can do that if there is if the weather is all, you're talking of England, and so weather is all right. Mostly it is not cloudy, sunny, temperature, wind, and so forth. So when you have got a certain combination of these factors, the answer is yes, you can play. For other combinations, the answer is no, you can't. And the question is, can one create a decision tree where I start with one variable and then I just go through the other variables and finally come to the thing whether playing or not playing. Now, in this case, for the decision tree, the variables are the points of the spectrum, the counts at each energy between 30 and between 5 kV and 23 kV. I believe that there are 43 channels which are available. Right? Then what you do is that the decision trees can be pretty whimsical. So one decision gives you one answer, other decision tree gives you another answer. So you do this over multiple decision trees, and then you take the average, the majority vote of this. And because with one tree you get a decision tree, with multiple trees you get a forest. So you get what is known as a random forest because the division of the data is randomized. Right? So therefore, I take my spectrum as the input, train it, and then the train set tells me whether it's a neutron star or a black hole. And here, this looks like a awfully complex diagram. It is really very simple. What we have got is on the x-axis, the names of the sources. On the y-axis, the accuracy reached for each source. How do we do that? Meaning, we take one source, keep it aside, train with all the other sources, and then test against this source. Right? So then when we test against that source, let us suppose that it has got 400 observations, and we know it's a black hole. Then you may get in 350 cases our prediction is a black hole, 50 cases a neutron star. Okay, then you say that yes, then our accuracy reached is 75%. And so you can see here that there's very low accuracies in some cases, and then in most cases it is pretty good accuracy. The size of the dot tells you that the number of observations. And so now the question is, why do we get these low accuracies in some cases? Because you see, after all, if I just say yes or no, it's a black hole, neutron star, there's a binary classification problem. In the minimum, I should get 50%. Why do I get 20%? And why do I get in some cases low accuracy, some cases high accuracy? One possibility, there's a question of signal to noise ratio. So you see that here there are sources signal to noise less than 100. Here there are sources signal to noise greater than 1,000. And clearly, and you don't need to, I mean, this is completely obvious, that the higher the signal to noise ratio, the greater is the chance of success. But here it is about 0.5, where the signal to noise is poor. But then signal to noise, even with low signal to noise, you can get high accuracies. And then there are these anomalously lower accuracies, okay, which are not predicted by the binomial distribution. So then what happens? So this is my last one. I've come to the end of my talk. So you see that there are all these, there are the hard states and the soft states, and then you've got the diagrams, all kinds of shapes which are very well known. And you see here in this diagram, we have plotted the hard thing for neutron star, neutron star, neutron star, neutron star, and then the intensity versus the hardness ratio for black holes. And then you see here that the lighter the dots, the lighter the circles, the greater is the accuracy of the prediction. So you see that the non-accurate predictions are bunched together in maybe the hard states. In the soft states, it is the accretion disk which is contributing. And in the soft state, the hard state is the X-rays which are contributing. It is the non-thermal contribution which is most important. So the most misclassified sources belong to the low hard state. The high hard state observations are very well classified. And most low SNR observations have a probability of 0.5. Most high SNR observations have a probability, high probability, but hard color value. So what is happening here is that we have started with machine learning classification. We have got pretty pretty good classification. It's going to be very, very important to use this kind of a technique later. And we also have some physical insights into why we get bad classification. So these are pretty good progress which was made. But we need further progress because RXT is now dead. So the point is, how can we apply this technique to other satellites? And there, we don't have to start from the beginning because they can always, there's something called transfer learning, meaning that other satellites will have different detector property, different PS, all sorts of things will be different. Nevertheless, the learned network that we have got here can be used. We can begin with that and take that and transfer that learning to other situations. And we hope to do that. And here is the prediction made for low mass X-ray binaries with unknown classes. So these are the things where we have got good spectra, we don't have the thing, and then we have predicted with a black hole. We have made a good comparison with the literature, which I cannot go into. Now, work like this has to be done with a large number of people. Now, there are mostly young, and but there are also other senior citizens here, like Sajid Philip. We have been working together for a very long time. And I would really urge other young people to take to this and other senior people to encourage their young people to work on this. Yesterday, I received a paper from Annapurni where they have applied this kind of a technique. I believe they have also applied random forest. I have not been able to read the paper yet, but there are many more papers like this needed. And if you don't use AI, you're going to fall into bad trouble. People resisted LaTeX, people resisted programming, people resisted the internet, they got away with it. If you resist AI, you are not going to get away with it. I recently heard a quotation from an important person, I've forgotten who it was, which said the following: it is not true that AI will replace scientists, but it is true that AI will, scientists who know AI will replace scientists who do not know AI. Right, so let's all be careful and start learning these new techniques in a very systematic way. And I have something more to say about that, which I will, if I get a correct, at some good platform. Thank you very much.
Thank you very much, Ajit, for a very exciting talk. And I think it was a really, really apt opening of the workshop. Although you said that you want a large number of data points for deep learning, you can see my happy face across. And I'm sure, there are a number of people who are attending your almost a tutorial session will be motivated to this. Just a point, we are doing things with the solar physics as well. Our filaments are detected with your same technique. And I think it's a good time. We should also talk to each other and see how efficiently we can take this forward across, all astronomical objects. So I will have a few questions here, probably. The first question raised hand is from Bhavesh Rajput. Can you unmute yourself, Bhavesh, and ask your question?
Yes, sir. Am I audible?
Yes, you are.
Yes.
Thank you so much for such a detailed talk, sir. It was very inspiring. I wanted to know, let's say while training the model, or let's say when the ML script is running on the system, and let's say it starts deviating while exploring the parameter space. So which statistical quantities do we use to tell the script that it is going the wrong way? So probability or something else?
Yeah, so you see that I showed you, I mentioned that there's something called a loss function. Yes. So for example, when you are following a classical technique, you minimize chi-square, you minimize the sum of squares. Mm-hmm. Right? So here there's a loss function, which could very well be the sum of squares, but there can be more complex loss functions. Mm-hmm. And you are trying to minimize it. Mm-hmm. As you go on, as you proceed further with the technique, the loss function can go through a minimum and start rising up again. And where it goes to a minimum is where you have to stop. Similarly, there's something called accuracy, which is defined, and the accuracy keeps increasing and flattens out. Mm-hmm. Now, the point is that if you just go on and on and on doing it, you not only are wasting computer time, but you're also overfitting the whole thing, because these networks are extremely clever. So you can give them a minimum, a billion different things, but if you give them enough time, they learn each one of them individually. So if you give any one of them for the test, you'll get a wonderful result. If you bring a new object, the machine will not know what to do. Right? So these are all a part of the technology which is used in this. So minimize the loss function, but do it in a transparent, conscious way.
Okay. And other thing, okay, so I do Bayesian analysis on eclipsing binary light curves. And there are many times, for example, I receive a light curve or my program gets stuck, let's say on 2 parameter values. So let's say there can be a light curve, a same light curve for 92-degree inclination and 88-degree inclination. So let's say a similar case happens in this process, in this a deep learning process. So how does the script identifies that which value is the right one for the right image?
If you have lots and lots of scripts and if you treat it, if you teach it, then it learns and then it can distinguish between these. So we can discuss this offline. Just send me email and we can discuss it further over a call.
Sure, sir. Sure, sir.
Where are you working?
Sir, I'm a research assistant at Villanova University under Dr. Conrad.
Okay.
And I've just graduated from my bachelor's.
Sure. Thank you.
Thank you, sir.
Thanks, Ajit. We have time for just 1 or 2 questions probably. So meanwhile, can I request you to unshare the screen so that KP can try
Sorry.
for the
Sorry.
next thing? Yeah. So there is a question in the chat box from Sumit. Have you checked the accuracy with known classification of a subsample for testing?
Yes. As I told you, what you do in all these deep learning, machine learning things is that you start with a large set of objects with known identities. You take 90% of them for the training and say 10% for testing. Now, in our case, we did that, but the question is whether you divide them by source or whether you divide them by individual spectra. So we have tried everything which is there, and then we have done the testing.
The next question in the chat box is from Prajwal Rawat. Sir, how to choose the number of hidden layers, their neurons, and optimization parameters?
So if you optimization parameters, they're called hyperparameters. Those can be chosen by testing the thing and see when is the best performance. So if you can give if you can give a very good intuitive argument as to how many neurons they should be and how many layers they should be, then you will come out on top as one of the great contributors to this art. Okay, so and you'll convert it into a science because mainly that comes out of practice, it comes out of fiddling around. It is not something which can be easily answered.
Thank you very much, Ajit. May I request KP to share the screen?
Yeah, I just like to say one thing, Deepankar.
Sure.
Is that if any one of the students is interested, they could write to me. Thank you.
Absolutely, absolutely. Yeah, please do that. And there is a Slack channel also, so which can be used as well. KP, can you just test your microphone?
Unmute. Okay, starting. Can you hear me now?
Yes, you are very clear.
Okay. Okay, so after this excellent talk by Ajit Kimbhavi on exciting topics, I go back to things a little bit more mundane.
KP, just once again, KP. There is some echo here. I just want to settle that. Okay, so before we move on, let me also introduce next chair. Shubhendu Rakshit is our new faculty here. I will request Shubhendu to take care of the following session. And probably just mute yourself and check whether you speak.
Okay, so
yeah, it's unmuted now.
So good morning, everyone. So welcome to the first AGN session of this workshop. And in this workshop, we have one review talk and 3 invited talk and 3 contributed talk. So the first review talk is by Professor K.P. and he will talk about jets from AGN. So welcome, Professor Singh, and so you will have 15 minutes for talk and 10 minutes for question. So you can start now.
okay, thank you. So I'll be talking about jets from AGN, and just to give you a little perspective here, these are the issues and topics that I plan to cover today. a little bit of history, and then the discovery of blazars, which are kind of jet-dominated quasars, examples of some jets, classifications, and so on. And then where I think the AI techniques will be wonderful in the future surveys. And the emission mechanisms involved, the studies of multi-wavelength emission, and the modeling, and some recent results that I've been working on with my collaborators. And then I will end with some, interesting topic about the jets, even in clusters of galaxies, and so on. Okay, so actually the first extragalactic jet was discovered in a plate taken by Herbert Curtis on Lick Observatory, one of the oldest observatories in US, in California. And Lick was one of the richest guys, and he gave his money to set up this observatory. And he noticed something in a jet-like feature in M87, which is shown here as the blue thing, but this is a modern CCD-based image and not the original one. I tried to get the original one from Raja, who used to Thakurta, who works in California, and this observatory has been, but apparently it was borrowed by Osterbrock, who passed away, and people are not able to trace it, and so on. So, but this is the so it goes far way back, than even the discovery, the idea of supermassive black holes and the other jets and so on. And then people who are doing variable star, studying the variability curves and so on. And in 1929, a German astronomer, Kuno Hofmeister, he published a catalog of 354 objects he thought were variable stars, one of the oldest variable star catalog. And one of these objects was what is called BL-LAC. This is a usual convention for variable star nomenclature. You have the two letters, which is ordered according to the discovery and the name of the constellation and so on. In this case, it was Lacerta, which means the lizard. Okay, so but this was very peculiar compared to other variable stars. It was erratic in variability. It had strong radio emission. And then they found later on, and these things happened slowly over time, took some decades. And then there's a faint and fuzzy galaxy around it. Its distance was very large. It has very strong polarization. All this happened in the up to 80s and so on. And then people recognized that this is probably a kind of object which can have its own class and so on. And the term blazars, because quasars had been discovered in the 60s in the meantime, and to retain the word BL, and then to kind of rhyme with quasars, it was called the blazars, an interesting catchy name for these objects. Okay. And then as far as X-rays go, it was found that this Parkes radio source 2155 minus 304, which are the coordinates, is also one of at that time of discovery in 1708. It was with the HEO1 by Agarwal and Rigler, was the brightest extragalactic soft X-ray source in the sky. And those days, we in this particular satellite, HEO1, which was launched in 77, and on which Agarwal had worked, he's making out the detectors. There was also a modulation collimator, which was the experiment A3, and there was experiment A2 that you can see here. And the A3 had a rotation modulation collimator which could localize. So this localizing objects to identify them or their kind and the properties was one of the big challenges in those early days of astronomy. And then they found that this little error bar here actually is settled on this 2155 source and so on. So it is not surprising that when we launched our soft X-ray telescope on AstroSat, I made it as the first light source on October 26, 2015. And this was the first light image of this source, and which is probably brought the biggest joy to me, that the soft X-ray telescope actually works, and can see this object right in the center of the field and so on. So this, then we used it as is kind of a target practice. We moved it around, and to establish the various characteristics of our detector and so on. It was a difficult analysis. This was then done by Sunil Chandra, that we could actually derive a light curve by correcting for vignetting and various other effects of the telescope, off axis and so on. So we used it for 9 days continuously looking at it, and we found, of course, it's highly kind of erratic X-ray variability over hours, time scale, and so on. In the meantime, after that 29 discovery of the variable object, the Seyferts had been discovered in 1943 by Carl Seifert. And what he found was that there is a star-like nucleus, but with non-stellar properties. Okay, it does not resemble any stellar emission. Stars mostly are absorption lines, and so on. Here we're finding broad emission lines, and he created a little small catalog. And also he found that the nuclear emission could rival the normal galaxy or even exceed it. And then later on, of course, people have found extremely large and rapid X-ray variability, which cannot be easily classified, and so on. So the notion of this is, I just wanted to show the image with AstroSat UVIT in far UV thing, that how the nucleus of the Seifert, a famous Seifert, NGC 4151, really dominates the entire light distribution in these wavelengths and so on. And so this is a modern picture instead of showing you the plate, which was done with various exposure times and so on. So this is how the notion of supermassive black hole was born, required to power these central engines. And of course, till then, people have found those other objects, but it was only when this Seyfert's discovery, and to understand the broad emission lines and so on, that you required a very big powerhouse in the central AGN and so on. Today, of course, we know from Hubble and all that almost all galaxies, especially with a significant bulge, they have AGN-like or a supermassive black hole in their center. So it has become a kind of a putative existence of a supermassive black hole in almost all the nuclei of galaxies and so on. So there's this wonderful recent review by Blandford and his friends, which now tells us that you can actually classify basing optical properties, and I think AI may help it further later on. You have these low ionization nuclear emission regions, which are probably the largest in their number density in the universe. And you can see that from compared to 10 to 7 for the field galaxies, it is liners are 10 to 6.5, and this is per gigaparsec. Okay, and of course, to some completeness value on the luminosity, that is how far you can detect. It's like 10 to 42. So they are also the faintest, and so on. And that's why they call weak Seifert-like galaxies and so on. Then there you have type 2, type 1, and then you have the really bright AGN, which are the quasi-stellar objects. Also, if they emit radio, called quasars. And then you have weak line radio galaxies. So you add in the radio galaxy analogs to these objects. Of course, the fractions or the number density is decreasing in the universe, and so on. But you have, so you see the bright quasi-stellar, strong radio emission, which actually dominate these studies and so on, are actually not that abundant in the universe. And these properties led to a very simple the reason why these led to the stipulation that okay, there is probably a supermassive black hole, were these simple properties that you have luminous long-lived objects in the universe, which are Eddington limited in their luminosity, and which corresponds to a very large mass, a billion or more, or up to billion solar masses. And the rapid large amplitude variability, it requires a very compact size for that variability to take place. And then, of course, the discovery with VLBA, the very large, continental-based array of radio telescopes, which sees asymmetrically broadened iron, which sees masers, water masers, and you can measure the velocity of those maser emission clouds, and which are very high. And then, of course, you also have the discovery of asymmetrically broadened iron lines, which are an indicator of the gravitational redshift, superposed on all the Doppler redshifts and so on. But the gravitational redshift, which, also call it strong lensing, which really broadens the iron line, and that is again requires very highly rotating black holes in the center, and so on, more like black holes. So this accretion business, which is the reason for this copious emission in all wavelengths of around the AGN, and leads to the powerhouse in the AGN and so on. So then, as I mentioned, the quasars, not very abundant, and they were actually discovered by the radio astronomers in 1963. And so they were optically identified, and they were called QSOs. And this one of the first one was the famous third Cambridge catalog 273 number 3C273. And today we know that this quasar, the nucleus, is extremely bright. It is like 10 to 45, 46 ergs per second, which is like 10 to 11 times more luminous than the sun, let's say. And it has a very knotted jet coming out from this nucleus and so on. And this is this knot, for example, has a luminosity which is rivals that of Seyfert galaxies and so on. And we still really don't know, and the formation and the collimation, etc., of the jets, which people are trying to simulate, and with the MHD and other calculations and so on. So this entire business and one-sided business is also led to the notion of superluminal motion, as we'll see later and so on. So this is just to show that these jet is actually multi-wavelength, and probably different energy particles with different aging as they emit and as they cool down, have a dominant spectra either in optical, X-ray, or radio. And you can see that the old electrons, which are giving the outermost parts of the jet, and you have radio emission, and the fresh input of electrons is very high energy, and you see the X-ray emission on the top, this knot, and so on. And the optical thing is rather complicated, and you see many knots and so on, all aligned, etc. And then you even have a strong bending, which you don't see here, and these other images and so on. So, and this is the thing which leads to the physics and studies of jets and so on. And you have jets which are not one-sided. You have also these double-sided jets. Is one of the earliest is in the constellation Cygnus, just like X-ray astronomer call X1, X2, the radio astronomers call ABC. And so you have this radio emission in red, and you have X-ray in the blue glow in the center. And if you go with a very high resolution thing with the X-ray and radio, you'll see there is a jet which aligns up with this large scale jet, which is then ends up in blobs. And then these hotspots are both visible in radio and X-ray. In fact, they're perfectly matched. And that's why they actually show up white, because in this composite picture. Another example is also the Hercules A, which again, this purple glow is X-ray now, and you have this blue is the radio emission, and you see various blobs and emission and so on. So it's like puffs of smoke coming out, from the central object, and so it also shows that this kind of probably episodic, emissions of particles and electrons, which probably leads to these, rings and complicated billowing of hot plasma. Well, this is cold electrons and so on. and through radio emission. The blazar jets are like this quasar thing, are one-sided mostly, and that is because of this beaming factor, which leads to superluminal motion. And I show an example of superluminal motion on the right here. And you see this is the scale and this is the time so just 8 months. Okay. And so you have this blob which is slowly moving away, and you calculate these velocities which are more than the velocity of the light, and that is the effect due to relativity. And you have this bulk factor of radiation gamma and a very small angle to our line of sight, which leads to this beaming factor, and which also is responsible for boosting the intensity in one side and weakening the intensity on the other side. So you see basically only the one side of the jet coming towards us. So, okay. And this led to then also these kind of radio properties led to another classification, which are named after Fanneroff-Riley, who the people who first came up with this classification. And then you have this type 1, which is a low power edge brightened dark source, and then these high power edge brightened radio source, and so on, with different. So you see the FR1s are quite abundant, even though they are low luminosity, and whereas this high power, of course, are greater than certain luminosity, 10 to 42 here, and they are less abundant, 10 to 1.5 per gigaparsec cube, so on. And then you have these Bielac objects, which are fainter than these very high power radio sources. So they are, but they are a little more abundant. And the flat spectrum radio quasars, which is one of probably the most, the brightest objects, though again, not as many in the universe as we can see right now. Even also this is, we can see only about 10 to 42 and so on. So there could also be some, observational biases here, depending on the luminosity and the telescopes used and so on. And now you have this E-Rosita survey coming up, and we expect to then start this. I think the AI would be the most powerful tool in quickly trying to figure out what kind of objects we are seeing there, and so on. And this is again maybe the kind of scheme that you may have to train your AI with, is like you can have this tree of AGN. And if you take a very broad view of radio quiet and radio loud, and then you can go on subdividing into all these kinds of objects based on their spectroscopic properties. You go on the radio quiet side, and then you go on the radio loud side, mostly based on their radio emission. Plus, you still have strong emission lines, but then because of the power of the jet, which is aimed right almost at you, these lines get very weak. And actually it becomes difficult to take spectra, and you get mostly continuum. And so they get the very strong continuum, except in the very bright, this radio quasar or the flat spectrum radio quasars. Of course, the quasar, because you have strong lines there and so on. So they are easier, and of course, so they are also brighter and so on. And then this whole area is where you have so these are mostly jet dominated, and this is where you don't see strong jets. You have jets, of course. Even in 1984, there was a big paper by these people from Maryland University, where they had taken some hundreds of Seyferts with the VLA, and that's not very well cited, but you had radio emission, even the Seyferts discovered as early as 84. So on. So then people emerged with a unified picture based on viewing angle. So your view is shown by the eye here, and the various features around the supermassive black hole, which is having the central, black hole in the center. We'll see what we have learned recently from Event Horizon Telescope. And you have the disk around here, and then you have dusty absorbers, and the line emission regions of depending on the line widths, or we call them broad line or narrow line and so on. And then you, of course, this goes and gets reflected. You have a torus, which is probably responsible for the very strong dusty emission, absorption, and scattering. And then you have the jet coming out. Of course, jet could come in various directions and so on. And then viewing angle, you can see the classification, radio classification, as well as the optical classification, and so on. So the top half is the radio loud and the bottom half is radio quiet, just to distinguish the different features and so on. Okay, so the blazar sequence, let's come to that, and that is what because this community, and I saw in the program, is blazar dominated community today, and so we have these TV emitting blazars, which we call them extreme high frequency BL-lacs. We'll just show you what the high frequency means just now, or high energy peak. And on the extreme right, you see the status of their emission line properties and so on. And so you have these basically these 5 types of blazars now that we know. Okay, so and this is what I meant by LBL and HBL, the low high energy peak and the high energy peak. So first thing you notice is that these are truly multi-wave objects, because the jet domination is such that it actually powers all the way from radio to very, very high energy gamma rays, like 10 to 24 hertz, going up to TeV electrons and so on. So you have plotted here on the y-axis the nu L nu, which is the total energy output. So this is basically frequency times the L nu, so that you get the ergs per second per wave band, so on. So you have the peak, 2 peaks, and the 2 peaks are shifting. So this color coded. And so you have right on the top is the flat spectrum radio quasars, and then you go down, and this peak is not straight line. You can see it is a somewhat tilted line, and so on. And that is, and similarly here, you see that the thing is, and there is this crossover. And that is very interesting, that this crossover happens between this kind of object and this right in the X-ray. So the X-ray properties, especially the X-ray spectrum, variation and shifts are extremely important if you can cover, especially from the soft to the hard together and so on. And this is where actually the AstroSat capability comes in. And then, of course, you also have the far UV available now, which is close to this site, so you can fix that. And then Fermi is always operating, and you can get, and also the ground-based various MAGIC, Veritas, and so on, which extend you to the high energy and so on. And then people try to understand what are the reasons for these peaks. And these just an indicative thing which was introduced 20 years ago, that you assuming that this jet is coming right from the center, and as it appears from imaging that it is coming from very close to the center on the black hole on the accretion disk. And then there are various possibilities, because the surroundings are pretty messy and so on. So firstly, of course, the jet has electrons or positrons, may even have protons, but let's look at just the leptonic emission, and they will emit synchrotron radio emission. And so that is the simplest thing, and that is mostly considered responsible for the very first peak that you see on the low energy side or the lower frequency side. And then those electrons and the photons which are come out through synchrotron emission can Comptonize. And that led to the notion of synchrotron self-Compton. And that is considered, these two considered one of the natural processes happening here in any case. But there are these clouds and absorbers and other regions which can lead to what is known as external Comptonization, or EC. Okay, and depending on what are the seed photons available there, you can have external Comptonization from clouds and so on, or various kinds of direct disk radiation and so on. And then you can also have reflections. Okay, so that is shown here, that you have reflected synchrotron emission. So you have synchrotron, you have SSC, and then you have various kinds of external content, and also you have reflection and so on. Now it is not easy because the observables are not as many as the possible likely model inputs and components here and so on. This is just to illustrate one of the very interesting object that we have been studying, is this OJ287, and there was a gamma ray flare in 2009, and then you could see the superluminal motion simultaneously, which could be correlated directly to this gamma ray flares and so on. Okay, so this is GeV, and this is an X-ray in keV. And then you have the red filter, and then you have the radio, different wavelengths, and like 3 millimeter to 250 microns microwave. And then also you have the 7 millimeter, 8 millimeter here, and also the CO band. And you could see that of course, these things seem delayed, and you could then figure out what the regions are. But these were very well nicely correlated to the VLB imaging going on. And so the emergence of the spot, a new spot, could be was the thing considered responsible, and so on. And then, of course, as it goes away, there's a deacceleration apparently. So this was the work that was then done by Pankaj Kushwaha, who was my student that time in 13 to 15 and so on. And then we looked at the higher resolution in the time scale, and looked at divided the flare into various 3 parts, and you could see that the spectrum in gamma rays was changing. Also in X-rays, the spectrum was moving during this flare time and so on. And then tried to make what we call the one zone model for this. To understand this kind of emission, you assumed a certain spherical region which is moving down the jet with some bulk Lorentz vector gamma at a small angle, giving you the Doppler boost of delta. And then there is assumed there has to be some kind of magnetic field entanglement, and then the particle distribution coming from the center, which is producing synchrotron and other emissions, has these spectra with the normalization constant, and then P and Q as defined in the shape of the spectrum here, and so on, with some minimum energy, etc. So these are the parameters that govern the emission properties in a simple fashion, and we understand the energy distribution. So this SSC model was used in here, but as I told earlier, that the observables are not too many, and so on, but you can actually have, these are narrow bands when you talk about, something like 17, 18, decades of bands here. And there are, of course, gaps which are not observable due to various constraints of observation. You don't have this region because you don't have a good Compton telescope. And you have only the hard X-ray up to here, and then you have very high energy with the pair production starts, and so on. So you don't have a detection technique in this region where the Compton interaction is the maximum, etc. And then again, there are these various absorption bands in the sky, and also from the Earth, and so on. So, but you can make an attempt, and this is what you try to do, that when you do this, just use that model and you find synchrotron. The self-synchrotron is not sufficient. So you have to add some cooling due to the external Compton, and which could come from disk or torus or the broadline region, photons, etc. And then you can actually fit the entire this distribution of double hump peaks in this particular source, for example. And you see that in state 1, the 3 things I mentioned earlier, it is changing, and it's changing pretty fast, in a day. And this kind of leads to some estimates. I will not, these are not really fits, because you cannot do a good statistical fitting job with satisfying all the statistical criteria, but you have some idea of what the parameters are like to match up with these observations and curves and so on. So you can get some fix on interesting results, which were like the okay, what is the origin and does it match up? It turns out that those toruses and the other regions which are seen as ejected out in the VLBA and so on could be the ones which are responsible for the various external quantization and so on. Okay, and you get some idea of what is the jet power required, what is the total radiation and so on. Okay. So, but then we have with AstroSat, and this was interesting that we were able to convince the new star people to observe simultaneously with us. And this was in 2017. We got a simultaneous observation with the AstroSat S60 shown in black and the two detectors on the new star. And it's extremely satisfying that with the same normalization and with the same parameters, the fits to both the spectra, and you see the residuals here, was excellent. Okay, and no systematics were needed or required here, and so on. So this also gives us a very interesting boost to the how good the calibrations are, and so on. And then we didn't have the same luck with 2018, 2020, and you see the things are changing and these are actually, this source is very weak. So this is based on several days of data added together. And the interesting states it went through. And if you take the new FNU like this, you can see that of course, with the new star, we have this kind of a shape, but then it is changing drastically in 18 and 20 from these observations, etc. So this is almost work done and finished almost, and just waiting to be submitted after all the co-authors and so on. So then we have, in the same observation, we have this was the data that we were waiting for 3 years, and finally we got it, and especially 17 and 18, we had simultaneous far UV observation in 17, and then of course only far UV in 18. And here we had near UV also, and there's a slight variability, but not much. And then we can put together the X-ray and the UV observations, and we have done the modeling based on these curves with the synchrotron and various external Compton effects and so on. Okay, so we are these are interesting results coming up. Another thing which has just been submitted a week ago is this work done from a very long observation shown in black here with AstroSat. Extensive, and this red is basically just a swift XRT daily sparse, much sparser coverage. Then, but that's the advantage. The Swift can only do once a day or something, but when we can do 14 to 16 times a day on that source when we are observing, and that gives a different kind of cadence in these with AstroSat, and so on. And you can see we can split it up, these two observations, and you see the behavior on this thing. You have this beautiful observation in S60 and matching with XRT. So the XRT points are these red stars and so on, and then we have, this is the breakup. So that is what I meant, that you have, but you match up very nicely. And same here, where you have only one Swift, etc. So we do have this beautiful structure thing that we see. And so and just to show you that the lax species also shows a similar behavior in both the cases. And but it shows much larger amplitudes and depths in the hard X-ray compared to the soft X-ray and so on. And so you can do lots of spectra, and we can try to get these various models fitted all the way up to 20 kV with the 60 and lax PC. Again, a wonderful fit no systematics required, and everything matching perfectly. And of course, we use a log parabola model, which is supposed to describe the blazar X-ray emission much better. And we find that this is in fact true, as I'll show you later, that whenever you have a high bright source and good quality spectra, power law doesn't work. Okay, and so this is a representative thing that we have from various states of SXT and so on. And then you have the Fermi observations here. And then you have some other observation for very high energy matched up here. And you see this beautiful clear hump. And this is still under kind of embargo at this stage. And this particular thing, we fitted with multiple shocks in a diffusive shock model for a jet in a turbulent medium, which was the, done by Botchers and other who are part of this collaboration and so on. And you can do both the light curve fitting as well as the energy density fitting. So this multiple shock diffuser basically Fermi first order process also invoked for supernova remnant shocks, for example, and you have magnetic field which acts as mirrors, and you gain energy, the electron through this crossing through the different going excursions through these mirrors of the magnetic field. And so you have a kind of converging flow, which kind of explains the direction of the jet, etc. And then these particles are scattered by waves and they cross the shock many, many times. So this is the field at the shock fronts in the jet and so on. And that leads to this energy of gaining the energy, particle gaining energy, and then doing synchrotron and quantization, etc. And this is also, we have another work going on. You can see the people below, and this is almost getting ready. We have this NUV, far UV, and of course much longer soft X-ray light curves. Nothing very drastic happening. There are small variations and so on. So this is another. This is a huge study that I'm just finalizing with the based on UV, multi-wavelength, SXT, LAX-PC, and so on. I'll show you the examples here. We have, again, beautiful fit with the log parabola models with the SXT and this, I'm showing you the photon spectrum, so you can actually see how much the difference in the normalization actually is. We didn't require any systematics to match up here. And so within the errors, we have excellent fit with absolutely the same model. Okay. And even get better with Markarian 421. And so this is the list. And this is what I was mentioning, where you have a powered law and you have a bright object. The reduced chi-square is 3, whereas the moment I have a log parabola model, I get down to 1.5. And this is the case with almost all these bright objects. And this is where we also had simultaneous LAX-PC detection. This is upper limit here because the sources are very, very weak in the soft X-ray. And so you get where we have bright sources. And example 421 is the brightest, and you get excellent spectral characterization. You go from so I make sure that the redshifts are incorporated, and because these have various different redshifts and so on. And you get, for example, even this ETA, and then you have 501, 14.6, and so on. And now I want to move on to a slightly different topic, which may be interesting to some people here, is that there are these long-tailed or narrow-angle tailed radio objects, which are usually, almost certainly, found in the clusters of galaxies, especially the ones with the strong cooling flows. So this was something we had discovered in X-ray in '87, one of the first cooling flows in the universe. And then immediately I joined with one of my friends here in Ooty, who's no longer doing astronomy, Patnaik. And we used that OSRT, which many people won't even be aware of. Before the GMRT came up, there were small cylinders put up by Govind Sarup on the hills surrounding the main cylinder. And that was the Ooty synthesis radio telescope and so on, which doesn't exist anymore. And we actually got this beautiful long radio tail, and which you put in this X-ray perspective. But you see the size is huge. This is like half a degree cluster gas, which is, for astronomy standard, it's a very large thing at a redshift of 0.35. And so you have this radio thing dangling around, and you saw that then we immediately did VLA, but that data was taken over by Sarazin, and he found that you have this tail, but in high frequency, going from 327 megahertz now to 15 megahertz. The tail doesn't extend that long. In the low frequency, you have this tail extending all the way. And you also have some other radio sources, and you have a double the source, which is matching up with this number 1 in the center. So there's a amorphous diffuse halo source in the center, and so on. And now the situation is that you finding these things, these are interesting. So this is a green in radio, and then you have purple, white, this is in the blue in the X-ray. And you see there is a kind of a cavity formed out, and the radio plasma, those goes out and bubbles. So you create X-ray cavities around the region where the radio bubbles are, and so on. And this is now considered and something that we proposed in 88 as due to buoyancy of the plasma on the hot X-ray, kind of floating on the hot X-ray gas, and so on, which is now well recognized effect. And you have many such objects. For example, going back to the M87, the very first jet that was recognized and much being studied now by the EHT and so on, you see that it has a very complicated emission. You have not just the jet, you have these huge bubbles, and then you have these rings and so on. And so you do some kind of unsharp masking and to bring out these high discontinuity features and so on. And you have, this is the overall very low frequency, 90 megahertz. These are somewhat higher frequency observation. And you can identify various features on not just the bubbles and the smoke rings, and all kinds of things going on. And they're actually showing that this has been happening over on a very dynamic time scale and so on. So, and this is the same thing. You can see Chandra and radio view here, and so you have this large field view at low frequency superposed on the X-ray temperature map. So this is the X-ray temperature. The contours are radio, and so on. And then you have again this the X-ray arms. So this is again X-ray image. And then this is the radio image I showed you earlier. Okay. So now, so this is what M87 jet is, and this is of course an AGN. And you have, as you go down deeper and deeper into this thing, and you see the jet here, and then you see even more details of the jet. And you go to half a parsec, then you go to 1/20th of a parsec, and then of course you go to the EHT scale. And you have this so-called the map of the very core, the center of the imaging of the accretion disk, which has been bent through the relativity effects to look like a circle, and with a hole which has been called the shadow of the supermassive black hole in the center, and so on. So you have this central region. I probably just skip this, is pushing it again. So I'm just trying to see where the origin of the jet is. And so you have the well understood theoretical physics, which tells you that of course there is an event horizon, which is 1 Schwarzschild radius. Of course that applies to a non-radiating black hole. And you have, this is the singularity. And then you have the photon sphere, and so on, which is 1.5 times the Schwarzschild radius, and so on. And there is also the ISCO, the in between, which is the region which is around 2 times Schwarzschild radius, and so on. And so that is the innermost stable circular orbit, and so on. So to which the particle, or which defines your innermost region. Okay, this is around 3 RS for non-radiating black hole. And that defines what is the innermost edge of the accretion disk. And that is very important. And people trying to understand this thing through the time lags and so on, from the very high variability seen from the center, because you cannot really I mean, till EHT is something that can be used only up to M87, which is the nearest supermassive black hole, okay, other than our Milky Way galaxy. The Milky Way galaxy black hole is smaller, and it turns out that the sizes, physical sizes and so on the Milky Way galaxy black hole, due to its 100,000 smaller black hole mass, etc., are identical, but the galaxy Milky Way is much more complicated in the center and low power source, etc. And so M87 was the first to come out with these kind of imaging, as you must have seen this. It's released in 2019, 2 years ago, this bright ring and so on. But what has come out just a month ago is the actual image at the very center using polarization measurements, okay? So you now can actually see the base of the magnetic field structure near the event horizon, and that is from where the jet comes out, most likely. And you see these, you can map the toroidal magnetic field. So it is not, it was assumed in the models, you know, that you have all these kind of magnetic fields, but now you have to work out the types of magnetic fields you have and how these toroidal, radial, and the vertical components of the magnetic field, which is mapped by this EST team led, you know, so this is alphabetical order for the EST team. And so you have the various mechanisms proved, and this is in APJ letters now in April and so on. So I will stop here and give you, so this is the resolved image due to polarization. Okay, and gives you the density and the temperatures, electron temperatures required in the plasma, and the estimate of the magnetic field is like 1 to 30 Gauss. So I will leave you with this image, and which is very fascinating.
Using NASA's Chandra X-ray Observatory, astronomers have seen a famous giant black hole in Messier 87, or M87. Is propelling particles at speeds greater than 99% of the speed of light. The Event Horizon Telescope collaboration released the first image of a black hole with observations of Messier 87 last April, making it arguably the universe's most famous black hole. Meanwhile, astronomers have studied a jet of high-energy particles powered by the black hole, blasting out of the center of M87 in radio, optical, and X-ray light for many years. Over its 2 decades of operations, Chandra has observed M87 many times, and now researchers used Chandra's data to determine that sections of the jet in M87 are moving at nearly the speed of light. While astronomers have observed features in the M87 jet blasting away from its black hole this quickly, at radio and optical wavelengths for many years, this provides the strongest evidence yet that actual particles are traveling this fast. When matter gets close enough to a black hole, it enters into a swirling pattern called an accretion disk. Some material from the inner part of the accretion disk falls onto the black hole, and some of it is redirected away from the black hole in the form of narrow beams or jets of material along magnetic field lines. Because the material can fall onto the black hole erratically, the jets are made of clumps or knots that can sometimes be identified with Chandra and other telescopes. A team of astronomers recently used Chandra observations from 2012 and 2017 to track the motion of 2 X-ray knots located within the jet about 900 and 2,500 light years away from the black hole. The X-ray data show motion with apparent speeds of 6.3 times the speed of light for the X-ray knot closer to the black hole, and 2.4 times the speed of light for the other. While this sounds like it breaks the laws of physics, it's actually an illusion that occurs when objects are traveling close to the speed of light along a direction that is close to our line of sight. The jet travels almost as quickly towards us as the light it generates, giving the illusion that the jet's motion is much more rapid than the speed of light. In the case of M87, the jet is pointing close to our direction, resulting in these exotic apparent speeds. The Chandra data are an excellent complement to what the Event Horizon Telescope, or EHT, found. The jet Chandra sees is 500,000 times larger in size than the ring imaged by the EHT. Another difference is that the EHT observed M87 over 6 days in April 2017, giving a recent snapshot of the black hole. The Chandra observations investigate ejected material within the jet that was launched from the black hole hundreds and thousands of years earlier. Astronomers are looking forward to seeing what else these telescopes can learn about black holes in the years to come.
Yes, no.
So let's thank Professor Singh for this interesting and wonderful talk. And now we have a few minutes.
Yes, A group of. A group of.
If you have any question, unmute yourself and ask the question directly.
Shivendu, may I ask a question to Professor Singh?
Yes.
Thank you, Professor Singh, for a very elaborative talk on jets and can you hear me properly?
Yes, I can hear you.
Yeah, I can actually have a lot of feedback. My question is regarding the last slide.
Yeah.
Shown the magnetic field structure, which looks very symmetric. However, in M87 image, however, the actual M87 shadow image does not look that symmetric in flux domain. Do you have any comment on that?
Yeah, so the that is the actually the image of the accretion innermost ring of the accretion disk in some sense. Okay, and and it is the brightness. Apparently, they have seen a day-to-day variation on the bright knots and so on. So it's again probably a beaming effect on one side more than the other, as you see in the jets, so on. So it's not very clear either to me what leads to this asymmetry and so on. But this more interesting feature is that you see the fields are also shown different strengths. On the vertical magnetic field, brightness is different than the one on the toroidal magnetic field, for example. Okay. So these one needs to get into a little more detail, and I have not, frankly speaking, read this paper completely yet. Okay, I just saw it 3 days ago. It's April 10 issue. It is coming out in FJ.
Thank you, sir. It looks very interesting. Maybe we can discuss sometime.
Yeah.
So any other question?
उसके माइक में प्रॉब्लम है हमारे
Pankaj.
Pankaj, do you have any question?
Yeah, can you hear me?
Yes, I can.
I don't know, it's too much echo, I think. So
Yeah, there's echo.
माइक ऑफ
I think KP will have to mute the mic. That's the echo coming.
Yeah.
Yeah, now you can ask the question.
yeah, okay. So my question is about the jets in the galaxy cluster that you talk about. So if there is any form, study or prediction that they are energetic enough to be seen at, let's say, in gamma rays or some other, because the field of view of gamma ray is very, very large. Yeah, I think you need to unmute. Probably.
I don't know why I'm getting muted. I'm not doing it. It just every little while I'm getting muted. So I think there are some, this MET7 has been probably seen in the gamma ray. I have to check up in the Fermi and so on. But the other, they are not as powerful in the center. They are more dispersed as these quasar and blazar jets are. They are on the weaker side.
Okay, lot weaker side, right? Yeah. Okay.
So any more questions, audience? Still the echo is coming. So if there is no more questions, then let's thank again Professor Singh. So we'll have a tea break now. Unfortunately, tea breaks are not so interesting in online mode, but I hope that you guys can arrange the tea for yourself. And let's meet after tea at 11:15, and we will have many more interesting talks. So see you.
Shivendu, can I test it?
Yes, you can. So you can you share your screen?
Yeah, sure.
हाँ
एक बार देख लो टेस्ट ये और आई कैन शेयर Amit, can you share your screen?
Yeah, I'm just trying it.
Okay. Yes. Yes, can you change the slides also? Then let it be like that. Yes, yes. Okay. No, just checking slides. After checking. Oh, sure. Just leave it. Yes, that's fine.
Shall I stop the sharing or left it like this?
Keep sharing on, so that's fine.
Yeah, you can keep. Yeah.
Because after the break, you will have the first talk. So. Yes.
Okay, sure.
Okay. एक वो फीडबैक आ रहा था ना बीच में उनके साइड से
ठीक है।
अभी और लोग आएंगे सर? नहीं, यहाँ बहुत कम लोगों को अलाउ किया गया है, क्योंकि जब से कोविड का केस आया है, यहाँ हम कोशिश कर रहे हैं कि मिनिमम लोग रहें। सभी लोग ऑनलाइन, लेकिन जो यहाँ से बोलेंगे उनका फोटोग्राफ ले लेना। और अभी मैं प्रेस नोट टिक कर रहा हूँ।
So welcome everyone again. So now we'll have a talk by Amit Shukla from IIT Indore, and he will talk about gamma ray flares from relativistic magnetic reconnections in laser jets. So Amit, welcome, and you have 30 minutes. So 25 minutes for presentation and 5 minutes for question answer. So you can start now.
Thank you, Shivendu. I believe I'm audible to everyone.
Yeah.
Okay, thank you very much. I start with thanking the organizing committee for inviting me to present this work. So today I'm going to talk about the flares, basically from blazars, and it is believed earlier, let's say past 5 years before, it was believed that most of the flares from AGNs or from the blazars are dominated by shock acceleration processes. However, over the last few years, this particular scenario is about to change, and I'm just going to talk about one of the results which we have obtained recently. This particular work has been done with the collaboration with Professor Karl Mannheim from University of Würzburg. And I also like to thank Professor Singh for very elaborative talk on jets and AGNs. So actually he laid a background for me, so I can just start with my results. And thank you very much for inviting me for this talk. Okay, so already he has already discussed this part, that the first observation of the jet was made almost 100 years, and it took 100 years to actually grab the image of the black hole shadow. However, by EST group, however, we still do not understand what is the main mechanism by which these relativistic outflows or jets are launched. There are several theories, and one of the most dominating or interesting theory given by Professor Roger Blanford, where he suggested that rotational energy of a black hole can be tapped, and that can actually support and sustain these relativistic jets. And that, I request someone to please mute. Yeah, thank you. So Professor Blanford has suggested that tapping of rotational energy of a black hole can actually sustain these relativistic jets. And here I am just showing one of the simulation made by EST collaboration, where they have considered the Blanford's NAC process, which can actually give rise to the very fast moving relativistic jets. And as you can see here, the black hole is rotating and actually twisting the magnetic field. And you will also see that due to some of the instability and change in the magnetic field actually produces a change in the flux at given radio wavelengths on which this particular simulation is obtained. So now what is the current scenario? What is the current problem? Using the imaging techniques, now we can actually grab the image of black hole. However, we still do not understand how this rotational energy or magnetically dominated jet, if it is, how this magnetically dominated jet, which is a Poynting flux dominated, is converted to kinetic energy dominated jet, where this particular change used to happen. So to understand these such questions, we have started a very systematic search using the Fermi lat observations, and which I will cover in next few slides. And yeah, so here very briefly, already Professor Singh has discussed this about the active galactic nuclei and blazars, but very briefly I'll just like to say a couple of lines that active galactic nuclei mostly host a supermassive black hole, and they are very luminous due to the accretion from the accretion disk onto the supermassive black hole. And sometimes we observe some outflows perpendicular to the disk, and if these outflows are relativistic and collimated, we call them as a jets. And most of these jets actually emit non-thermal emission, sometimes even up to the very high energy gamma rays. And if these jets are aligned to the line of sight to Earth, then we classify these active galactic nuclei to either to a class called blazars. And blazar further can be divided into several classes, but broadly you can divide it these blazars to two classes. One is BL-lac sources, another one is flat spectrum radio quasar, depending upon the emission line present in the optical spectra. The broad, if I speak very broadly, these particular blazars show two humps in their spectral energy distribution. The first hump is attributed to the synchrotron emission. However, the second hump is still under debate. There is no consensus in the community. There is a belief that most probably the high energy gamma ray bump is due to inverse Compton scattering. It could be synchrotron self-Compton or external Compton. However, there is also possibility of photopion decay or hadronic processes. So either proton can interact with another matter, or a photon and produce pions, neutral pions, and further decay into the gamma rays. And detection of a neutrino by IceCube in 2018 has opened up the scenarios and a lot of possibility. One of the other interesting thing about blazars that they show a lot of variability, and the emission, which is in AGN jet frame or blazar frame, is isotropic, actually get beamed in the observer frame. So you will see a very small, you will observe a radiation or emission from a very small narrow cone, which is beamed towards us. And that actually makes a lot of transformation in energy as well as in the time frames. So the observed time frame at the observer is actually divided by the Doppler boost. Now, I will start the actual presentation where we discuss the problem which I am working on. So I have already explained what can be done through the imaging technique, but here I would like to tell you what cannot be done through imaging technique can also be done through the time domain astronomy, which we have done. Here I have shown you 3 or 4 plots, or basically a time series of a few active galactic nuclei, mostly blazars. Blazars are known to vary over the very long time scales, from decades up to the very short time scales, up to a very, let's say, few minute time scales. So here the first observation or first plot is from NGC 1275, where the source is varying over the entire Fermi era from 2007 to 2019, and the flux is slowly increasing. This is quite common. These trends are observed in several sources. We have also observed the day time scale variability, which is shown in the second, or I would say, the third panel. You can see the observation from flat spectrum radio quasar CTA 102, where we have observed a day scale variability. This is also very common. Now, CTA 102 also show a hour scale time variability, or which we call it intra-night or intra-day variability, which is very common in optical astronomy. This kind of intra-day variability is quite rare in blazars. Still, a lot of people have observed it, but still they are rare. Not a lot of sources show this variability, and when they show, they are at the a high flux state. These intraday variabilities are not observed when the source is quiescent or moderate flux state. And the fourth one, which is the most interesting one, is the minute scale time variability, when the source has changed its flux state from one to another. Let's say the flux order of flux has changed from 1 to 2 or 1 to 4 within few minutes. And this has been first observed by MAGIC as well as Hess telescope. MAGIC has observed from Markarian 501 and Hess has observed from PKS 2155-304, and they have shown that flux can change over the time of, let's say, 3 minutes. And that is shown by Arihonian et al. In 2007. The flux, and they have shown a remarkable flare which has several rise and decay and showing flux can just vary over the few minute time scales. Now the problem comes, why we are so bothered about it? Means sources are variable, we have very high Lorentz factors, we can just simply accommodate very high Lorentz factor into the our models and simply explain this variability, that saying that in observer frame variability is short, but actually in the jet frame variability is not that, the source region is not that small. However, so this was the case in 2006 or 7 when I started my PhD, and over the next 5 to 10 years, what we have realized that considering high Lorentz factor will not solve the problem. And this will only solve the problem in BL lax sources where we do not see any or observe any broadline region clouds. So they cannot emit Lyman alpha photons, and gamma rays from even from the very inner core or inner jet can actually escape. But however, if you observe a variability or fast variability from the BL lax sources, from the FSRQ sources, that will not be possible to explain through just considering a high Lorentz factor. And considering all these scenarios, there are several models were put forward, and one of the more interesting thing happened in around 2010 to 2013 or 14. A lot of particle in cell simulations suggested that actually shock acceleration is not efficient in magnetically dominated plasma. So it was sort of consensus that shock is not the main driving force for the blazar variability, but there are some other possibilities. So people started looking to some other possibilities as well. So this was the actual picture in, let's say 2010, 2011, that from the BLX, that the source can show a variability of order of few days, sometime even intraday, and sometime over the day scale. If you see the intraday variability, it is considered the emission zone is inside the BLR or much closer, less than a parsec away from the central engine. And if you see higher, longer time scale variability, then source is much farther in downstream. But this fast variability poses a lot of constraint on shock acceleration. So people started coming up with the solutions, and the first solution was increase the Doppler boost, or Lorentz boost or Lorentz factor. However, it does not solve the actual problem. Then people have already proposed plasma instability, even including us. We have said that, let's say, if you consider fire hose instability, that can disrupt the jet and produce very fast decay in the flux. However, this particular instability scenarios only explain the decay part of the jet, and it disrupts the jet. Then there are some other models, such as star-cloud interaction, magnetospheric gap models, where emission actually takes place from the ergosphere of the black hole. These models are can explain the fast variability from the BLX sources. However, they cannot explain any variability of the order of few minute time scales from FSRQ, because if the emission is within the BLR, it should be absorbed and we should not see it. So once MAGIC has observed a TV flare which was variable over the 15-minute time scale, it was very clear that just boosting the Lorentz factor will not help, or all these models will not favor or will not explain the very fast variability. So to keeping in mind these problems, these fast variability, we started a systematic search. We thought, let's look into the Fermi lag data, look for the FSRQs, and look for the fast variability if we can find it out. So what we have done, we have considered almost 10 years of Fermi lat data, and Fermi lat actually observed gamma ray photons from 20 MeV to 300 GeV, and within almost 3 hours it completes almost entire sky. So it surveys entire sky in almost 3 hours, and it has a very good so it basically work on pair protection telescope technique, where it uses silicon strip detectors for the tracking and cesium telluride crystal as a calorimeter. However, I will not go into the detail of the detector, but these informations are available with our publication and as well as on the NASA website. So anyone can just go and check it out. Okay, so what we have done, we have chosen almost 100 bright blazars, including most of them are FSRQs, and some of them are BLAC. And using some of these algorithms, we have started looking for the fast variability. And we have used almost 10 years of data with 100 sources. And the first result, what we have achieved, that we in around 2017, we have observed CTA 102, or in the data, what we have found that CTA 102 a flux variability of order of 30 minutes. And look, it's a black hole mass, it's around, it gives you in time domain, it gives you around 150 minutes. So the time, the RG or Schwarzschild radius is around, give you a time scales of around 150 minutes. It means it takes time, the light takes 150 or 140 minutes to cross the event horizon for a non-rotating black hole. And for the maximally rotating, it's around 70 minutes. Okay, and what we have observed, the variability time scales with 6 sigma, it was just 30 minutes, which is almost 20% of the black hole size. So this is the first time with with a very good confidence, with the more than 5 sigma confidence, we have detected a sub-horizon scale variability from any flat spectrum radio quasar, and that is basically putting a very strong constraint on the particle acceleration process. As I have already explained, that the intra-day or intra-night or basically sub-hour scale variability cannot take place inside a broadline region emission cloud, because if it takes place, the the Lyman alpha photons will basically interact with the gamma ray photons and produce the pairs. So you will not able to see any, you should not see any gamma ray emission on the time scales less than a day or so from any flat spectrum radio quasar. So considering this particular scenario, we have proposed that might be in CTA 102, we are actually seeing these particles are get accelerated through magnetic reconnection. However, still, there are several magnetic reconnection models, and they have predicted a very peculiar pattern in the light curve or in the time series if the particles are accelerated through magnetic reconnection. However, in this particular result, we could not see that particular pattern. And that pattern is basically tells us that there is a slowly varying envelope, and on top of that, there is a very fast moving flare. So you will see an envelope which slowly increases over the few days time, and then at a certain time over this envelope there will be a very fast flare of the order of, let's say, 1 hour or so, even lesser than an hour. So we started looking for this particular pattern in our Fermi-Lat observations, and the cherry on the cake has arrived with our next result, which we obtained in 2018. And we have observed from flat spectrum radio quasar 3C279, there are 3 flares. And these 3 flares are very interesting. They are very identical in, if you look their temporal behavior. So these 3 flares, so you can see the light curve on the left top corner, and the black dots are actually 1 day bend light, 1 day bend average, and different colored points are actually 3-hour bend light curve. And as you can see, all these 3 flares look very similar. And if you also see their spectrum, so we have fitted their spectrum with the log parabola. And what we have found that their curvature parameters are very similar. And these temporal as well as spectral parameters suggest that we have all these flares might have originated from the same process as well as co-spatially, or almost in the same place in the blazar jet. We have observed the rise time from these flares of around 1.5 days. And out of these 3 flares, first two flares show very interesting results. The first flare actually show a very interesting spectrum, which I will not talk about it because it's already part of another publication. However, the second flare has shown a very interesting peak in peak behavior. The first flare also showed the peak in peak behavior. However, that is not that strong, but the second flare shows a very strong peak in peak behavior or pattern, which is predicted by magnetic reconnection models. It means we have seen a very slow variation or slowly varying envelope, and a very fast moving flares are superimposed on this slowly varying envelope. And during this particular era of, let's say, half a year, for each of these flares, we have observed very high energy photons associated with these flares. We have observed photons up to 100 GeV from a flat spectrum radio quasar, which were not observed earlier from any flat spectrum radio quasar. So that tells us that that the emission is actually happening outside the broad line emission region. Now, here is the zoom of the second flare. As you can see on the left top panel, there is a light curve of a second flare with 3 hour bin light curve shown in the blue with the blue points, and the red points or maroon points shows orbit bin light curve of 96 minutes. So you can see there is a envelope, a blue color points. You can see there is an envelope, and almost just after the mid of the envelope, there are 3 fast flares. So these flares has shown extremely fast flux variability, and from the starting of the first flare, as you can see, there is a gray line plotted on the first point, or I would say the second maroon point. We have looked this particular orbit and looked for the fast variability. Actually, we have checked all the orbits for the fast variability, and only few orbits we have seen the signature of the fast variability. So here we have seen, so if you see the bottom panel, here we have observed we have binned the light data with 3 minutes as well as 10 minutes bin. The points in the red and maroon, or which is basically changing with the significance, are 3 minutes light curve, or I would say the circle one are 3 minutes light curve, 3 minutes bin points, and the square ones are 10 minutes bin point. And here we have observed 8-minute flux variability with 4.8 sigma, and around 12 minutes of flux variability more than 6 sigma, which confirms that we have, for the first time, we have seen a flux variability from the 3C279 with so much significance. And this is the one of the brightest flux state from this particular source. And this also confirms that for the first time we have observed from any high energy telescope, from 3 Cherenkov telescope, MAGIC has and Veritas and Fermi, for the first time we have observed a peak in peak structure from any light curve, where a very slowly varying envelope emission is observed, and on top of that, extremely fast moving flares are observed. Now we have again done the spectral analysis for the slowly varying envelope as well as the fast moving flares, and what we found that again the spectral the curvature parameter, we have used the log parabola to fit the spectrum. What we have found, the curvature parameters is again very similar, suggesting that these gamma ray flares, which might be originated either through the inverse Compton scattering or photopion interaction, but in any case they have suffered or they have interacted with the same seed photon fields. In either case, when it is inverse Compton scattering, then also they have interacted with the torus photon field, which is infrared, or if it is a photopion interaction or a hydronic process, then also they have interacted with the same photon field for both, so for the slowly moving envelope as well as the fast moving flare. And that tells us that these emissions are co-spatial, and that is very important to further demonstrate that what is the particle acceleration mechanism which is dominating the blazar flares. So in almost in 1980s, basically suggested that I have already discussed, but that he suggested that the black hole's rotational energy can be actually tapped, and the ordered can be tapped, and the ordered magnetic field basically moves along with the black hole and get twisted at some point when information actually weakens. These ordered fields are prone to kink instability, and through kink instability, the jet get disrupted, or basically the spine of the jet get disrupted. There are when the jet get disrupted to the kink instability, there are current density patterns are prone to magnetic reconnection in the these small filamentary plasmoids actually start interacting and start magnetic reconnection. Some of these magnetic reconnection energy actually goes through these, and some of these plasmoids during this interaction also, and they also carry some of the energy magnetic reconnection, and basically they form a mini jet. It's been shown several particle in simulations. Also suggests that the size of plasmoids could be can also reach up to the 10% of the volume in which the magnetic reconnection is happening. So this is the light curve is shown at the bottom panel, or this is basically a schematic. So this is what was predicted by magnetic reconnection models. So they predicted that there will be a slowly varying envelope, and on top of that, you will observe several fast moving flares. So as I've already said, we have looked for this particular pattern, and here it is. We have actually observed it with from 3C279 data.
Amit, you have 2 minutes left.
Okay, all right. I'm almost done. Thank you. So this is for the first time we have observed this particular source from this particular scenario. And here there are, we have also, as we have already observed the predicted light curve, we have just tested against the scenarios that this cannot be originated due to any other possible method. So there are three possibilities. That first thing is the emission, the entire flare, as well as this fast moving flares and slowly varying envelope actually originate inside the BLR. That cannot be possible because we have seen the high energy photons. The fast flares can evolve or originate inside the slowly varying envelope outside. That can also not be possible because we are seeing a very similar spectrum, and that tells us strongly that if this is the case, then the fast flare has seen much more photon density from BLR and torus and from the disk. So the curvature should have been different, which is not the case. So that is basically telling us it is a co-spatial. And in the co-spatial case, there are two possibilities. One, it could be originate at the recollimation shock. But if we consider recollimation shock, then it will be basically you require very high Lorentz factor. And same with the case if you take fast flare as well as slowly varying envelope emission zone outside the BLR, you required very large Lorentz factors. However, in the magnetic reconnection, you just required a very reasonable Lorentz factor of around 35, which actually requires to make the jet not super Eddington. And the gamma ray photons produced by synchrotron cells should not produce pairs within the emission zone. So it's a very moderate Lorentz factor is required for magnetic reconnection. And using the model parameter have actually obtained the theoretically we observe possible variability time scale flare. So we observe the time scales for the envelope emission, and using some of the parameter try to obtain what possible flux variability time scale for a fast, and it comes out to be 8 minutes, which is very matching with the observed one. And consider when Gauss magnetic field 0.486 match the the overall flux during the fast flare as well as the emission. Now is the part that we believe that instability disrupt the jet through when it. Basically, we have an ordered field which is at some point where the jet gets disrupted, where the recollimation ends in the jet. At that place, instability dominates and disrupt the jet and produce lot of current density to magnetic reconnection, and there is a formation of plasmoids that act as a mini the existing and produces these fast flares as well as and the entire emission zone or magnetic reconnection zone provides emission to the slowly varying envelope. So we have just put our model image 29, and they have proposed that around 0.4 parsecs they believe that more taking place, and what found that region is around 0.48 parsecs, which matches very well. And finally, we believe that a rotating black hole is through Blandford-Znach process is sustaining this jet in 3C279, and our publication got a lot of media attention as well, and it had a lot of news were published in all languages globally. And finally, this is the last slide where I just like to say that the next few years will be basically a time for a time domain astronomy, and most probably through Cherenkov telescope array. Here I have shown these two observations which have changed the course of blazar variability and given us very deep information about the mechanisms by which flares can be produced on the left, but we can only do it when the source is extremely bright. CTA will do it when event source is in quiescent. So a lot of science is awaiting with CTA. So I would invite all of you, whoever is interested in CTA, please join us with the writing this particular proposal to the government. Thank you very much.
So let's thank Amit for such a wonderful presentation and review. We have now time for one question, I think, and one question is already there. So the participant who is asking the question can unmute himself and.
Hello. Hi, Amit.
Yeah, Amit. Okay.
Hello.
Yeah, we can hear.
Yeah, this is Indranil.
Yeah, hi there.
I have many questions. Hi.
Please.
Nice talk. I have many questions, but I will just restrict to just one. A little, coded message. 2 questions in one.
Sure.
So you see, the equipartition arguments gives the magnetic field around 1 kpc around 0.16 Gauss, 0.2 Gauss, and so on. And of course, as you said, that the Lorentz factors required to previously required was very high, more than hundreds of
yes.
Lorentz factors, which is also a little bit weird. I mean, nature cannot be all the time extreme. The point is your magnetic fields. So is there a trade-off between the estimation of magnetic field and the Lorentz factor? Because that's what I said, that the most AGNs, the magnetic fields of these jets around 1 kpc is 0.2 Gauss, 0.1 Gauss, something around that. Okay.
I'm talking about magnetic field at almost 0.5 parsecs.
Okay, so even the core estimations are around that. Okay, a little higher, but not much high. So what should be the magnetic field estimation if your Lorentz factor has come down from hundreds to 35, which is high, of course, but not as high.
So, okay, so what exactly this model provides us that we actually we required high Doppler factor, and that is because the newborn jet is actually favoring the line of sight, and that is why the actual Doppler boost increases. And that makes the flare go narrow and high in luminosity, because flux goes by delta Q, and the variability goes as a delta T divided by Doppler factor. So for the, if I model, I could not get enough time to explain this, but for fast moving flare, the Doppler factor is around 80.
Actually, the question comes from physics concerns, because if it is moving at 35, Lorentz factor, around 35 Lorentz factor, which is very high. So your, I believe your, the jet kinetic luminosity has not reduced. So your mass loading might be different, and magnetic field will be different. Has of course been different if you take different assumptions and different calculations. So I am just wondering that whether these magnetic fields are important enough for a matter that is moving with Lorentz factors around 35.
So we are out of time actually, and I.
Okay, Amit, I'll talk to you later.
Yeah, sure. We'll take it offline. Thanks.
So the Slack channels are also available. So if there is any discussion, and then participant can join there and ask question and discuss over there. So that will be useful. So yeah. So thanks, Amit.
Thanks, Subhendu.
And you can disconnect yourself. Thanks, Amit.
You can stop.
You can, yeah. So our next speaker is Lankesh De, and from TIFA, he will talk about the presence of supermassive binary black hole in OJ287 using multi-wavelength observation. So Lankesh, yes.
Yeah. Am I audible?
Yes, you can. We can hear you.
Okay.
So you have 30 minutes just for, and you have 30 minutes, 25 minutes for presentation, and 5 minutes for question and answer. Okay.
Okay. Thank you.
I'll give you a reminder also.
Okay.
5 minutes.
Okay,
you can start now.
Okay. Good morning, everyone. My name is Lankesh De. I'm a PhD student at TI from Mumbai and working under the supervision of Professor Gopakumar. And I want to thank the organizing committee for giving me this opportunity for talking about my work. And today I'll be talking about confirming the presence of a supermassive black hole binary in OJ287 using multi-wavelength observations. So this is the plan of my talk. In the introduction, at first, I will discuss about the defined properties of OJ287, especially related to the binary black hole central engine model. And after that, I will talk about the history of observation campaigns of the predicted flares and their implications. And then I will discuss about our 2019 Spitzer observation of OJ287. And then I will talk about how the radio observation, high resolution radio observation can can inform us about this blazar. And at last, I will briefly talk about the possibility of detecting gravitational waves from such sources. So OJ287 is a very bright blazar at a redshift of around 0.3, and it is situated very near to the ecliptic. And the interesting thing about this blazar is that we have 130-year long optical light curve for this system. So in this figure, you can see the optical light curve of OJ287 from around 1880s to 2020. And this optical light curve shows some periodic variation. So you can see there is a long-term periodic variation of the with a period of around 60 years, which is tentatively shown by this red sinusoid curve. And on top of that, it shows some high brightness major flares. So you can see like there is a major flaring around 1970s, and again around 1983, again around 1995, and with a duration of around 1 year. And if we zoom in on one of these major flares, and if we zoom in on all of these major flares, I am only showing here one of them from 1882 to 1885. So we can see like the major flare, on the major flare, there are doubly peaked flares which are superposed on these major flares. And these doubly peaked flares, they are very small duration, or duration around 1 month. And this is the case for all the major flares. Like the major flares have a period around 12 years, and all the major flares are composed of these two doubly peaked flares, which are separated by around 1 to 2 years. So what can explain all these variations, these 60-year variations, these major flares, and this double epic nature of these flares? So the natural explanation of all this variation can come from a binary black hole central engine model, where this 12-year periodicity is related to the orbital period of this binary, and the 60-year periodicity is related to the advance of periastron timescale. So this binary black hole central engine model was first proposed in 1996 by Leto and Voltonen, and it has been improved over times. So according to this binary black hole model, there is a supermassive secondary black hole of around 150 million solar mass, which is orbiting around a primary black hole with a mass around 18 billion solar mass in an eccentric orbit with an orbital period of 12 years. And those double epic flares arises because of the impact of the secondary black hole with the accretion disk of the primary black hole. So in the figure, as you can see, the orbital plane of the secondary black hole is inclined with the accretion disk, and whenever this secondary black hole punches through the accretion of the primary black hole, then the flares happens. And those major flares that arise because of the tidal interaction of the secondary black hole with the accretion disk, which enhances the accretion rate whenever it is going through the pericenter. So this is a very nice movie which describes whole situation. So you can see there is this primary black hole and secondary black holes going around this primary black hole, and whenever the secondary black hole impacts with the accretion disk of the primary black hole, you can see a very bright flares. And these flares can give us like fixed phase point on this orbit of the secondary black hole. So here I am showing another movie for the same thing. Here you can see this is the primary central black hole, and the red circle is the secondary black hole, and this pink line is the accretion disk. So whenever this secondary black hole crosses this accretion disk, then you see this double epic flares. Like once is going through this, there is one flare, and what is coming back, there is another flare, and these are separated by regularly 1 to 2 years, and this gives fixed phase points on the orbit of the secondary black hole. So this is a very highly relativistic system. So if you want to calculate the orbit of the secondary black hole, the Newtonian dynamics is not enough, and we use post-Newtonian equation of motion to solve the binary orbit. So this is a typical post-Newtonian equation of motion shown in this one. So this x double dot is the acceleration and x zero double dot is the usual Newtonian term, and all the other terms are correction due to general relativistic effects. So this 1pn, 2pn, 3pn, these terms in first line, these are called conservative terms, and this causes the orbit to, or on the periastron of the orbit to advance with time. And the terms in the second line, which is shown in the red, the 2.5pn, 3.5pn, 4pn tail, and 4.5pn, those are called reactive terms or radiation reaction terms. So these terms arise because of the gravitational emission from the binary system, and due to these effects, the orbit sync with time, and its eccentricity also decreases with time. And the last line terms are coming because of the spin orbit interaction and quadrupolar interaction of the binary system. So in past, 2.5pn accurate equation of motion was used to successfully predict the impact flares of 2007 and 2015. The 2007 impact observation of 2007 impact flare was very very important because it showed the importance of the gravitational emission. Because if we didn't include the gravitational emission from this system, then the flare would have come 1 month later than when it actually came. So this actually showed that this system is coming closer because of the emission of gravitational waves. And in 2018, we used very accurate 4.5pn equation of motion to calculate the orbit of the secondary black hole and to calculate the most up-to-date parameters of this system. And also based on that solution, we predicted that the next flare was going to appear during July-August 2019, and we named it Eddington flare to commemorate the centenary, the century celebration of this famous Eddington observation of solar eclipse. And not only predicted the time when the flare would arrive, we also predicted the expected set of the light curve during the 2019 flare. We were able to do that because in this figure you can see the secondary orbit, and this is the impact points for both 2007 flare and 2019 flare. So both the 2007 and 2019 flares, for both these flares, the impact happened at a very similar point on the accretion disk, and also at very similar inclination, and also the velocity of the secondary black hole was also very similar. So based on all this similarity, we expect that the light curve of 2019 flare should also be very similar to 2007 flare. And we predicted this is how this 2019 flare should look like based on the 2007 flare. But unfortunately, during the predicted time, the OJ27, as it is close to the ecliptic, and at that particular time, it was very close to the sun, and it was impossible to observe OJ27 with any ground-based telescopes. The only telescope that were able to observe OJ27 during that time is Spitzer. So Spitzer was very far away from the Earth, and with Spitzer, we were able to observe OJ27 between July 31st and September 6th for around 21 epochs. And so if you see here, the predicted light curve here was in optical R band, but the Spitzer was in near infrared band. So all the observation of Spitzer were done with near infrared bands at 3.6 and 4.5 microns. So so as the observation was different wavelength than optical, there should be a base level change, because at lower as this blazar has higher flux at lower frequencies. So so in this figure, you can see, after taking into account the differences between the optical and near infrared band, you can see this blue line. Blue line was the predicted template for this light curve, and this red and green points are the observation from a Spitzer from two channels. The channel 1 is 3.6 micron and channel 2 is 4.5 micron. And you can see, like, after correcting for this different wavelengths factor, this follow very nicely. The observation follows very nicely the predicted template. And we also do many more mathematical studies to show that this flare, which we predicted, was actually observed or actually came within the predicted time. And we also showed that this is not a chance coincidence that this is matching with the predicted light curve, and this is very genuine. And the implication of 2019 flare is that this 2019 flare also would have appeared 1.5 days earlier if we neglected the higher order radiation reaction term. But it appeared within the predicted time. It shows that the higher order radiation reaction terms are also important to accurately calculate the orbit of the supermassive black hole binaries. And also the next impact flare is predicted during July 2020. And again at that time, July 2022, again at that time, OJ27 will again be close to the sun, but at that time Spitzer is not there. So we are exploring the possible observational approach. So there goes this optical and near infrared observation of OJ27, but can high resolution and radio observation can tell us anything about this binary nature of this system? So OJ27 has been observed in very high resolution VLB observation in 1543 and also 86 gigahertz. And in high resolution radio observation, what we measured is called the position angle of the projected jet. So in this figure, you can see this XY plane is the sky plane, and Z direction is the direction towards the observer, and this blue cone is the jet. So when we observe the radio jet, what we actually see is this projected jet on the sky plane, and the angle of this projected jet on the sky plane from a particular reference direction. Here we are showing this by Y. This angle is called, what is shown by eta. This angle is called the position angle. So this position angle has been measured for OJ27 at different frequencies for almost 25-30 years. And in case of OJ27, the very interesting fact is this position angle shows systematic variations in all three frequencies. So here I am showing the position angle for OJ27 in 43 gigahertz observation as shown in Inaugural 2014. As you can see, like position angle varies with time, and there was a sudden jump around 2005, and after that it again varies with time. So what is the cause of this sudden jump and why this is varying like this? So can we explain again? We know that this is a potentially supermassive black hole binary system. So can we explain this variation in position angle from this binary black hole model? So for that, I think yes. Okay, because the simplest explanation of this position angle variation can be the precessing jet, and as this is a binary system, the jet of the system can precess because of the precession of the spin angular momentum of the primary black hole or precession of the accretion disk. So we don't know what actually determines the jet direction in an AGN. So we have here considered the two models for the jet launching mechanism. One, the first one we call spin model, and in this spin model, the jet direction is determined by the primary black hole spin, which is from this Blandford-Naik model. And the second model we call it disk model. And according to the disk model, the jet follows the direction of the angular momentum of the inner accretion disk, which is from this Blandford and Payne model. So for the spin model, we again use this post-Newtonian equation of motion to solve for the binary orbit, and we follow how the spin of the primary black hole is precessing with time from according to this spin precession equation. The spin is precessing because of the spin orbit interaction and also from this quadrupolar interaction. And this is what we get. So we determine the direction of the spin by using two two angles, this polar angle and azimuthal angle, this theta and phi, which can determine the direction in a spherical polar coordinate. And we see that this theta direction almost remain constant, but the phi direction changes with time, which shows that it is actually precessing around a fixed axis. And the phi is not, this is not a smooth function. You can see sometimes it is flat and sometimes it is going down very fast. This is because the jet rotation is a very highly eccentric system. So this fast decay is happening when it is close to the pericenter, and all the jet relativistic effects are very prominent there. And this slow decay is happening when it is at the apocenter. So the jet relativistic effects is not that prominent. And in the disk model, we model the accretion disk as a cloud of point-like particles, and we simultaneously evolves all these disk particles along with both our binary black hole using a post-Newtonian equation of motion. And we also then track how the angular momentum of the inner part of the accretion disk is evolving with time. And again, we are determining this direction using two angles, theta and phi. And here we see that here theta is also changing a little bit with time, and the phi is also again decreasing with time. But here theta is, you can see there is a clear 12-year periodicity and 60-year periodicity. This is coming because of the interaction of the secondary black hole with the accretion disk particle, and this 12-year periodicity is related to the orbital period, and 60-year is related to the advance of peristron time scale. And here also you can see this clear 12-year periodicity in the phi variation. So now from the disk model and from the spin model, we know how the jet direction should evolve with time. But how do we calculate the position angle from this jet direction? The position angle actually depends on both the jet direction and also direction of the line of sight. So jet direction is calculated from this theta jet and phi jet, but the direction of the line of sight is parameterized with two angles again, which we call theta obs and phi obs. And we need some more parameters to fit for this polarization and this position angle, because any change in the central engine or any change in the direction of the jet waves will take some time to propagate along the jet and to be observed at different frequencies. So we introduce a time delay parameter called delta t, and it should be different for different frequencies because different frequency actually probe the jet at different distances from the center. With high frequency probing the inner part and lower frequency probing the outer part of the jet. So we expect the delta t to be small for high frequency observation and to be large for low frequency observation. And we need one more parameter, which is called delta PA, to take into account the fixed direction of the sky plane from which the position angle is measured, which is not known in our coordinate system. And delta PA can also depend on the frequency, because as the jet propagates, it can bend with bend at it propagates. So the position angle at a particular time depends on this theta jet and phi jet at a time which is at t minus delta t. It also depends on this theta obs and phi obs, that is the direction of the line of sight, and also this delta PA parameter. So to fit for this PA, we simultaneously fit for all PAs observed at all three frequencies, and we fit for this theta obs, phi obs, delta t's, and delta p's at independent parameters. So we need more total eight parameters because theta obs, phi obs are 2, and we need 3 delta t for 3 different frequencies and 3 delta pa for 3 different frequency observations. So here is the posterior distribution for the fitting of delta pa, fitting of Poisson angle variation for spin model, and we can see all of them follows more or less Gaussian distribution. And this is again for the disk model, and all the median value of standard deviation are shown in this table. As you can see that theta obs and phi obs, which determine the direction of the observer line of sight, is almost very similar for both our spin model and disk model. And as we expected, the delta t is small for 86 gigahertz observation in both the models, and delta t at 43 gigahertz is larger than this, and delta t for 15 gigahertz is more than both delta t 86 and delta t 43. So this actually, all these posterior actually do follow the astrophysical expectations. And with all this, with all the median value, we fitted for this Poisson angle variations, and these are shown for 86 gigahertz. We are showing the Poisson angle variation. The left panel is for spin model, and the light panel is for disk model. And here you can see these green points are the observed points, and these are calculated from GMVA 3 millimeter data. Now you can see that in both the models, it more or less follow, and as if we have more data, we'll be able to say which model fits the observed beta better. And this is the fit for 43 gigahertz again. This is for spin model, and this is for disk model, and this is for 15 gigahertz. The long-term behavior of these PA variations can be explained from both these models, and at present there is no clear and strong evidence to favor one model over the other. But future ongoing and future observation will be allow us to say which model is more favorable for this jet launching mechanism. And the more important thing is that this binary black hole model, which explains the optical observation, can also explain those broadly the variation in the Poisson angle in the radio jet of OJ287. And we can also use this for this EHT, because EHT also observed EHT OJ287 is one of the sources for EHT collaboration. And this is from this EHT GMVA plus ALMA GMVA plus EHT observation. And here also we can see that these red points here are still unpublished, and it is a work in preparation. So you can see that future observation up to 2020, they're also following our prediction quite nicely. And as I said, that OJ287 is a very important non-linear source for Event Horizon Telescope, which first published the image, the shadow of a black hole in 2019. So we used to observe OJ287 at very high frequencies at 230 gigahertz, and our model can also be used to test this EHT observation can also be used to test our model, because our model can also predict and explain the observation of EHT at this very high frequency. Additionally, as the secondary black hole impacts with the accretion of the primary black hole, it can accrete some matter, and it can host a temporary jet, which should be observed by EHT because of this very high resolution that can be achieved with EHT. And we can also use our model to say in which direction the secondary jet should appear. And this is a current ongoing investigation, and this should be very interesting so that we can confirm whether we can see a secondary jet in this EHT image or not. So apart from that, being an supermassive black hole binary.
Lankesh, you have 5 minutes more.
Okay, thank you. Yeah. So apart from this, from this optical, infrared, and radio observations, it is very clear that OJ287 is a very strong candidate for supermassive black hole binaries. And as a supermassive black hole binary, it emits nanohertz gravitational waves, which will be detected by pulsar timing array. So pulsar timing array aims to detect nanohertz gravitational waves by observing a bunch of millisecond pulsars. So here is a schematic of how it will measure the gravitational waves. So there are lots of pulsars, and whenever a gravitational wave passing through the space between a pulsar and Earth, will change the arrival time of pulses from those pulsars, and the pulsar timing array tries to detect those modulation in the arrival time of the pulses, so to detect those gravitational waves. And the important thing is this PTA signal due to audio to testament kind of binaries can also depend significantly on the eccentricity of the orbit and also the spin of the orbit. And we need to accurately model this PTA signal to detect it from the PTA data. So here I am showing the PTA signal or PTA residual due to gravitational wave from OJ 287 for two different spin values. One is for 0.38 car parameter, which is the actual measured value for the time being, and another is for very low when the spin is very small, let's say 0.01. And we see that this for different spin values, the PTA signal is quite different. So this implies that the spin of the black holes can also change the PTA signal, and this is very important also to consider the spin of the black hole whenever we are trying to detect gravitational wave signals from the PTA data. And this is my summary of my talk. So the 12-year quasi-periodic optical flares in OJ287 implied that the central engine of this OJ287 is supermassive black hole binary, and this binary black hole model has successfully predicted last 3 flares in OJ287. Latest of what was observed in 2019 with Spitzer Space Telescope. And the radio observation of the jet of OJ287 at different frequencies can also be explained from this binary black hole model, which is developed in the optical observation. And being a supermassive black hole binary, OJ287 is a very important source for the pulsar timing array, which aims to detect the nano gravitational waves. And this detection of gravitational wave from such kind of system will certainly help us to understand supermassive black hole binary dynamics in more details. So keeping all this in mind, it is very clear that OJ287 has the potential to inaugurate the field of multi-messenger nano-hertz gravitational astronomy, because it can observe because from OJ287 we can be observed both at gravitational wave with pulsar timing array, and it is already being observed in optical, near infrared, and radio observations in the optical spectrum. So thank you very much for your attention.
So let's thank Lankesh for this wonderful talk about the presence of supermassive binary black hole in OJ287. And now we'll have time for question and answer. So if there is any question from the participants. So Pankaj, you please go ahead.
Hi Lankesh, can you hear me?
Yes, I can hear you.
Yeah, very nice and elaborate talk, and thanks. So I have a couple of questions, but it's a very different. So you mentioned that the measurement is, the 2019 measurement I'm specifically talking about. That the prediction is for R band, and then you shifted it to IR band. Yes. You do. So what was the underlying thing? Whether you took a constant jet emission something, or how do you transfer that?
Okay, so
yeah, some profile.
Okay. So during the flare, flare has two components. One is the usual synchrotron component of this from a blazar, and also it has another component which is coming because of the impact of the secondary black hole with acting on a primary, which is Bremsstrahlung in nature. So this Bremsstrahlung nature flare, that is the excess flux coming because of the impact, this has a very flat spectrum, and we expect this to have very similar flux in both in infrared and also in optical. But the synchrotron part, which is the usual flux from this blazar, which has a power law kind of thing. So for the synchrotron background, the background should be higher, should be of higher flux at infrared than in optical. So we have to subtract. We calculated what is the expected base level difference for this synchrotron flux, background flux for optical and infrared, and we subtracted those base level flux.
So basically assuming some power law spectrum and some constant type, right? You did not vary it. So, okay. The other thing that you just showed a nice result about this PA variation, which your model explained nicely. So it seems that the GVMA data that you talked about are are maybe in preparation are going to be, already submitted. It seems to favor the disk model. Is it correct?
Yes.
The jet origin as a accretion
Yes.
disk interaction, right?
Yes, so it looks like it favors the disk model, but when we combine all those three frequencies and look for the evidence, in that case it's not very clear. It is showing that both the model are consistent. But in 86 gigahertz, if we see this short-term variation, it looks like it favors the disk model.
Further observations will be required, and this is actually GMWay ALMA proposal. It's taken from the.
There seems to be a connection problem.
Yeah, I don't know. I also didn't hear anything.
So
Unfortunately.
Lankesh?
Hello?
Yeah. We lost you for a few minutes. So can you?
Yeah, so what I was saying, can you hear me now?
Yeah. Yes.
Yeah, so yes, so the recent observation from this GMVA at 83 gigahertz, it looks like it is following the disk model better, but just for 3 points we cannot say, because it has to explain. If we consider all the three frequencies of 86, 43, and 50 gigahertz, it is not very clear. If we look at the evidence, Bayesian evidence, both of the model looks consistent with the observed data. So we require more data to confidently say one model is fitting the data better than the other.
And if I have we have time, I have one quick last question.
1 minute left. Yeah.
Okay, fine. So in the last slide, you in the IPTA work that you have been doing is undergoing submission or preparation. So you consider two spin values. That's 0.38, that is the model prediction, and the 0.01. Is there a specific reason not to consider a higher spin value?
Yeah, we also consider higher spin value. Yeah, we also consider 0.99.
Okay.
For also it looks very different. So I just wanted to but I'm not showing it here. But for different, what I wanted to show that for different spin values, the signal looks very different. So for 0.9 also it looks different from 0.3 and 0.1. So it is very important to consider the spin while searching for this kind of binaries in PTA data. That was the main motivation.
Thank you.
So let's thank Lankesh again, and you can disconnect.
Thank you.
Of screen sharing, yeah. And our next speaker is Gulabsi Davangan from Ayuka, and in this talk he will talk about AstroSat study of type 1 AGN. So welcome, Gulab. So you will have 30 minutes, 25 minutes for presentation and 5 minutes for question and answer. And I will give you a reminder 5 minutes before. So there's, yes, it seems fine. So we can't hear you so far. So it seems there is a microphone connect. It seems there is an internet connection problem from Guladamangan. So we'll wait for a few minutes. Yeah, he seems to have some internet connection issues.
Sure. Next is
Can you hear me?
Yes, now clear.
Okay. Thank you.
Welcome.
Yeah. So let me thank the organizers for giving me this opportunity to give the talk here. Sorry for the delay. So I'm going to talk on multi-wavelength study of active galactic nuclei with AstroSat. So you already have excellent introduction on AGNs by KP and other speakers. So I'm not going to go into detail in the introduction. So AGNs are essentially powered by accretion onto a supermassive black hole, and this accretion process essentially results in the accretion formation of accretion disk around a supermassive black hole of 10 to the power 6 to 10 to the power 10 solar mass or so. So depending on the mass and the accretion rate, the temperature of the inner accretion disk can vary from between few electron volts, few tens of electron volts. And this accretion disk essentially emits in the ultraviolet and extreme ultraviolet, depending on the temperature, of course. And it is optically thick thermal emission, so it's more like a multicolor black body emission. The accretion disk photons are then comprised by a hot corona, and hot corona is some of our observations suggest that this corona is compact, not more than about 20 spatial radius or so. And the temperature of the hot corona is about a few hundred electron volt, and this repeated inverse Compton scattering of the accretion disk photons in the by the hot electrons gives rise to broadband X-ray power law from 0.1 kV to about few hundred kV. And this X-ray power law, of course, we observe directly, as well as it illuminates this accretion disk. As a result of the illumination, there are two effects. Part of this illuminated X-rays are reflected, which we observed in the form of a broad iron K-alpha line, as well as a reflection hump. The other part of this illuminated X-ray power law is absorbed, and it is reprocessed and re-radiated in the optical ultraviolet bands. So essentially, the central engine of the AGNs, if I exclude the jets, I will be focusing more on the radio quiet AGNs. The central engines of radio quiet AGNs essentially emit in the UV and X-rays. And we can, oh, sorry, this is something. Something has turned on.
I will probably rotate or flip, I think.
Yeah, I think I'm looking at that.
It was showing in the property when you opened it, probably. I mean, it's when you right clicked on the figure.
Yes. Okay. Yes. Yeah. Okay, so here is the spectral energy distribution of AGNs. So the primary continuum of active galactic nuclei, that is from the existing disk and hot corona, is confined in the optical ultraviolet to broadband X-ray emission. So the optical UV emission is observed in the form of big blue bump, which is supposed to be the direct emission from the existing disk. And as I mentioned, it peaks in the ultraviolet and extreme ultraviolet. And the broadband X-ray power comes from the inverse Compton scattering. In addition to these two components, there is another important component known as the soft X-ray excess, which we observed as the excess emission below about 2 kb. And when we model as a thermal Blick body emission, the temperature is about 0.1 kb or so. So this band from optical UV to hard X-rays is well covered by AstroSat. AstroSat has 4 co-aligned instruments. One of them is this ultraviolet imaging telescopes. It has 3 channels, and 2 channels are useful for science observations, the far ultraviolet channel and near UV channel. Together, these channels cover the wavelength band from 1200 to 3000 angstrom. Each of these channels have 5 or several filters, and the FUV channels has 2 low resolution slitless gratings. The NUV channels also has 1 grating. In addition, we have the soft X-ray telescope, which is an imaging X-ray spectrometer, which is sensitive in the 0.2 to 8 kV, and the large area X-ray proportional counters, which are the non-imaging detectors, they're sensitive into 3 to 80 kV. And there is CZTI also, but CZTI is not very much useful for AGN studies because of its sensitivity. But the UVITs, SXT, and LEXPC are excellent to study the primary continuum emission from active galactic nuclei and the optical UV to hard X-rays band. Therefore, using the AstroSat, one can probe the accretion disk emission, the soft X-ray axis, the hot corona, and the interplay between them. And that is what I'm going to discuss in this talk. But when we try to study AGNs, there are a number of complexities. First of all, the AGNs are embedded in host galaxies, and they are complex objects in the messy environment. So one needs to carefully think about the intrinsic UV extinction if one wants to study the intrinsic accretion disk emission from AGN. Of course, there are contamination from the host galaxy as well as the line emitting regions like the broad line region, the narrow line regions, etc. This is one example of associated observation. This is the associated observation of IC4329A, and it shows the 3-color image formed by the FUV, NUV, and the Chandra X-ray emission. You clearly saw the nucleus, the bright nucleus at the center here. And of course, you see the dust lens which are passing directly through the center, which complicate the study of the intrinsic emission of from AGN. There is another example of associated observations. In this case, we see bright nucleus, of course, the AGN, but we also see contaminating emission. First of all, there is a diffuse UV emission, most likely the star forming from the star forming regions, the central regions, and there is an additional compact source which may look like a dual a pair of nuclei. But we have done detailed analysis of this compact nearby source, and what we found that the spectral energy distribution of this compact source is not consistent with an active accreting object, but it is consistent with a compact star forming region. So therefore, all double nuclei like AGNs do not host a pair of binaries, a pair of supermassive black hole pairs, like in this case. We have performed detailed study of IC4329A using AstroSat UV as well as X-ray instruments. So here, as you see in the color image here, so first we have separated the AGN emission from the host galaxy emission by studying the radial profile in the central regions, and by modeling the radial profile in terms of a point source and galaxy profile, we actually separate out the AGN emission. And once we have the AGN emission, we then correct for the galactic extinction as well as the internal extinction. And the internal extinction is very much uncertain, so we actually use a number of extinction correction depending on different extinction laws. We use the C-journey at extinction law with a color excess of 0.8, and this we infer for this we obtain from Balmer decrement, because Balmer decrement is a measure of extinction. We also use the color excess of 1.0 as inferred by Mehdipur and Constantini et al. By continuum fitting. In addition, we have also used the Gosker and Bonker extinction law, which is another extinction law is appropriate for active galactic nearby observed AGNs. We also use the starburst extinction law because the dust lane and the diffuse UV emission are likely coming from the star forming regions, and that is why we use the starburst extinction law. And that's how we infer the intrinsic emission from this AGN. And once we have the intrinsic emission, we then correct for the contribution of the broad line region and narrow line region, essentially the contribution of the line emission. For this purpose, we used the quasar composite spectrum, because we do not have the far ultraviolet and near ultraviolet spectrum for this AGN. And then finally, we infer the intrinsic continuum emission, which should be arising from the accretion disk. And then we compare this intrinsic emission with the accretion disk models. In the left side, you see the models, the curve, the accretion disk around a curved black hole shown in the solid lines, and the accretion disk around Schwarzschild black hole shown as dotted lines. These are for two different extinction correction for the same extinction law C-journey et al, but different color axis values. And you clearly see that these data points do not correspond to these the accretion disk models. Here we have also used the optical data from Hubble Space Telescope. But if we truncate the accretion disk at about 80 to 150 RG, then these data points are well described by the truncated accretion disk models. If you use the other extinction laws, we still see very clear evidence for the truncated accretion disk rather than a full accretion disk. So we think this AGN hosts a truncated accretion disk with an inner accretion disk radius of about 80 to 150 RG. We also observed this AGN 5 times with AstroSat over 5 months period, and we observed a strong X-ray variability. For example, this figure on the left shows the spectrum steepens with increasing X-ray flux, and this is not new. Such observations, such characteristics of AGN are radio quiet AGNs are very well known, and this such variability, spectral variability, are explained as cooling of the hot corona is the increase in the seed flux, and seed flux, of course, is thought to arise from the accretion disk. And in earlier observation, there was because of the lack of simultaneous UV and X-ray observation, one could not actually confirm such a scenario. But now with AstroSat, we have simultaneous UV and X-ray observations. Then we looked at the UV variability as well, and here are from 2 different techniques. One is simple aperture photometry, and another one is the radial profile analysis. And we clearly infer the UV variability by a factor of 2 in about 5 months. And to compare this UV AGN variability in the UV band, we also looked at the time series of background and a star, which are not really variable. So this variability and the near UV variability of this AGN is genuine. Once we have the AGN intrinsic emission, then we actually fitted the broadband spectral model consisting of accretion disk, thermal componentization, and reflection to the broadband UV to hard X-ray data, the UVIT data, the soft X-ray telescope data, and the LEX-PC data. And we find that thermal componentization describes the power, primary power very well. And we then see that the spectrum, X-ray spectrum, does steepen with increasing NUV flux. This is like saying that the NUV flux is actually cooling the hot corona. And when we fit the thermal componentization model with a fixed optical depth, which was inferred from a new star, what we see is that the temperature does seem to decrease with increasing NUV flux, essentially proving the cooling of the hot corona model. We have also acquired the spectra with the low resolution UBIT gratings for a number of AGNs, and here are some of the examples. Here I will talk about the grating spectroscopy of one of the AGN Feral 9, and you see the typical emission lines seen in the ultraviolet, carbon 4, Lyman alpha, nitrogen 5, etc.
Gulab, there seems to be the slides are blinking every time, so.
No, I don't see any problem with this.
Many audience participants says that they have this similar problem. The screen is blinking.
Okay, maybe due to this internet connection, possibly.
Possibly, yes. We can see it, but it disappears sometime and it's blink.
So looks like just due to internet connection.
Yes.
Oh, okay. Let me see a little bit. Give me one minute just.
Yeah, sure.
Yeah. Is it slightly better now? Hello?
Yes, now it's still the same problem, I think.
Okay, shall I stop sharing and reshare?
Probably that will make better. Probably.
Yeah, it should not be that slow.
It's continuously. Yeah. Audio is clear, but
okay, okay, let me see. Is it okay?
Yes, still now. So far, it's okay. Yes.
All right. Okay. Thanks. So when we try to study the UV spectrum, as I had mentioned earlier, there are a number of complexities, and in order to derive the intrinsic continuum from accretion disk, one needs to correct for this number of effects. So we have implemented some of these models which to correct for this various effects. So we have created this extinction model for the spectra for the UV spectra based on Sejourne et al. Extinction law. We have also created a model for the iron 2 complex. Iron 2 complex dominates in the optical UV spectrum of AGNs in several bands. There is also Balmer continuum, which can also be modeled, and which have created a model for this as well. And of course, for the emission lines, one uses typically the broad and narrow Gaussian lines. And using these tools, we have actually modeled the quasar composite spectrum, which is seen here, and it's well described with such models. So this and once we have this models and tools, then we need to worry about modeling the UV and X-ray data together. UV data is usually in wavelength, and while X-ray data is usually in energy. So one has to be careful about doing this. For this purpose, we have created the response matrices, just like what we use for X-ray instruments. For the UV-IT gratings, we have, as well as for the broadband filters, we have created response matrix. And here we show the two approaches for Feral 9, which exactly result in the same final best fit spectrum shown in these two figures. So once we have these tools, then we go ahead with the UV X-ray spectral modeling. This is the spectrum of Feral 9. You see the dispersed image of Feral 9. This is the 0 order, the -1, -2 order. And here is a comparison of the far UV, near UV spectrum from AstroSat UV-IT with the HSD front object spectrograph spectrum. And these compare very well with the continuum and lines, etc. Of course, the change is due to the variability here. And once we model the UV spectrum in terms of the power law continuum and number of Gaussian absorption lines as well as galactic extinction, and then if we and we do find very good fit, and when we extend this fit to the X-ray band, what we find as the X-ray data shows a deficit, and this is a clear evidence for the hump in the UV band, and which is thought to be the big blue bump due to the accretion disk. So this excess UV emission or deficit of X-ray emission is due to the presence of big blue bump in the UV band. And then we try to go for physical models. So in this AGNs, using the XMM Newton data, particularly using the soft X-ray excess emission, Lofink et al. Have inferred the black hole spin of about 0.97 by using a blurred reflection model. And therefore, we directly use this black hole spin and construct accretion disk, relativistic accretion disk model, and we essentially use the available model, relativistic accretion disk model, and then fit to the UV data. What we find that such a model do not satisfactorily describe the far UV and near UV continuum age seen here in this bottom figure. Then we try another model. In fact, something called the intrinsic disk componization model. In this model, the accretion disk behaves like a standard disk down to a certain radius or corona. Below this radius, the accretion disk is no longer standard, but it is warmer compared to the standard accretion disk. And this warmer, optically thick material in the inner regions essentially componizes from componizes the disk emission from the mid plane or from the the transition region, and gives rise to this soft excess component, which is shown here is the green line here. The red line here is the spectrum from the standard accretion disk, and in addition there is this hot corona which gives rise to this power law component shown here is the blue. And when we use such a model, the data, the far UV, the near UV, as well as the SXC data are fit very well, and we infer this R corona about 20 RG. That means the standard disk emission is present only up to this 20 RG, below which this soft excess emitting medium dominates. And by measuring the total luminosity, one can convert and can measure the efficiency, and from the efficiency one can infer the black hole spin, which turns out to be 0.5, which is significantly lower than what is inferred from soft X-ray excess by interpreting soft X-ray excess as the blurred reflection emission. In addition to the broadband UV X-ray spectroscopy, AstroSat, because it can observe in UV and X-ray, it can one can acquire time series in the UV and X-rays, and then look into the relationship between the UV and X-rays. And this is very important because, as I was mentioning earlier, the accretion disk emission are actually compromised by the hot corona. This means the disk photons have to travel from the accretion disk wherever they are arising, and then to the hot corona. So therefore, there must be delay. So if this process is dominating the UV X-ray emission, in that case, the UV emission must lead compared to X-ray emission. On the other hand, if this corona is illuminating the disk and then some fraction is reprocessed and re-radiated in the UV, in that case, the UV emission should lag behind. So some of these models can be tested with UV X-ray variability, and that is what we have done for some of the AGN. Here, before we do such a thing, we need to demonstrate the associated capability for such studies. So this is one observation which does demonstrate the UV X-ray variability capability for AGNs by AstroSat. This is a 4-day long associated observation of NGC 4593, one Cepheid, one galaxy. Here you see the bright nucleus, and these are the light curves in the acquired with SXT, the UV far ultraviolet channel and UV near ultraviolet channel. And you see the strong variability. And when you do cross correlation analysis, what we find is that the FUV band lags behind the FUV and NUV band lag behind the X-rays by about half a day, and this is very much consistent than what is already found out from Swift HST observations. So this is the lag spectrum compared to the lag is measured compared to this radiation at 1928 angstrom, and therefore if you look at here, so there is a time delay of about 0.5 days, which matches very well with what we measure with UV with AstroSat, and that gives us confidence to study the UV X-ray lag in AGN. This is another observation, NGC 7469. This is again a well-known Synchrotron galaxy. Here are the soft X-ray, far UV and near UV light curves, and these are the cross correlation function. Here you clearly see the peak of the soft X-ray, the cross correlation functions are shifted away from 0, and here the negative lag means the FUV or the NUV FUV band is leading, or the NUV band is leading. And when we do more detailed analysis to find the statistical significance using a technique called flux randomization and random sample selection, what we find is that the FUV is delayed by about 33 kilosecond, the NUV is delayed by about 55 kilosecond, and there is possible delay, but this delay is more or less consistent with the zero lag between FUV and NUV emission. So in this case, unlike in the case of NGC 4593, the UV emission is leading, therefore it cannot be the reprocess emission. And by this lead time, one can actually find out whether find out what process or which process actually giving rise to this. And in this particular case, we find that if you look at the time lag between the UV emission where it arises in the accretion disk, and then if it is being computed, then one can first calculate the light crossing time scale using standard accretion disk theory, and this is the relation. This gives the light crossing time for a given for a radiation at wavelength lambda effective here, and which of course is a function of the accretion rate related to the Eddington rate and the black hole mass. For NGC 7469, these are the central wavelengths of the broadband filters which we used, and the relative accretion rate is about 0.37, and the black hole mass is about 10 to the power 7. So this gives us the light crossing time of about 19 kilosecond for the FUV related to the X-rays, and this NUV band about 31 kilosecond. And when we also calculate the computation time scale, which is actually much shorter compared to the light crossing time scale, which is about 5 kilosecond in this AGN. So the sum of this light crossing time scale and the computation time scale is comparable to what we observe in the lead in the far UV and near UV given the large errors. So in this AGN, we think there is an evidence. We find that thermal computation does give rise to this UV lead, or the UV lead is consistent with the thermal computation model. Here is the summary of my talk. So UV and X-ray observations with AstroSat are providing important information on accretion disk and its connection with X-ray emission in AGN. High resolution UV images of IC 4329A enable us to separate the AGN and the host galaxy emission. And this is important. The UVIT produces excellent, the very high resolution images about with a resolution of 1 to 1.5 arcsecond. And that enabled us to decompose the AGN and the host galaxy, and gave us the evidence for the truncated disk in this AGN. The monitoring multi-wavelength observation of IC 4329A established that UV emission from disk indeed acts as the seed photons for thermal computation. The far and near UV continuum spectra and the X-ray continuum from FAIR 9 suggest moderate black hole spin. The UV lead in NGC 7469 appears to be consistent with lags expected from thermal computation model. And thank you very much. So here I would like to acknowledge the ISRO, of course, responsible for AstroSat, the payload managers of different AstroSat payloads and the payload teams, of course, the operation team, as well as the AstroSat science support cell. And here are my collaborators listed here. Yes.
Can you hear us?
Yes, I can hear.
Hello?
Yes, I can hear.
Hello?
Yes, I can hear. Yeah, I can hear.
Gulab, we can hear you too. And the question, I don't know why he can't hear back.
Ah.
Hello, can you hear us?
Yeah, I can hear. Others can hear you. It seems
Actually,
you are not able to hear.
Yeah, actually, there seems to be an internet connection problem from our end, from Aries.
Ah, okay.
So, yeah, so that was the problem. So we thank you for this such a wonderful talk, and we are happy to see such interesting results from AstroSat. So now we will have some, we will take one questions because we are running late time. So is
Yes, please go ahead.
Let's thank again the speaker. Oh, there's one question there. So who is Baidehi? Baidehi, can you hear us?
Yes, I can hear you. Hope you can hear me well.
Yes, yes, Baidehi, I can hear. Please go ahead.
Nice talk.
Yes. Good.
Okay, just
Thank you.
one small question I want to understand is that this truncated accretion, this feature is a stable feature observed from AGN, or it is just like a temporary event?
So first of all, if you, in order to find whether the disk is moving or at what time scale the disk is moving inward or outward, you need to find the viscous time scale. The viscous time scale for AGNs is very, very long. It will be like thousands of years. So it's on practical time scale, it will be like more or less stable a truncated disk. Vaidehi, could you hear me?
Yeah, I can hear you. Thanks.
Okay.
Thanks.
Hello?
Yes.
Yes. So thank you for this nice talk. And now you can stop the screen sharing.
Thank you.
Yeah. And our next speaker is Dharam Lal from NCR TIFR, and he will talk about kiloparsec scale radio jet in radio galaxies. So Dharam, you can, yes. You will have 12 minutes for presentation and 3 minutes for question answer. So can you hear us?
Yes, I can hear you. Yes, I can hear you. Thank you. And thanks to my presentation is visible and people are able to hear me.
Yes, I can hear you.
Yeah. Fine. So thanks to you and the organizers for accommodating my small piece of work.
Dharam?
Yes, please.
Can you come a little closer to the mic? A little feeble.
I am quite closer to the mic. Is it clear now?
It's clear, but a little feeble.
Oops. Okay. Okay. I'm speaking as close as possible, and I'll try to be loud also.
Yeah. Okay.
Thank you. So this piece of work is done in collaboration with following people who are listed there: Tiziana, Burning Fanaroff, and thanks to the earlier speaker, particularly KP Singh, who gave a very good. Sorry, I can't go to. Sorry about this glitch. Yeah, thanks to the earlier speaker, particularly KP Singh, who gave a very good overview of radio galaxies, AGNs in particular. And this is one little introduction about the objects which I'll be talking about. So what you see on the left, 3C296 is a Fanaroff-Riley class 1 source, and on the right is Cygnus A, which is Fanaroff-Riley class 2. The two classes differ largely in radioluminosity and morphology. If you take the Fanaroff-Riley class 1 source and put it in a cluster environment, because of the ramp pressure, you essentially, the two jets trail behind, and depending on angle the two jets make, then you may call them narrow angle tail radio source, which is an example over here, or you can also form a wide angle tail radio source. These are not the only kind of morphology. You also see exotic sources like X-shaped source, which is over here. These are thought to be either merger of two AGNs or reorientation of jet axis. So with this introduction, I will move to motivation. I'll give you a flavor of two results from the radio galaxies using upgraded GMRT. One is interaction of the traversing radio jet with its surrounding media. and what we see, particularly the transverse spectrals, and hence the velocity structure in these sources, and what the Kelvin-Helmholtz instability, what they play a role. Another is we are doing a small piece of work where we are revisiting this Fanaro-Riley classification for some of the sources, particularly asking a question: does the sharp classification of Fanaro-Riley class 1 and class 2 types still hold when we improve our imaging capabilities? Particularly when SK is coming up and upgraded GMRT is in place, Meerkat is happening. Or in other words, to ask a question is, do we need more morphological classifications? This is to set the stage, an interaction of radio jet and the ISM of the host galaxy. This is on the arc-second scale. So you're talking just a kiloparsec or so. What you see here in the top panel is a background image, which is a HST image, or superposed on it is radio contours. And what you see, as soon as the radio jet leaves the host galaxy, it essentially flares up. And this is same thing is shown in the bottom panel also in some other manner, which is essentially X-ray corona of the host galaxy embedded in a cluster environment. So this essentially is saying that the radio jet is undergoing a transition as they leave the dense corona. And is it the Kelvin-Helmholtz instability playing the role? A word about Kelvin-Helmholtz instability. This essentially predicts the onset of instability when a streamlined flow passes through different densities. You probably have seen a matchstick when it is burnt, it streams, and then there is a suddenly as smoke plume accelerates upwards, it triggers a Kelvin-Helmholtz instability. That's the simplest example. And in radio jets flows of streamlined flows, you routinely see such things. And I'll talk about this. And this is the example source which I'll be talking about. This is NGC 4869 observed using upgraded GMRT band 3 image in full glory. You have head-tail radio galaxy where this is the core and the two jets were emanating in east and west direction, but the eastern direction jet went further because of the ram pressure, and the two jets twist, overlap, and then move further. And then there is a sharp boundary where the jet bends by 70 degrees and it also flares up. This is the feature I'll be talking in the next slide. So if you do the spectral index analysis for the source, essentially we can do this because you have broad bandwidth 300 to 500 megahertz at one shot. Typically in these sources, you see steepening due to synchrotron aging. Things are happening at the supermassive black hole accretion, which Gulab mentioned a little while ago, and the jets which are carrying most of the relativistic plasma, which is emitting in synchrotron emission, it steepens as more and more distance is traversed. So as a function of distance from the core, you will see spectral steepening, which is true in this case. You are seeing spectral steepening as a function of distance from the core, but as a transverse location in any place, you essentially see there is a spine which is in the center, which is red in color, which is flatter compared to enveloping sheath, which is green in color, which is steeper. So you not only see steepening as a function of distance from the core, you also see a spine which is flat enveloped by a sheath which is steeper as a function of distance. And that is further shown in here for various distances over here, here, and here in the three colors. And you see there is a steepening and spine is shitting over here, sheaths are on the either side. This is one aspect. If you progress further, this is the X-ray background image. Superposed on it is the radio contours from the GMRT image, and red is at L band, and the yellow one is at the band 3, which I was showing you earlier. And you see a sharp edge in X-ray surface brightness. So what you're seeing is essentially a collimated jet and experiences a sharp surface brightness discontinuity, and it flares up. This location over here essentially is shown in surface brightness counts. You have a jump over here, and you also see jump in density and temperature. Temperature is on the right side over here. So what you are seeing is rise in density inside, lower temperature on the left side, and vice versa on that side. This is an example of cold front, a merger scenario, but a collimated jet is experiencing this surface brightness edge, and hence it is flaring up. This is lastly because of the Kelvin-Helmholtz instability. Next, I'll take to the other question which I was raising. Do we need more morphological classification? This is a pilot study for 4 objects which we have started from a large sample of 12 objects. So we are showing images of 2 Fenner-Rayleigh 1s and 2 Fenner-Rayleigh 2s from band 4 of UGMRT and L band of Meerkat. So the black contours are Meerkat contours, red contours are the UGMRT. And this project is very carefully chosen in the sense that we are comparing apples to apples with identical imaging sensitivity, angular resolution, etc., etc. And these are 4 example sources. This little source on the bottom right is we are dynamic range limited, which we need a little bit more work. This is the images in the full glory for 3 of the sources. You see, this is for this X-shaped source, which I am showing you here. For the first time, we are seeing inner pair of lobes and outer pair of lobes. So this is something like double radio galaxy, but with an X-shaped morphology. This is a new discovery. And of course, in this source, you have 2 parallel streams of jets. Which one is a forward jet, which one is a reverse jet, we do not know. We are still looking at it. And they form essentially 2 multiple lobes. So you see exciting features in these. And these are the spectral index images. You essentially see it classical picture, spectral steepening as you move from core all the way to the upper part. And if this matter is diffusing into the wings, it is steepening further. In this is a surprise. We see nearly identical spectra around -0.8 all across the source, except the radio core, which is inverted spectrum. And we do not know how to explain it, and you see multiple hotspots in this. So I'll take example from one. I talked about this thing. You have multiple inner pair of lobes and outer pair of lobes with an X shape, which is for the first time we are seeing, and a classical picture of spectral index. And you can perform equipartition measurements for this thing. You typically see age of hotspot or of the hotspots or of the diffuse wings, which are of the order of few tens of million years. So these are based on the equipartition parameters. I'll take another example, which is this source. So you see an inverted core, a steepening of the spectra on either side. So the color is spectral index map, and the contours are total intensity contours from the Meerkat image L band. So you see steepening, and then as a function of it, steepens further, and then it forms over some radio lobe over here. Whereas in this side, you see a sharp break around this thing. From here, red, it suddenly transfers into green. And this is largely, we believe that this source is sitting in a cluster or rich group kind of environment. And this little notch over here, the eastern protrusion, which we call, is very, very steep, -1.6, which is again, and what is it causing? Who is feeding it? It's not a background source, which we know. And so we have put this same source, same contours on a SDSS image, sorry about that. And we see there are large contributors to the background sources, which are also showing emission in radio. And fortunately, because we are able to do this little, Meerkat allowed us to do polarization structure in this. And if you look at now the 2 lobes, the eastern lobe and the western lobe, of course there are bends, etc. The eastern lobe is less polarized compared to the western lobe, which is highly polarized. And this is largely because this jet is facing towards us. This is receding from us. And the 2 lobes are experiencing different amount of magneto-ionic medium. So this is essentially getting depolarized because of the magnetic ionic medium, which is facing more compared to this. And this is largely the line director effect, which we are seeing over here. Now I come straight to my summary slide, so essentially I was saying that the 2 things, we are seeing complex shapes, radio jets, radio lobes, but what we believe from the pilot study is that we would add very little value if we include complicated morphological classification system. And presently, very likely, the Fenner-Rayleigh class 1 and class 2 suffice for most of the things. Yes, you can add some more weather phenomena like Fenner-Rayleigh class 1 source lying in a cluster environment, and hence you see wide angle tail or narrow angle tail. That will add some more information, but FR1 and FR2 suffice. And earlier I gave you an example that we are seeing steep spectrum sheath enveloped by a flat spectrum spine. Or conversely, you can say that there is a transverse velocity where fast moving spine surrounded by a slow sheath layer. And that's largely because the source is sitting in a hot gas environment and the sheath is engulfing material from the environment. And in the same source, we also see a flaring of a straight collimated jet as it crosses the surface brightnesses, which we believe that is due to Kelvin-Helmholtz instability. Thank you for your attention.
Thanks, Dharam, for such a wonderful talk, and we can have one or two questions from the audience. So if there is any questions, please raise your hand. I see one microphone is on. Sumit.
Yeah, hello.
Yes,
hello. Yes.
Yeah, Dharam, while making the spectral index map, do you consider the core shift at different wavelength?
We have very good image registration and we don't experience any shift in two images. And these are in-band spectral index, essentially the Meerkat in-band spectral index, where we are getting data from 850 megahertz all the way to 1750 megahertz. And we don't have to do anything there. This spectral index structure is a bonus to our observations.
Okay, as we know that if for higher frequency we go closer to the core. So if we use two bands, so there will be some core shift.
Right. So further to answer you, this is what we put in a lot of effort when we are picking up these four sources. We made sure that we are using different instruments, but different instruments are giving identical sensitivities, identical resolution, mapping a large field of view, so that we don't suffer from registration issues between two images. We don't see this thing.
Oh, okay. Okay.
Thank you.
Thanks. Yeah, thanks.
We can take another question if there is any. Okay, since there is no further question, let's thank again.
Thank you very much.
Yep. And now we have another speaker from Rupjyoti Gogoi from Tejpur University, and she will talk about clues regarding the origin of jets in host galaxy morphology. And on her behalf, Sonali Sajdev is giving the presentation. Okay, yes. So you will have 12 minutes for presentation and 3 minutes for question and answer. And
Can you hear me?
Yeah, yes, clear. You can start now.
Yeah, thank you. So I'm Sonali. I'm a postdoc at RRI. We are thankful to the organizers for giving us an opportunity to present our work at this workshop. Rupjyoti has apologized that she couldn't give this talk in person due to last-minute university work and election duties. I'll attempt to do justice to the talk on her behalf. We have tried to find out clues regarding the origin of jets in the morphology of host galaxies. Here Rajshri is Rupjyoti's master student who is dedicatedly involved in the analysis. Ravi is the one who suggested this work, and we have and look forward to Gulab's guidance to get maximum science out of this project. Okay, I'm not able to view. Okay, yeah. Okay, so I would like to begin by reminding you of the remarkable fact that observations have established over the past 2 decades. Not only do these supermassive black holes exist in the nuclei of possibly all galactic bulges, the properties of these black holes and the galaxies in which they live are linked on a galaxy by galaxy basis. The mass of the black hole exhibits a tight correlation with the velocity dispersion, mass, and luminosity of the bulge that hosts them. This has been exhaustively reviewed in Cormendi and Ho 2013. The accumulating observational evidence at local as well as higher redshifts has made it clear that the cosmic evolution of galaxies and their supermassive black holes have been driven by interlinked physical processes. It has been a hard fact to digest because there's a 6 to 7 orders of difference between the size of the black hole and the bulge. In addition to the observational evidence, a considerable theoretical motivation to invoke this linkage has developed as well. Interestingly, neither current semi-analytical models nor numerical simulations can successfully reproduce the properties of present-day galaxies without invoking some form of feedback from the AGNs. Feedback takes place through an interaction between the energy and radiation generated by accretion onto the supermassive black hole and the gas in the host galaxy. The radiative mode AGNs are associated with populations of lower mass black holes and bulges that are growing via accretion and star formation. These are considered to have not yet reached their evolutionary endpoint. The jet mode AGNs, on the other hand, are associated with higher mass black holes and spheroids. These are considered dead systems where the bulk of star formation and black hole growth has already occurred at higher redshifts. So overall, this picture implies that actively growing AGNs live inside star-forming disk structures, and fully grown jet-producing AGNs are a part of passive ellipticals. The accuracy of this scenario is rigorously probed, as this involves our understanding of the growth of galaxies and AGNs through mergers and accretion. And also, it provides the framework for understanding the quenching of star formation in galaxies over cosmic time. A major challenge to this scenario has come up in the past decade is the observation of gamma ray emitting jets from narrow-line Seyfert 1. Narrow-line Seyfert 1 are low mass AGNs with black hole masses less than 10 raised to the power 8 solar mass, which accounts for the narrowness of their permitted emission lines. They are more barred, have higher star formation activity, and support disk-like bulges. So while they were considered to be radio quiet, hundreds of them have lately been discovered to be radio loud and also found to harbor powerful relativistic jets. This has led to the fall of the old paradigm according to which only massive black holes could launch powerful jets. So a new paradigm based on jet presence and power has been gaining relevance. It is now an important debate as to whether radio loudness is related to galaxy merging or tidal interactions. To obtain insight, one needs to investigate how radio loudness correlates with host galaxy properties. In our project, we are analyzing the morphology of all narrow-line Seyfert 1 radio loud galaxies that have been observed by the high resolution and high sensitivity imaging survey from HSC Subaru. There are 45 sources for which we have multi-band images. We have performed all the preliminary analysis, including estimation of sky background variance, creation of mask images, estimation of most valid sigma and PSF images, etc. The black hole mass has been estimated following the virial method using the width of the broad emission lines obtained from Sloan's spectrum. In addition to that, we have taken the values of black holes estimated by fitting the accretion disk model to the galaxies. The two sets of black hole masses can differ, and there is an ongoing debate as to which estimates are more realistic. However, our major focus is to compare structural parameters, so we have taken them both for an exhaustive analysis. The structural fitting of these sources has been carried out in a very systematic manner, which includes a number of intrinsic checks on the accuracy of the measurements. Here is a glimpse of the mask images generated for each source in each band. This is the mask of this. This here, if you see this source, so it has been masked here. So they cover all sources and their diffuse light, but barring the central source of interest. So here, here, this is the main image, then the model image, and then the residual image. The intensity profiles were created separately by fitting elliptical isophores. Initial parameters for image fitting were also derived from here, this is the central AGN light, and this is covered by the PSF. Then the components are according to the model image. So we decide on the best fit based on the image and profile residuals. The main difference in fitting normal galaxies and AGN galaxies is the inclusion of the PSF component to account for the bright source at the center. Obtaining host morphology parameters for type 1 AGNs is as yet considered a challenging problem because of the lack of contrast between the AGN and the host galaxy. An important thing that has been lately understood is that the maximum amount of uncertainty in disentangling the AGN from the host galaxy stems from the accuracy with which the PSF is able to match and model the central source. Even slight amount of mismatch results in the over or underestimation of the flux of the host galaxy. But this can be mitigated by oversampling the PSF and the source image. So this implies that the PSF will then cover larger number of pixels, which helps to reduce the interpolation error, leading to a more accurate match of the central source and the PSF peak. The master student Rajshri has in the past month worked with various convolution kernel sizes to find out the most appropriate, to find out the most appropriate convolution kernel size and for accurate modeling. So she's at present convolving and fitting the images based on that. We actually see a lot of interesting features in the residuals, including double nuclei, tidal tails, merger signatures, and following this, we will include radio quiet, Following this, we will include radio quiet galaxies and check if things differ for them. So this will give us a very good handle on the kind of physical processes that would have been responsible for radio loudness. Then of course, their relative placement on various correlations should also provide insight. So we'll be publishing our exciting results soon. Stay tuned. I end here. Thank you.
Thanks, Sonali, for this such a wonderful talk, and we will have a few questions about this. So, is there any questions from audience? Vaidhi, you can unmute yourself and ask the question.
Thank you. Good. It's a nice work. Maybe I might have missed it, but so from this exercise, what is your overall conclusion?
So the overall is this: we find double nuclei also, which would so we are just trying to find out what fraction would be have these interesting features that tell us that these galaxies might have been the jets might have been triggered by a huge amount of accretion or by so things that are happening in the host galaxy. What clues can we get from there by comparing the various signatures that we get from a radio loud sample and a radio quiet sample, and of course, and also check for their placement on the black hole mass and those correlations like the bulge mass, the bulge luminosity, etc.
Okay, thank you.
Pankaj, yes, you can ask the question.
Oh, no, just this is a follow-up of what Vaidehi asked and Sonali replied. So you said that you are looking for the host galaxy morphology and things, but you are only studying the central part. So I'm not able to understand. How are you?
No. So central part will be taken care by the PSF, and then we'll be fitting various components to see what is there to begin with, like only a single component, then maybe disk is there, then maybe we need to add another component, but we have to be very careful about it because the moment you increase the components, the quality of the fit improves. So we have to really check if that component is required. Yes, so the major focus is to get the morphology parameters and then to compare them that, okay, this is the kind of bulges that are there. You can get the profile shapes, you can get the overall, maybe the disk is more dominant in non-radio loud, in radio quiet galaxies rather than the radio loud ones. So those kind of things will come out when we have all structural parameters for these galaxies.
Okay, just a short query. So is it a redshift limited, or you are taking just galaxies that
So this
are
is
detected?
where they this is Rakshit's
Okay.
sample. This is redshift less than 0.8. They found out some 11,000 galaxies that are narrow line Seyfert one. Then they checked with first survey and found that 550 are like there, and then they divided them in radio loud and radio quiet. So that is the sample.
Okay, thank you.
Yeah, thanks, Sonali, for the presentation.
Thank you.
And you can now close the screen sharing. Yeah, and so we'll have the last talk before the lunch break, and it will be by Jahir Shah from IUCA, and he will talk about AstroSat observation of HBL 1IS during its October 2017 flare. So Jahir, you will have 12 minutes for a presentation and 3 minutes for question and answer, and you can start now.
Yeah, am I audible?
Yes, yes, clear.
Yeah. Hello, good afternoon. Myself Zahir Ahmed Shah. I'm postgraduate fellow at the Inter-University Center for Astronomy and Astrophysics. I will talk about AstroSat observations of the 1IS 1959 plus 6550 during its October 2017 active state. The motivation of this work is that for the first time with the AstroSat observations, we observed a time lag between particle density and spectral index, and we have developed a model which can explain and reproduce such time lags. So I will start with a brief introductory slide. Blazars, these are radio loud areas with strong, powerful collimated jets pointing close to the line of sight of observer. This results in extreme properties from the blazer emission, like their non-thermal spectrum extends from radio to GeV energies. They show rapid variability in flux and spectra. They have typically double Humphrey spectral energy distribution, and they show superluminal motions in high resolution waves. Blazars are broadly classified as BLX and late spectrum radio quasars. This classification is based on the characteristics of their optical spectrum. They are also classified as low synchrotron peaked blazars, intermediate synchrotron peaked blazars, and high synchrotron peaked blazars. And this classification is based on the peak of their synchrotron component. So this our source 1IS 1959 plus 650 is an HBL source, which is located at a redshift of 0.048. And this source is very active. It has shown a number of flaring events across the electromagnetic spectrum, and including intense activity at very high energies. During flaring, this source shows a significant variability at X-rays. And in 2017, SAFE has observed a unprecedented historic flaring activity from this source, where it reached first time a count rate of 49 counts per second. So following this observation, AstroSat had carried a target of opportunity observation of this source for a total duration of 145 seconds during the period October 25 to 26, 2017. So the details of this observation is AstroSat observation are given in this table. So in order to check the temporal variability of the source, so we have generated 100-second wind light SXT and LXPC light flow. The top panel here is SXT light flow, and middle and bottom panel are LXPC 10 and LXPC 20 light flow. So we calculated the fractional variability for these light flows. For SXT, this turns out to be 0.085, whereas for LXPC 10 and 20, this turns out to be 0.171 and 0.158. So for the spectral analysis, we have generated the time averaged spectrum in the energy range 0.7 to 40 keV. This includes the SXT spectrum in the energy range 0.7 to 7 keV and LXPC spectrum in the energy range 4 to 40 keV. So in this source, 1IS 19, being an HBL source, we know that its X-ray emission is due to the synchrotron process. Therefore, we assume that the emission arises from a spherical blob, which is filled with the isotropic particle density and the tangled magnetic field, so that the synchrotron emissivity can be written by this integral. Once we have the synchrotron emissivity, we can obtain the synchrotron observed flux by this relation. So this equation, it is solved, this integral, it is solved numerically, and this is included as a local convolution model in the XSpec, where this model gives us a synchrotron spectrum for an input particle density. So in our work, we took three functional formulas of this particle density, like power law, log parabola, and broken power law, and fitted our time average spectrum. What we found here that for this time average spectrum, the broken power law provides comparatively better fit, and the reduced time scale is better compared to the log parabola and power law model. So in this case here, since we are using the convolution model, in the XSpec, the energy variable should be considered as xi here, which is basically the square root of energy. And next, what we did the time resolver spectral analysis for this source, where we divided the total observation time into time segments of 5 milliseconds. And in each time segment, we generated the X-ray spectrum in the energy range 0.7 to 40 keV, and then in each spectra was fitted with the best fitted broken power model, which is obtained in the time average spectrum, and the best fit parameters obtained in each time is shown given here. Since here in case of broken power, the reference energy was chosen such that the error on normalization is minimum. So since this break energy, this reference energy occurs before the break energy, so what we are interested in our work, we are mainly interested in the low energy index, that is the index which occurs before break energy. Here we have plotted the low energy index versus the flux, and it shows the usual hotter and brighter phenomena, which is the known feature of lasers. Now coming to the interesting part of our work. So in case of broken power, we know that the definition of normalization is that it is equal to the particle density at the reference energy. So what we have done, so we plotted this index, the low energy index versus the particle density, which is basically the normalization at the reference energy. And we again obtained an anti-correlation with a correlation coefficient of -0.68. So what is important here is that if we shift this index by a time of 60 seconds, a strong positive correlation is obtained between the low energy index and the particle density. This is with a correlation coefficient of 0.9. This is further clear based on this slide curve, where if we see that the starting shape of this variation in the particle density resembles with this shape corresponds to this shape of the time gap of 60 seconds. So in order to understand this behavior and model the time lapse, so we assumed that the spherical region, which we considered for the synchrotron emission, is consists of acceleration region and cooling region, such that the evolution of the particle distribution in the acceleration region and the cooling region are given by these two equations. So once we have these two equations, one can obtain the steady state solution for these conditions. Like Na is the particle density in the acceleration region, and Nc is the particle density in the cooling region. So here this gamma is defined as a ratio of acceleration time scale to the escape time scale plus 1. So if we assume that the observed variations, they are due to the variation in the acceleration time scale, then we can write this as variation in the index will be equal to the variation in the acceleration time scale divided by escape time scale. In that case, this particle density in the cooling region, we can write it as fractional variation in the particle density in the cooling region by this equation. Remember here, the particle density in the cooling region are responsible for our synchrotron emission. So if we see this here, this gamma, this will be always greater because gamma 0 is the minimum Lorentz factor, so gamma will be always greater than gamma 0. So in this case, we will have the magnitude of the variation of particle density should be much greater than the index. But observationally, if you see here, this particle density, its maximum variation is up to maybe less than 0.1. But the index variation is of the order of 0.5. So this contrary with this result is contrary with the observation. So we have noted that this problem persists even if we consider that the escape time scale variation results in the observer variation. So remember here for this, since we are considering here the steady space solution, and in this case the time scales of the observer variations are slow, means that they are much slow compared to the time scales of the system. So the possible solution here can be that with the time scale, the time scales of the observer variation are comparable to the time scales of the system. In such case, the steady state solution will no longer be valid. So one has to consider the time dependent solutions of these equations. So we obtain the time-dependent solution for these two equations by giving a sinusoidal perturbation to the acceleration time scale with this equation, and then using the linear approximation, we can obtain the solution like the fractional variation in the particle density in the cooling region by this equation, and then using this relation, we can obtain the relation between the change in index corresponding to the fractional variation in the particle density for the time-dependent solutions. So finally, replacing this by a real sinusoidal function given by this, we obtain an important relation between the variation in the index and the normalization. So this equation, it contains a phase lag which corresponds to a time lag of this, like tau acceleration log of gamma by gamma 0 by 2 between delta gamma and n. And if you see here, if this observed variations are much slow, like the time scales are much larger, then in that case omega will tend to 0. So then this solution will it will be like the steady state solution we obtained earlier. However, if the observed variations are comparable with the time scales of the system, then in that case this term phi lag by sine of phi lag will be orbitally large. So we can obtain the magnitude in such cases, the magnitude of the variation in the index will be much greater than the magnitude of variation in the particle density. And the same we have observed in our observation, like here, delta gamma is much larger than the fractional variation in the particle density. In addition to this, one will observe a sufficient time lag of given by this tau a log of gamma by gamma 0 by 2 between the variation in the index and the normalization. So we checked this framework with our observations. So we choose n omega and phi such that it will reproduce the shape of our fractional variation in the particle density, and then we substitute these n omega and phi in this equation. So it gave us the variation in index at a time lag of 60 kilometers, like here. So this here, the obtained lag is consistent with what I have shown in the correlation study. So here it comes like nearly 60 seconds again. So using this time lag, one can obtain the estimates of acceleration time scale directly, and from there we can approximate the size of the so this is the concluding remark that the 60 seconds of time that in our observation there of the order of length of observations, and our inference that our model is based only on one oscillating cycle. So therefore, in future we need significant longer duration of observations. They are required to statistically further confirm that time. Thank you.
Thanks, Jahid, for this wonderful talk, and we'll have a few questions. So from audience, is there any question? So Pankaj, go ahead.
Hi Jahid, so very nice talk and work.
Yeah.
So so you derive an acceleration time scale of 10 power 5 seconds, right?
Yeah.
And you say that 60 kilosecond observation. Is there something missing? I'm not able to get.
No, this acceleration time scale you will obtain once you you reproduce this particle normalization index. Then this equation will give you a measure of acceleration time scale.
Okay. Okay, so the second thing that I want to ask is, okay, let's say you have applied it for 1 year. I think it is an extreme HBL or just HBL?
This is HBL source. Okay.
So what is your expectation from this for other HBLs from this study? I mean, or is it just specific to this particular one?
No, we tried this for, we see if this model, our model will be applicable to other words, provided like we have a simpler model, that the spectrum will be fitted by simpler model. Like in our case, we this spectrum was better fitted by broken power model. So if your spectrum is fitted by like complex models, then in that case, applying this work will be difficult. And again, we have tried for Mercurian 4-to-1 observation also. There we didn't find any time lags between the particle density and the index spectrum. So it depends. If your observation shows a time lag, then possibly can use this for this.
Okay, so one quick question. So in the fit where you have showed the power line, broken power lag parabola fit, on the slide. So you're in the the power law fit, the NH value is quite large. But okay, the fit is bad. Okay, probably.
So the fit is bad. Yeah, it's
okay.
So we have rejected based on the fit.
Okay. Yeah, I didn't notice that one. Thanks.
So let's thank Zahid again, and yeah, you can now close the screen sharing.
Yeah, thank you.
So we'll come to at 2:30, and we'll have a new session, and we'll talk about more about blazars and AGN in general.
Yeah. So next session is Professor Gopakumar. So I hope Professor Gopakumar, are you there online? I believe
I am pretty much here.
Yeah, and one small change is there that in the second session, one fellow postdoc called Main Paul, he has some difficulty with his laptop. So I just wrote an email to you. So please take care, and accordingly we can either tell speakers to either they can speak longer, or those 15 minutes could be accommodated for discussions and so on. So
I think yeah, that should be fine. Yeah.
Yeah, and postal systems are also there later on. So yeah, right. So it could be accommodated in tea break postal session, or if someone like we can speak like Pankaj, Vaidehi, Professor Saikia, if they want to speak longer, the time could be given to them to accommodate those 15 minutes because we don't have additional speakers. So
I will be liberal with the questions.
All right. Okay.
That should be able to take care of 15 minutes.
Yeah. Thank you.
Okay.
See you post lunch.
See you. Then I will reconnect around 2:25 or something.
Yes. Yes.
Okay. Bye.
Thanks.
Sundar, yeah. So you're in talk. So how was it? It was okay. Huh? Okay. 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 Yeah, Sundar. Hello. Yeah. Okay.
Mute microphone. Can you hear me? Okay,
Yes.
okay, absolutely fine.
Yes, we can hear you. Yes. Yes.
Hello?
Yes.
Okay.
Shwendu is done, I think.
Yes, yes.
Yeah. So you have a talk right now, right?
Not right now. I have talk in the afternoon, 5 o'clock, I think.
Okay.
Now Pankaj will talk, and then there are other two. He will talk, and then yes, Dhruv Sakia and Saikia and Vinitaja. Yes.
Okay, I see that Pankaj is already checking his slides. Hi, can you hear me?
Yes, we can.
Yes,
sir, we can.
yes.
Okay, thanks.
Hi, Gopu. Shall we start or wait for a few more minutes?
Okay. I was waiting for people to assemble. We can start in a minute or two.
Okay, no problem.
And I will give you a reminder around 25 minutes, and and I will be fairly liberal with the question answer session because it seems Mainpal may not be able to make it. So
yeah, okay. Yeah, I will try to abide by my time.
And maybe you can also emphasize because I guess Mainpal was planning to talk about something he did with you, right? You can
yes, but
slightly
the thing is
emphasize
that because it was his part, so I just took one part to say that the details of this will be presented by somebody else. So I cannot
Sure.
include at the last moment. You know?
I understand. I realize. I also come to know. I also came to know about it essentially an hour ago. So
yeah. So
don't worry. You can just emphasize that. Okay. Pankaj, are we ready to go? What about the LOC there? Can we begin?
Yeah, please go ahead.
Okay. So welcome to the session 3. So today this afternoon, we will be having roughly 7 talks on various aspects of blazars and active galactic nuclei. So we will kick in the session with a review presentation from Pankaj Kushwaha, who is a former graduate student here and is at ARIES these days. He's going to talk about new spectral phases of blazar OJ287 to get a good feel about the jet and accretion physics. Pankaj, floor is yours.
Yeah, thank you, Gopu. And first, let me thank the organizers for providing me the opportunity to present my work. So, okay, so I'm going to talk about this specific blazar, and you may wonder that there are far too many blazars. Why this one? So we will see, and that's what I hope that by the end I will be able to convince that yes, this source is unique when we see in terms of blazar, and not only for studying jet physics, for which the blazars are primarily known, but accretion physics, and as already Lankeshwar has talked about, GR physics as well, so general relativity and strong physics. So, okay, so here is the outline of my talk, mostly blazars and observational property, but I will leave these because many of the speakers from morning till the last speaker, everybody has talked about this one, so I will directly go to the complexity and challenges, and then specifically talk about OJ287 and the recent observations, especially since 2015, and I will focus mostly on the multi-wavelength aspect and how it helps on the current problems that we have in, of course, for different features that has been identified in this source, as well as in general in understanding the jet and, as I said, accretion physics. So I will leave this. We have a very good talk, except again, just for repetition, that blazars are the nuclei where the relativistic jet is directed towards us. And there are 2 types of sources. I mean, purely observationally classified. If you take a different observable, you can classify differently. They are called BL-like objects, and the second one is flat spectrum radio quasars. So in the BL-like, you have very weak emission lines. If you see on the continuum, you probably will not be able to discern them unless you subtract them. But in the FSRQ, the lines are pretty strong, and you can discern them in the continuum immediately. So, and this has been talked about that so we do not know the physics. So observationally part, I mean, do not understood the physics very well of why so huge scale of variability or something. But observationally, they are characterized by they vary on all time scale from few minutes, as we have talked by Amit, and decades, as Lankeshwar was telling about this 12-year periodicity of this blazar, and they emit in all the bands. So we have, you see that there are very different features at different flaring activity. So here you see 10-minute variability, but here you see simultaneous variability at more than 700 GeV gamma ray. The source flux variation looks like this. X-ray seems to be a bit delayed with respect to that, but similar more or less trend. But optical is completely different, so it is far more complex. What is interesting is actually that even the flux vary order of magnitude and everything. The spectral energy distribution, which actually tells how much emission does the source emit in different energy bands, actually so always maintain a double hump spectral energy distribution, which is shown by this 2-shaded region. And for example, in Mercurian 421, So there may be spectral changes, but the shift location of this peak, these and these peaks, rarely have been observed to shift. So only in the few rare cases you find that flux has varies and this peak has shifted here or something additional has come, but in general it doesn't change. So, and the one of the most important characteristics of, where we say that the jet is pointed toward us is basically this superluminal motion. So if you see a superluminal motion, it is expected that the source is moving at close angles to our line of sight with relativistic velocity. So coming to the challenges. So as I said, you have time variation on all time scale from minutes to decades, which is 6 to 7 order of magnitude. If you want to understand these sources, you need to cover these scales. On top of that, they not only emit in one particular band or strong, but they emission across the whole available electromagnetic spectrum. So which is 70 to 20 order of magnitude in span. So, and then if you see polarization, they also show very significant variation in polarization as well as polarization angle. And if you image, the jet extend from the very core of the supermassive black hole all the way to the galactic scale, which goes to megaparsec. So the scales that we need to cover to understand these sources are, if you actually want to understand very well, are too huge. But then another complexity comes in when you combine this with stochastic variability. What basically is that you don't know on which time scale, what kind of a spectra you will see, what polarization is expected, nothing we don't know. So basically this all whole will multiply, and then you will find that you have some number which is unfathomable, which is beyond our reach. So that is a problem that we are talking about. And then if you go and try to understand jet physics, what we observe is basically this top one. And below this one are the processes that goes from jet formation to how jet propagates, how the energy from magnetic field is transferred to particle, and then what kind of emission mechanism, what is a local condition, and what kind of photon field is present. So basically what we observe is basically photons, which is because of this. And this is a convolution of a lot of these things which has already gone about. So it's quite complex, but again, one can, depending on the different aspects, focus on the sources and their nature and try to explore various aspects separately, and then try to, and once you understand it separately, then try to probe the link, missing link, how they are connected and something like that. So mainly I'm going to focus on this one, but then of course this is inherently tied to this one, particle acceleration. And this particle acceleration has an uncertainty because we don't know what actually the plasma is mainly constitute of. So whether it is basically electron positrons or there are protons, and what is a typical number. So these three things actually are the primary concern when you go about just studying the emission and trying to understand these sources based on the variability and emission. So coming to the OJ287, so this is in the traditional classification, which is based on optical observation and whether you see lines or not. This source is classified as DL like RT, which basically means the emission line, if we see, either you don't see it or they are very, very weak. Okay, and interesting. So, the interesting aspect of this source is that it is very bright at radio and optical energy. And the source is located close to the ecliptic. So unintentionally, it has been observed for more than 100 years in optical, the photographic plate that has been used earlier to image the sky. So we have in optical band, we have almost 100-year data, more than 100 years of data. And people exploring this data have found that, okay, that there is a 12-year quasi-periodic optical outburst. And that actually has given a model, which actually Lankesar talked in the morning, that this could be a signature of binary black hole. And we will see there is another class of model. There is another interpretation of this periodicity, which actually comes from radio studies. So this one is basically based primarily on optical, while the other model actually is based on radio. And as we will see, and they rather actually interpret or rather claim that no, this is because of a precessing jet. So before I go ahead and delve into the observed things, so here is a look of this source in different energy bands and the complexity. I mean, the thing that I want to highlight is complexity. So if you look into the X-ray, you can see the jet. This is the core of the source, but then you find there are many bright spots within the jet. What it says is that these bright spots are actually significant emitters. So if you go to the radio, you find that, okay, these bright knots that you see in the jet in the X-ray are actually also seen in radio. This marked by these positions, and they are coincidence. I mean, co-spatial, more or less at the same location. So what it says is that at least apart from this core, jet has these 4 hot spots which actually emit in X-ray and radio. When you go into the go at optical energy, you find that you only see the core, this part, and you don't see any signature of the jet here. This is the cartoon, the jet, this X-ray jet. And similarly, at the IR, you don't see any bright spot in the jet, only the core. So what it says is that basically optical and IR emission are mainly from this core, unresolved, which is unresolved. At gamma ray, we don't have enough resolution, so you only see a point source. So basically, all these things are within just a source. So then, what actually, when we see variability, that's the question comes here: whether these 4 knots that we see in radio and optical, radio and X-ray, whether they contribute or don't, are basically gamma rays from this unresolved core. So let's come to the 12-year periodicity things. So AGN in general show stochastic variability, which basically is you don't see any signal, so they just randomly vary. And if you try to see what is the power spectrum looks like, this flux variation, you find that they follow a radar flicker noise power spectrum. So, and so far we have 3,000 blazars from Fermi-LAT, and only 11 has been found to show, indicates that there is a signal of, there is a QPO signal. But again, this is only in gamma ray. And so if you look into this 11 and compare with 3,000, you find that yes, any QPO signal are, in general, QPO signal are very rare in blazars or AGNs as well. So this is shown here. So this is a gamma ray light curve of the one of the source, which KP talked in the morning, and one of the famous source, which is target of X-ray study for anything. You see that at the gamma ray, you don't see any signal. This is just a power law, power spectrum. But then there has been detections of QPO in this source as well. And here is one X-ray observation where people have found a QPO signal, which is very significant. So as I said, only a handful of QPO are known, and most of them are transient. So basically you see one time and then probably you don't see them and don't know until when. So if you look into this number of sources, and then there are few QPO signals, you find that 12-year QPO is actually rather persistent. And so it is peculiar because in general you don't expect it. So that is what this is about this. This is the importance of this signal when you consider in terms of blazars or AGNs. But there is a controversy as well. So if you purely approach the data from data point of view, you have to take a data from optical, X-ray, and different energy bands, whatever is available. And if you do a timing analysis using modern methods, which are actually more favorable, rather favorable for AGN studies, timing studies, rather than the traditional Fourier-based method, you don't see any signal at all in different energy bands. So here you see, I am presenting this flux variation power spectrum from Goya Little, and you don't see any signal, which is this 12-year is expected at this location. So it is not detected in the recent analysis. And as I said, recently people actually analyzed more than 2,000 of blazars, and they don't find this QPO signal again in the OJ287.
So from the purely data point of and time series analysis of view, this is actually a controversy. So then the second question is, detection of QPO is actually hard in blazars. So the second question comes is, how reliable are these methods that also say that there is no QPO signal? So you can do a test. Actually, you simulate a data. You know what kind, I mean, what is a typical AGN variability, superpose a signal in it and try to test this. And what people found is that none of the methods that we know currently are 100% fail safe. So basically, so here is one example. So there are 4 signals that has been dumped into it, this simulated light curve. And then you use one of the method, which is power spectral density, which is one of the most favored method in AGN timing study. And you find that, okay, the lower QPOs you can recover, but at the higher period QPO is hard to recover. So this is when you have a very good sample, I mean, continuously sampled data and long-term data. So then what to do? I mean, so far, so what as we will see, or as Lankeshwar has said, that actually the model, I mean, their model predicts some flares at some time, and actually we observe them. So that has been observed. So what actually, at least it says that there is some flare around those time. So we assume that there is signal, and this debate, and leave this debate about whether 12-year QPO is present or not, is for the time being not that important. So coming to the model, Lankeshwar has already explained, so I will not go. It just say that, okay, there is supermassive black hole, I mean, primary, and the secondary goes around it in orbit perpendicular to the accretion disk of the primary. And every time it hits the accretion disk, it leads to an emission, thermal emission. And what they say is that the flare, that 12-year flare that we observe, is actually a thermal Bremsstrahlung emission from some 10⁵ Kelvin gas. And their prediction, recent prediction by this model was end of 2015 and again 2019, which Lankeshwar talked about, and both were observed observationally. So the one of the interesting thing about this model is that it is predictive. So it also predicts about the timing. It also says very specifically about that the emission is thermal Bremsstrahlung. So this is very handy for us. So when you go and try to verify a model, actually you look for all kind of observables that can actually check the model. So Lankeshwar has already talked about the polarization angle, as well as explanation of polarization angle in this model, as well as the timing properties and the observed flare. So what I am going to actually add is additional input, which is whether if the flare is thermal Bremsstrahlung. We know jet emission is non-thermal, so they both have a very spectrally different signature. So actually you can test the model. The other model that I was talking about is from radio study. So let me clarify that the earlier one, there was a 12-year periodicity in the flux variation, but this one is about position of the bright knots that I just showed that in the X-ray and radio, you see those bright hot spot, but then there are superluminal features as well. So what you do is actually you observe the superluminal features and then note down the position with respect to the core of the source. So this is a study from 2000 at 15 gigahertz using VLBA data from 1995 to 2017. And they found an interesting pattern in the location of these superluminal features are the stationary features, bright spots. There is a systematic shift of the location of these spots are moving features until mid 2006, and after that it start to shift in opposite direction and reaches somewhere at the more or less the same base level in 2017. From there, using this, they derived that there is a 22-year periodicity on the location of this position of the bright knots. So based on that, the bright knots are within the jet. So what it basically says is that the jet is to a very broad level precesing. So this is one model where they say that, okay, precision model where the emission region is traveling within a helical jet, and this jet precesing around this, our line of sight is this. So depending on the orientation of the jet with respect to our line of sight, the Doppler effect varies, and that Doppler effect actually leads to a variation in the flux because the Doppler boosting varies as angle. So this is the prediction, I mean, the model, this is observed light curve at optical, and this is the model prediction. You can see that, okay, more or less they can reproduce, but there is a catch. You find that the emission profile are quite broad compared to the flare that you see. So there are many flare within this single model predicted curve. So, but as of now, these models are still favored. As you can see, this model is recently from 2020. So the debate is still on between which one actually truly represents the central engine of the source. So as I said, okay, the two models have very different prediction, at least in terms of emission or emission spectrum. That is actually what we observe. One say thermal Bremsstrahlung, the other say synchrotron. Synchrotron is broadband, while Bremsstrahlung, when you see in context of synchrotron, is very narrowband emission. So actually, if you look at the spectra, it actually is a better test compared to others. So the other thing is polarization, of course. Thermal emission is expected to have zero polarization, but thermal Bremsstrahlung. But the problem is what we observe is combination of both thermal Bremsstrahlung as well as jet. So you expect in general very low polarization if this binary model is the true representation. But the problem is that even in the jet emission, now we have enough observation that says that, okay, even during the flare, the polarization can be very low. So it's really need a huge amount of data to actually check this. So that's what I was saying, that if you look at polarization as observable to test it, add additional info, test the model, you need a lot more data. So 12-year periodicity, you need a huge amount of data, too long duration to actually test this for the model which is true. Timing, yes, we have different timing profile, but then the problem is that jet emission is highly variable. So underestimating or estimating the base level is hard to establish whether it varies. The jet emission has varied and not the Bremsstrahlung component and these things. So actually it's complicated the matter. The third one, as I said, is actually spectral, and this is one of the best observable currently we have, other than what people have already talked about. So you see here there is a power law. In general, AGNs blazars have a power law spectrum, and if you have a thermal emission, you expect a bumpy feature compared like this. Here you may find that, oh no, this looks like a broad, but if you look into the overall broadband of the blazar emission, you find that this is quite a very narrow component compared to this all the way from radio to gamma ray emission. So I'll actually focus on this. All we need to do in this respect is that we need a multi-wavelength data to verify it. So before going ahead and testing it, so this is the general spectrum of the source, which has been observed so far, and found that this characterizes this source. So you have a power law spectrum at R energy. So you have in near infrared and optical, you see a power law spectrum. At X-ray, you have a power law spectrum, and as well as a gamma ray, you have a power law spectrum. And these are during different flaring states. So this is flare, this is in between flare and quiescent, and this is quiescent. You see that the flux increases, but not much change in the spectral thing. Even if its spectrum changes, it's remain a power law. Here I saw an IR optical, where you again see a power law spectrum. And this is one, again, additional observation where you see that, okay, at infrared optical, you have a power law in different energy bands. So this is what the characteristic jet emission of this source is. And when we go to present the new things, this is what we are going to compare with. So coming to the 2015 activity, what we observe is a spectral change in all energy bands, near infrared optical, X-ray, as well as gamma ray. So this is a flaring, this is the outburst flare, the 12-year quasi-periodic flare data, and you see that there is a strong change in the near infrared and optical spectrum. So you expected them to be a power law here, but there is a break somewhere. Near infrared is much lower compared to the optical UV. Similarly, there is a change in the gamma ray spectrum. In general, the gamma ray spectrum, as I showed in the bottom right, is this declining power law, but here it seems to go up and then declining. you may say that, okay, there is a huge error bar, but it's just because of the statistics. But mark my word that this is actual trend. So if you integrate more data, I mean, average over more time, you'll find that the data goes like this and then decreases this. So there is a change in gamma ray spectrum. So during the flare, there is, okay, the X-ray look like X-ray look like power light spectrum as usual. But before this, the observation shows significant departure from power law. So this is the X-ray spectrum, and you see the power law is expected to be like this one if you compare this one or this one, but it's actually show a rise. Basically, this is in AGNs, it is something called soft X-ray. So basically fit a non-thermal power light spectrum to this is to the X-ray data and then extrapolate it to lower energy. What you find is that this data appears to deviate from a power law. So this is what we called excess. And this was supposed to be talked by Dr. Mainpal, but since his talk has been, at least he cannot give the talk due to his problem with his laptops. So, but my point is that, okay, there is change in all energy bands. Okay, so then you try to model this. What could actually explain this sudden break that you see in near infrared and optical? And actually, if you find that if you put a thermal accretion disk spectrum from 2 into 10 power 10, I mean 10 billion solar mass black hole, it nicely fits. I mean, it nicely sits at the observed location and explain this break. Sorry. The another thing that we did actually is then we have a lot enough data, so we actually tried to see when this change from power law to this power law behavior to this break appeared, and we found that it actually appeared in May somewhere in 2013. So this actually nicely fits with the disk impact model that Lankeshwar talked about. That okay, so that the black hole mass is somewhere around 10 billion, and that and they predicted that this impact should happen somewhere in 2013 June, and we observe in July. So it basically, if you take with respect to that, it actually favors the disk impact model compared to the jet model. The second is
Pankaj, 5 more minutes, please.
Yes. Okay. Yeah, I'm more or less through. So then again, in the 2016-17, a new activity arrived. You see that activity is actually a strong change in X-ray spectral state here. And that is after the end of this 2015 activity. Again, once the source ended its 2016 activity, the X-ray spectrum returned to its usual base level. I mean, typical emission spectrum that characterizes this source. But again, in 2020, the source again underwent a flare, and then the previous the soft X-ray spectrum again resurfaced. And what we found is that actually this soft X-ray spectrum is actually what we call in Blazar's term HBL-like, where the peak of the synchrotron optical actually peaks in UV X-ray. So this is UV X-ray band if you extend. So this is because of the new non-thermal broadband HBL-like emission component. So not only this, the NIR optical break, this red point, also resurfaced, but this time the timing is completely odd with what we expect from the model, this binary model that was presented by Lankeshwar. And of course, there is a change in X-ray, gamma ray spectrum as well as X-ray spectrum compared to the base level. So if you look into the observables that I talked about, what we found is that, or what it says actually is that NIR optical spectral break actually favors binary black hole scenario. Simple precision cannot, because you don't expect any spectral change. So you only expect increase or decrease in flux without any spectral change. The softer gamma excess actually also is additional proof in favor that favors this binary disk impact model, because it requires a 10 billion solar mass black hole. The other forces, there is another interesting aspect is that this NIR optical spectral break that I talked about, actually it also indicates a significant evolution, which is basically, so if it is accretion disk, it actually allows for accretion physics, allow us to probe accretion physics. Now, so I will talk about few of the jet physics. So this is the source broadband emission in 2015 and 2015. And this is about, we still have a debate whether the gamma ray emission is because of the synchrotron self-Compton or external Compton in the electron-positron scenario. So what we found in 2009 study during a flare, that it is actually due because of the inverse company scattering of IR torus photon, which KP talk presented in the morning. But in 2015, there was a change in the gamma ray spectral shape, and we found that it is basically because of the BLR. So we know from other studies that IR torus is at parsec scale. What it implies is that the emission region is actually at parsec scale. And in 2015, it says that the actually emission region is somewhere in sub-parsec scale. So this we have known, but we have not so far this has been advocated from many studies, but this actually gives a very nice proof of that one. So I will not talk about this one, where we actually showed that even the disk impact scenario, the binary black hole model one can explain because of the hadronic emission model. So the second thing is that this shows significant X-ray variability, as I showed earlier. So the question is, what actually drives these X-ray changes? And that is where the AstroSat FUV data that was recently observed in 2017 and 18 actually make it clear. Earlier, because of lack of this data, we could not say, because the spectrum can go like this, or it can go like, rather than going extended power like this, it can show a cutoff like feature. And so it was not clear whether what drives the X-ray spectral changes. But now with this one, with these two observations, you see that, okay, it's primarily because of the evolution of the high energy end of the synchrotron spectrum. So this is optical spectrum. And if you extend it to the X-ray energies, you see that it can actually nicely explain the observed X-ray spectral changes. But if you cut it off, you see that it goes to the usual location. So basically, this now resolves that the X-ray spectral changes are basically because of synchrotron spectrum. So to summarize, so the longer dynamic activity or spectral changes that I showed or I presented actually allow us to study jet physics. It has actually resolved many of the things. Actually, like at least for this source, it has resolved the gamma ray emission mechanism, as well as has given a hint to the location of emission, where is the emission region located. And also this data has actually, this dynamic study has actually showed that the most of the X-ray spectral changes in its normal state is because of the evolution of the high energy end of the synchrotron spectrum. It has also ruled out many of the earlier model where basically BL-like were believed to be, the gamma ray emission in BL was believed to be due to synchrotron self-compton. And in the two models, that central engine model, it actually currently rules out the simple precision model. Regarding the accretion physics, as I showed, that the observation and disappearance of this, the thermal component actually allow us to study accretion physics from transient disk formation to how the matter flow under the strong magnetic field. So with this, I stop.
Thank you, Pankaj. You almost overshot by a couple of minutes, but since I'm planning to take main Paul's slot into the discussion, I can accommodate a couple of questions. Do we have some questions from the audience? Especially students are most welcome to ask. Well, if not, I may have to. Okay, so there is a question from Vaidehi. Please go ahead.
Hi, Pankaj. I hope you can hear me well.
Yeah.
Okay, good. It's a nice work. Just one small point I want to know is that during these different flaring activities which you showed,
yes,
where you are proposing that there's a direct strong accretion disk emission. Were there any nearby optical spectroscopic observations of this source?
No, actually, I tried to look into SDSS. At least I didn't find.
No, not in SDSS. I think if you check the Steward Observatory database.
Okay, I have checked it earlier, yes, not recently.
Yeah, but, so because they regularly observe these sources, so I think that they may have some optical spectra taken during these flaring state. The simple idea is that if you're proposing that optical emission is dominated by accretion disk, we expect to see some broad emission lines.
Yes. So there. So okay. Let me tell. So you expect to see broad emission line for this redshift. Actually, Steward band is not useful. I mean, you cannot actually out of these hydrogen lines, but others you can. And actually Stewart had actually stopped updating the data after somewhere in 2018.
Yeah, but
okay.
I think your accretion disk emission was seen in 2015 flare.
Yeah, so I have looked into that, but so far, to be honest, I have not found, because the data looks
okay.
Pretty
okay,
nice.
It's okay. If they haven't updated it, that's okay. No problem.
Yeah.
There's a question from Amit. Please go ahead, Amit.
Thanks, Gopu. Pankaj, very interesting talk. I just wondering the result you have shown from the Goels et al.
Yes.
So using karma technique, there is no quasi-periodic oscillation observed around 12 years period,
yeah,
right?
So yes, no.
So as I understand, or at least in current scenario, karma is quite a strong technique to detect these periodicities. So what is your opinion, whether we are actually seeing a periodicity, or there is no periodicity, it's just red noise dominated source?
Yeah, okay. So if you take that the analysis is already presented and the result is out, so you see that there is nothing, I mean, at least there is no signal there, right? So, but the problem is recently there is work by Martin, I don't remember the name, but I know the guy, I need to check it. So they also studied the karma method and applied it to simulated data to test how good they recover the QPOs, okay? And the two problems that they faced was actually whether how you decide which karma model. There is a P and Q parameters there, which decides the spectrum very well. Okay, normally people take the lowest one. Okay, I mean, if you have a model where P and Q, there are many parameter set of P and Q, which actually describes the model, they take the lowest one and do one. So their study, and I looked into that, their paper, it is out in Abject 2020, that it's not clear as of now. So the method is questionable in terms of recovering the QPO, especially at longer time scale, because in the AGN, the spectra is rising. You see, I mean, at lower frequencies, the spectra is rising. What I was saying is, sorry, let me see if I can. So this was, so if you go at low frequency, okay, so the spectrum is rising. So this is questionable at if your signal is at the end of this spectrum. That is a thing.
Okay.
Okay, so I will have a comment, and I just want to, again, we have to go to the next one, so I'm going to make it a very fast. So most of the models we try to explain the radio observation, they clearly state that we are not trying to explain this, of course, the big 11-year cycles are explained, but that's not what our binary black hole scenario is about. It's about those impact flares, which are sort of superposed, and they are bi-orbital. So that's where the models were trying to well, eventually, if you want to see is a black hole, binary black hole or not, we will require IPTA and Indian pulsar timing array. Hopefully we'll do that in the next 10 years or so. Okay, so thank you, Pankaj. It's a beautiful talk, and I will move over to the next speaker. Big applause to Pankaj. So the next talk is by again a local resident. Vaidehi is going to talk about the origin of relativistic jets 2021 and beyond. Vaidehi, the floor is yours, and I will ping you after 25 minutes.
Thank you. I hope you can see the screen and you can hear me well.
Yes, we can. Please go ahead.
Okay. So thanks to the organizers for the invitation. I'm sure like everyone who has worked on relativistic jets or say blazars or radio galaxies, all they must have at least the question must have came to their mind that how these things have started, means how this blazar phenomena started, how jets are triggered. So these are some of the very fundamental questions which usually came to my mind also, and fortunately we just observed a few sources that holds the key to understand this fundamental problem in jet physics. So I'll be talking about these objects here. So we'll start with the very simple fact is that as we all know that our universe is full of galaxies. all types of galaxies: elliptical galaxy, spiral galaxy, disk galaxy, irregular, dwarfs, and all. 1 in about 100 galaxies host an active nucleus, and that we know that is called active, and its center of those galaxies are called active galactic nuclei, or AGN. Without going into the detail, we know that AGNs are classified as quasars or Cephers, where quasars are more luminous AGNs compared to Cephers are low luminosity AGNs. Type 1, type 2, where type 1, where we are looking close to the pole on view of the AGN, where the type 2 sources were looking the edge on view. We know radio loud, radio quiet AGNs, where this term radio loudness basically can be considered as a symbol for the presence or absence of jet. And then there are a class of blazars, where the sources that have powerful relativistic jets, and jets are pointed towards us. 1 in about 300 AGNs host bipolar relativistic jets. So you see, like 1 in 100 AGN galaxies have AGN core, and then 1 in such about 300 AGNs have relativistic jets. So this means the presence of jet is a very rare phenomenon. So the immediate question comes, how these jets are launched? What is their origin? So people have tried to study the host galaxies of these sources that have relativistic jets, and it was found that jets are almost all the time, jets are associated with massive gigantic elliptical galaxies. Means the black hole mass at the center exceeds 1 billion solar mass or so. Now we know from numerical simulations and from the recent observations also that elliptical galaxies are formed via galaxy mergers. And we also know that mergers often trigger AGN activities. So if we try to connect the dots, so this gives an indication that probably jets are triggered by galaxy mergers, because we have seen jets in elliptical galaxies. Elliptical galaxies are formed via mergers, and these mergers also trigger AGN activities. So they may trigger jet formation also. So what people have done so far, people have tried to study mostly type 2 radio loud quasars or radio galaxies. And they have found traces of turbulent past of these sources, giving indication that these sources underwent major or minor galaxy mergers in their past. So this supported the hypothesis that maybe jets are triggered by galaxy mergers. But the problem is that type 2 sources may not be the best type of objects to understand the connection of galaxy merger with the jet. So what we have to do, and second thing is that these sources are already evolved sources, where we do not know whatever happened in the past. So we need to find young AGNs where these activities are happening, where we can see the ongoing merger or interaction, or where we can see a young jet. So we need to find young jet that have which are hosting relativistic jet. We need to find type 1 AGNs so that we can observe the innermost regions of the system. And we need to find system with low jet power. Now, I am sure everyone understands that when we are talking about the type 1 AGNs that have relativistic, that have jets, in all likelihood, the radiation emitted by the jet will contaminate the overall observed radiation, or say the overall observed means jet emission will dominate. It will overshine the radiation coming from the host galaxy. So we need to find systems that have low jet power so that we can see the underlying host galaxy. Just giving you one example, you can see there are two cars on the left which has a powerful jet. It's very difficult to see what lies behind. But on the right, we have a low jet power AGN, where there we can see the host galaxy. So this is the idea. So putting all things together, we need to find a young type 1 AGN that have weak jets, and then we have to try to study their host galaxy environment. So there is a class of AGN called narrow line Seyfert 1 galaxies. I will try to justify that these sources qualify all these criteria. They are young AGNs that people have proposed long back, since in early 2000s. They are type 1 AGNs, we know that. But the question is that, do they have jets? As I showed earlier, that Seyfert galaxies are typically low luminosity AGNs. They are mostly radio quiet. less than 10% of narrow and Seyfert ones are radio loud. So they are almost radio quiet. They don't have jet. But in 2008, when Fermi was launched, at that time, a few radio loud narrow and Seyfert 1 galaxies were detected in the gamma ray band, and significant flux variability was detected. So this provided unambiguous confirmation for the presence of beamed relativistic jet. Okay. And then later I found a few more sources. So as of now, we know about 15, 16 such sources compared to thousands of blazars. So people who are not well familiar with the narrow and Seyfert ones, just giving you a very brief introduction about these sources. They are a class of AGNs identified solely based on their optical spectroscopic properties. They have a narrow Balmer emission lines where the classification says that FWHM is around less than 2,200 km per second. They have weak O3 emission lines and they show strong iron complexes. About 5 to 7% narrow and Seyfert ones are radio loud. That means most of these sources are radio quiet. And interestingly, these sources are powered by low mass black holes, about 1 million to tens of million solar mass black holes. And then people try to calculate the accretion rate. They found these sources are powered by very high accretion rate, often at the level of Eddington accretion. So people propose that these sources are rapidly accreting young systems. I have followed some of these gamma ray detected sources, and what was found that these sources have low power jets. On the left hand side, you can see where I show the accretion disk luminosity and the variation of the jet power as a function of disk luminosity. And these gamma ray detected Seyfert galaxies are shown with the stars, where the blazars are shown with the red circles. You can see that they follow the same pattern, the same trend shown by the blazars, and most of these sources occupy the low disk luminosity, low jet power regime. So it suggests that they are the sources having low power jets. And on the right hand side, I show the central engine property where we have disk luminosity as a function of the central black hole mass. Almost all these gamma ray detected Seyfert galaxies have radiatively efficient accretion system that you can see that disk luminosity is greater than 1% of the Eddington luminosity. And they follow the same trend as shown by the blazars. So this means these sources are having low power jets and they harbor low mass black holes. So now bringing all these things together, now we know sources which are young have relativistic jet. Now we know sources which are type 1 sources. And now we know AGNs that have low jet power. But the last question comes whether these sources show interaction or merger or turbulent activities. So yes, there are many gamma ray detected narrow line Seyfert 1 galaxies whose low resolution imaging done with mainly with the pan stars or SDSs show traces of ongoing or recent galaxy mergers. So this means these sources are the perfect, you can say, objects to study the interaction of the relativistic jet with the host galaxy, the jet triggering mechanism. So in this regard, I just give you one example of a narrow line Seyfert 1 galaxy, TXS 2116. This is a narrow line Seyfert 1 galaxy. It exhibits a flat radio spectrum. This source is detected in the gamma ray band, and it has shown variable gamma ray emissions. So this suggests the presence of a beamed jet. Jet is pointed towards us. And on the right hand side, you can see it's the low resolution R band SDSS imaging of this object. It doesn't look like an elliptical galaxy. It looks like some sort of like a spiral with like a S-shaped structure, maybe a spiral arm or whatever. So I had an opportunity to observe this object from Subaru a couple of years ago. So this is what we found. So it looks like that this is a system where a galaxy merger is ongoing. And probably this is for the first time where we are seeing a gamma ray emitting relativistic jet hosted in a galaxy merger. When and see in this is the J band image. On the center, the contour you are seeing, this is the radio contour VLA contour at 1.4 gigahertz. When we did this Galfit modeling, so it turned out that both galaxies are late type galaxies that have pseudo bulges. And this is aligned with the hypothesis that narrow line Seyfert ones, including gamma ray detected sources, are young AGNs. But one can ask a question here that how to ensure that these sources are indeed merging and they are not like in the plane of the sky, they are just overlapping on each other. So what we did, we carried out optical spectroscopy of both nuclei. So here you can see the optical spectra of both sources, both merging galaxies, which has confirmed that these sources are indeed at the same redshift. This means the merger is ongoing. And we took the optical spectrum from the 10.4 meter GTC and 4 meter William Herschel telescope. So now we know a relatively young system, ongoing merger, hosting a gamma ray emitting relativistic jet. So can we somehow determine whether jet is triggered due to this merging activity? And can we throw some light on this merging environment? Because this is probably a new thing which we were not knowing these events before. So let's start with this. First, we analyze the high resolution VLBA observations. So on the right hand side, you can see the image. And what we found that this source has a very compact jet. So right from arc second down to milli-arc second scale, this source, the radio emission remained unresolved. We see only a compact core. So from the upper limit, we calculated from the VLBA beam size, we calculated the upper limit of the jet length, assuming a small viewing angle, say about 3 to 5 degrees. That tells us about the approximately projected length. And then a certain assumption about the velocity of the jet, we calculated what would be the corresponding kinematic age of the jet. So it turned out that this jet is pretty young, about less than 15 kilo years. It's very, very young jet. Now, to understand the properties of the merger, what we did, we took the long slit optical spectra of the system, and then we extracted the optical spectra along the 8 different parts along the long slit. So this fuzzy structure that we see around both nuclei, this is the common envelope in both nuclei are emitted. So it's like we are seeing the late stage of merger, where these galaxies were almost on the verge of merging each other. So we extracted the optical spectra and then carried out stellar population synthesis. So see, because here you can see the different parts of this galaxy merger tells us about the properties of the merging, you can say, material or environment. And here the basic assumption is that star formation activities are triggered by this merging. So this means if we can try to understand the properties of the stellar population, that may give us some indication about the properties of the merger. So we carried out stellar population synthesis. There are some publicly available tools. And then from that, we calculated the age of the stellar population along the different parts of the slit and different other parameters. So what we found that stellar population is this gives us a merger, means we are seeing a stellar population which is having a typical age between 0.5 to 2 gigayears. And this time range is pretty consistent with that predicted from the theoretical simulations for the galaxy mergers. So now we see that these galaxies this merging event is happening for say about 0.5 to 2 gigayears, where the radio jet is having an age less than 15 kilo year. So this means this provides I would say it's a very strong evidence that this jet in this object is considerably younger than the merger. In other words, the relativistic jets, or you can say these jets, are triggered by galaxy mergers. Okay. Now, briefly talking about the merging environment. In the northern hemisphere, this GTC has one integral field unit integral field spectrograph called Megara. Probably one of the very few facilities in the northern hemisphere. So on the left-hand side is shown the H-alpha flux map for the system, and the white contours are that taken from the infrared image. So you can see this is a bright H-alpha emitting material in the form of a ring surrounding the jet. You can see the center, the brightest red. This is the gamma emitting narrow line Synchrotron. So here we see that this is a H-alpha emitting material surrounding the jet, and it goes on, this passes towards the companion galaxy and goes towards the southeast. Okay, but it's very difficult to explain how this, because we don't see this kind of structure in the infrared image. On the right hand side, we show the H-alpha velocity map. You can see it's a pretty turbulent structure environment. There is no systematic rotational pattern also. So probably this indicates a turbulent environment, maybe due to shocks that might have been originated due to the galaxy, this merging activity. But I would like to emphasize that Megara has a very limited wavelength range. So we are planning to observe the same source with the Muse mounted at VLT, because this source has a negative declination, so it is well observed from the from Chile. And then we also try to get some observations from ALMA to understand the properties of this merging activity. One can ask a question here is that this is only one source, what the big deal? There are exceptions everywhere. So no, there are many more gamma ray detected narrow line C41 galaxies that show distorted structures. So we started a campaign through our collaborators. We submitted proposals to all the biggest facilities available on the planet, including Keck, GTC, as well as Gemini telescopes. And we have started getting observations. So very quickly, I will give one example here, is that on the left-hand side is the infrared image of one of the narrow line C41. It looks like a boring elliptical galaxy. That's what was published about 3-4 years before using the left-hand side image. And it was proposed that this is an elliptical galaxy, just like a blazar. But on the right-hand side, we observed this source very recently with the Keck, which has a adaptive optics facility in the J band. And you can see that we are seeing traces of ongoing galaxy mergers. And you see the spatial scale that we are probing here, 0.3 arc second. So just to give an idea that this is the kind of resolution where is needed to address the cutting edge research problem as of now. So if we are thinking 5 to 10 years or say 20 years down the line, we can extrapolate, okay, what kind of resolution or what kind of observational facility will be needed to tackle front-end research problems. So to summarize, I have just finished my presentation. So to summarize that, I think I have convinced everyone that gamma ray detected narrow line C41 galaxies are the crucial sources to understand the origin of relativistic jets. Okay, I'll stop here. If you have any questions, comments, suggestions, please feel free.
Thank you very much. In fact, we have plenty of time for questions and comments, and so the floor is open. If students have doubts, I will prefer them to go first. Okay, I will begin with Pankaj, and I will keep scrolling to see. Yeah, Pankaj, go ahead.
Hi, very nice talk. Okay, I hope you can hear.
Yeah, please.
So what is the typical spatial separation? I mean, the projected separation between these two, I mean, the merging galaxies that you have shown and presented in this one. Probably you.
Yeah, it is about 2.5 arc second.
No, so I mean, I am asking in terms of
general.
No, not scale. I mean, kiloparsec or something like that. Actually,
you are asking in terms of kiloparsec?
Yeah, I mean the projected separation.
Yeah. So typically, you see it's about a few kiloparsec, not very large.
Okay, you have kiloparsec at the top.
Yeah, and even in the source which I showed in the last slide, this is within 1 kiloparsec. It's a parsec scale separation.
Okay, kiloparsec scales. So these are all nearby sources, right?
Yeah, these are all less than redshift 0.3.
Okay. Yeah. So the other thing is just so what if you see at radio wavelength but higher frequencies? Because I believe at lower frequencies, I'm not sure if we can see anything, but
there are not many observations available. We are submitting proposals to get more observations. Yeah, but hopefully we will see more. Let's see.
Okay.
Okay, then I will move over to Amit. Please go ahead.
Thanks. Hi, very interesting stuff. Can you hear me?
Yeah, please.
Okay. So I have two quick questions. One is,
as in this particular image, I can see the both cores which is lit, they are quite far away. So what exact mechanism you are considering which triggered the jet formation? That is one question. And the other question is that you said jets are weak in these kind of sources, these narrow line Seyfarts. So recently you people have published a paper with Andrea where you have seen variability of the order of few hours or less than 2 hours, I suppose. So still it's not a contradiction what you have said, this particular observation which or paper you have published recently. I'll be glad to have the comments.
Okay, thank you. So first of all, you see this, there are recent observations where people have proposed that radio loud AGNs preferentially reside in denser environment. Okay, where their chances of galaxy interactions are higher compared to radio quiet AGNs. So you can see it's like within a smaller volume of the universe, there are many galaxies. So there are chances of interactions are much higher. Okay, this is gravitational interaction. So I presume that, and they have also proposed that radio loud narrow line Seyfert-1 galaxies preferentially reside in a denser environment. So that may be one of the reasons for leading to the galaxy merging activity. Regarding PKS 2004 or general the jet power of these gamma ray detector Seyfert galaxies, on average they have very low jet power. What you are talking about is a specific flaring event, okay, which was a very short, which had a very short duration. So even in PKS 2004, when we calculated the jet power, though it is model dependent, but it turned out that the jet power is still very small. See that the short time scale variability you are telling about, this is a very localized event. And in fact, if we compare, because people try to calculate the mass of the black hole also from the variability time scale. So that also tells us that these sources are having low mass black holes. So it means we are talking about a completely different jet launching environment. They have a low power jet because they have a low mass black holes at the center.
Okay.
Thank you. I have
Thanks,
another. Yeah, I have maybe I will ask the last questions. So you are talking about the galaxy mergers associated with narrow line Seyfert-1 galaxies. So I mean, you might have estimates for the component. Is it considered to be a major merger or a minor merger?
No, this is in this case, it is a minor merger. We calculated the total stellar masses for both galaxies. It turned out to be that the gamma ray detected source, which is at the center,
correct,
this is much more massive compared to the companion galaxy. So there is, in the literature, I found there is some certain mass ratio. If the mass ratio of the two galaxies is larger than that, it can be considered as a minor merger. It's a minor merger.
So it's around 10 or more.
Yeah.
Okay, since the black hole masses you're talking about are in the million solar mass black hole range, this may be sort of an interesting implication, especially for LISA, whether whether they can. Of course, you have to look down the line, but whether they can form, if there are too many of them, these are just the tip of the iceberg from electromagnetic observation, whether they can be projection for some sort of a background as you are identifying these objects with the mergers, and so that may be an interesting option.
Yeah. There are recent, I remember last year there were a few white papers which came from this AAS, where people have proposed that galaxy mergers could be potential targets for the future gravitational wave detection.
So that's true. That indeed the case. But here the problem will be if there are so many of them, then that will end up creating a background rather than individual sources. And especially if you are going to identify a class of AGNs as associated with the merger, that may have implication. That's what I'm saying.
Yes. So far only very few sources are known. Let's see.
Sure.
We will see many more observations are coming.
Sure. Yeah. Okay, and I think we will move on. Thank you very much. And So we will move on to the next speaker. Next speaker is Professor Saikia. Sykes is going to talk about young radio sources. Sykes, I will ping you after 12 minutes, if you don't mind.
Sure.
Thank you. Please go ahead.
Yeah, thanks very much, Gopu, and a very good afternoon to all of you. So taking on from the previous talk, I will talk about jet propagation in young radio galaxies. And the basic message is that jets in young galaxies tend to have a bumpy journey. And the thing is, what can we learn from them? Are these clouds or that the jets bump into, are they part of the fueling process that triggers an AGN? Do they trigger star formation? Is it ubiquitous? And what is the evidence for it that they bump into such clouds as they start off from the nucleus of the active galaxy? So I will not deal with generation of jets. I will talk more about propagation of jets. And when I talk about young radio galaxies, I'm going to talk about galaxies which are small in size. The largest radio galaxy is about 4.7 megaparsecs in size. It's one which we found from a combination of GMRT, Effelsberg, and VLA observations. But to reach to those dimensions, they have to start young. They have to start small. And so today I will confine myself to these young sources, which are typically defined to be less than about 20 kiloparsecs in their projected linear size. I've just given you 4 examples over here to illustrate the kind of structures that one tends to see in these small radio sources. And you can see that there is a wide variety of structures that you see. There's one which looked like a Van Riley class 2 object with hotspots at the outer edges, no jet, and there is 3C48 where the jet seems to be completely disrupted, very close to the nucleus. And I've given the typical sizes over here. This is about 107 parsec. This is slightly larger. The bottommost compact component is believed to be the nuclear component over here. Here is a source where energy supply to the outer lobes may have stopped. So the question arises again whether the nuclear activity itself may be episodic, not only in these small sources, but also in large sources where there is evidence for it. But this may also be occurring in small sources. And then there is this Galaxy 2355 plus 4950, which have jets on either side of it. A compact feature over here, not well resolved over here, is believed to be the nucleus of the galaxy. So you can see there is a wide variety of structures. And when I say there is a peak spectrum, these are all synchrotron emitting sources with a non-thermal spectrum, steep non-thermal spectrum, optically thin, but many of them tend to turn over at low frequencies. So why do they turn over? It is believed to be largely due to synchrotron self-absorption in the hotspots themselves because the cores are weak. These are steep spectrum sources. So they're not heavily relativistically beamed, even there may be effects of mild beaming. And this is so the more compact the source is, the higher the frequency at which it peaks. But the high frequency peakers also, there is a catch. Some of the flat spectrum objects when flaring tend to exhibit a peak spectrum. So one has to monitor these objects over long periods of time to find out the genuine peak spectrum sources. The higher the peak frequency, the smaller the size of the source. So that broad trend is consistent with synchrotron self-absorption, although detailed spectral shapes of several sources suggest that free absorption may also be important in at least some cases. Now, how do we know they're young? Of course, we can do estimates of them by measuring their velocities or measuring their spectral ages. Measuring their velocities actually is a long and tedious job because you need the most compact objects because the motion is very small. It's a few milliarc seconds or so per year. So you need VLBI scale observations, and they're moving much more slowly than the superluminal sources you heard about earlier. So you need to monitor them over long periods of time. For example, a standard Australian telescope compact array, which did not show any motion over a 12-year time scale when Tassosiomus and his collaborators looking at it, showed motion when monitored over a period of 32 years. So typically these sources have been monitored for about 5 to 10 years or so. And you measure it over long periods, you also see complex motions. But you can see that the velocities of advancement range from about 0.04 C to about 0.4 C with a median value of about 0.1 C. And when you go back and estimate what the age should be, the smallest is about 20 years. So you can see even by, given my age of 65 plus, this is pretty young. So, but there's several around 100 years of age or so, and the median value is about 600 years. This is about 40 sources which are known till now. Jet components tend to have higher velocities not only in the superluminal sources, which you heard about earlier, but also where it has been measured, but also in these compact C-spectrum sources, where we have been able to measure motions of features in jets. But there are also subluminal ones, as in the standard calibrator for both the GMRT and the VLA and many other telescopes, which actually shows that when the quasars tend to show superluminal motion, they're overall consistent with the unified scheme for active galactic nuclei. Now, once we know that they're young, I want to find out that as they traverse outwards from the nuclear region when they're launched, what is the kind of environment that they face? And what implications does it have? And how do we find out from radio observations? Right now, you heard about observations at optical wavelengths, or there have been also studies with adaptive optics, space-based telescopes trying to look for what might lie there in the nuclear regions of the galaxies. But at radio wavelengths, what happens is that if you can find evidence of it, you can actually go through the dust and probe much closer to the central engine. Now, to first show that jet propagation is not very smooth for them, they have a bumpy ride, is that when you look at the motions of these objects, for example, this is an object 1335 plus 5844, which is a compact C-spectrum source. And this is the motion which they have monitored with respect to the northern hotspot, because the core is believed to reside here, but you can see it's a bit elongated, it's a bit weaker. And you can see these two hotspots over here, B1 and B2, which should be better resolved in high resolution images. Their motion, there is a slight motion along the axis as you'd expect, as the jet is propagating along the interstellar medium, trying to plow its way through, but you find that there is significant transverse motion. And this is not the only example. And you can see these evidences of obstruction in its path by also, for example, when you see a jet which is deflected from a primary hotspot to a secondary hotspot. How do you know it's a secondary hotspot? Because the secondary hotspot is seen to be moving away from the primary hotspot. So a jet has ricocheted of material, of a cloud of gas, feeding relativistic plasma to a secondary hotspot, which is propagating outwards, and that is something which you can determine from very high resolution observations. There's also models which involve what Peter Scheuer suggested a very long time ago, that the edge of the beam could be unstable and poke different points at different points of time, which would also give you multiple hotspots. But you can see definite evidences of obstruction by this kind of transverse motion. And this is not the only example. A significant number of them have shown motion transfers to the axis, and also motion of the secondary hotspot away from the primary hotspot, to show that there are obstructions, there are clouds, and they are not symmetric. You can probe this in other ways as well. And for example, you could go and measure the hotspots for individual lobes and consider the most asymmetric sources. I picked up two examples over here, two studies over here. One is by Monica Orienti and her collaborators, where they have tried to pick up two of the very asymmetric sources from the Bologna sample of compact spectrum sources and try to find their ages from spectral aging arguments, because as you know, the higher energy electrons would radiate to higher frequencies, and the spectrum will steepen faster at higher frequencies, and the spectral break will shift to lower frequencies with time. So from spectral aging, you can determine what the spectral fitting, you can determine what the age is, and from the separation, you can determine what the velocity is. Okay, now you can find over here that the velocity over here for the component which is much closer is much, much smaller than the one which is further away. Similarly, but a more direct measurement would be kinematic ages. And that has also been done. For example, this image which I've shown over here, the separation ratio is about 1.8. So the nearer component is much closer. And when you actually estimate the velocities, you find that the nearer component is really slowed down by more than a factor of 2 compared to what is further away. And they did some modeling of the external plasma, and they find almost a factor of 12 difference in particle density over there. So you can see that there is obstruction, which you can find from the structural asymmetries. Am I cherry picking? Am I picking up the most extreme examples to propagate a viewpoint that you can try and estimate by considering a much larger sample, probably uniformly selected? But as you saw, they're trying to monitor these motions over long periods of time, or getting spectral coverages of compact hotspots in these millisecond scale structures is not terribly easy. So what we can try and do is that we can make images and just look at the symmetry structures of these sources. For example, if the external medium is symmetric and the jets are symmetric, you would find reasonably symmetric structures. But on the other hand, if the medium in the nuclear region is asymmetric, you're going to get far more asymmetric structures. Asymmetry can also arise because of light travel time effects, because the sources are not preferentially oriented towards you. You may pick up preferentially oriented sources at high frequencies because of beaming effects. But if you take low frequency selected samples, they should be more or less randomly distributed in the sky. Now you can see over here that the further component in that case would appear closer, because at a given point of time, light would have started from there earlier. But what you see over here is that this is something which we did some years ago, but this has been repeated by several authors using different samples, and the basic trend is the same. The shaded ones, the ones which are darkened, are the compact C spectrum, small sources. And you can see this is upper one is for quasars, lower one is for galaxies. And you can see that the further sources are far more symmetric than the compact C spectrum sources. So clearly in these early phases of their evolution, they're bumping into gas clouds. Whether they're dwarf galaxies which are being swallowed up, whether there could be dense gaseous clouds that are falling in which fuels the nucleus, we don't really know. That would be speculation right now, but they're clearly facing such an environment. This is one such source which we studied in great detail, 3C459, which is also a starburst galaxy. The nucleus is sitting somewhere over here. And this is the component which is sort of not being able to move forward, but this is larger in sizes. You can't really do VLBI kind of measurements over here. There's nothing compact, everything would be resolved out. But we can probe such sources by other means. How do we do that? We'll try and come to that in a moment. But just to tell you that, that one thing which requires a bit more work and study is to find out that when it hits a cloud, how does it become more symmetric as time goes by? We did some simulations to show, taking asymmetric slopes in central region, that it does become asymmetric and tends to symmetrize, but we need more realistic sort of simulations than what we did many years ago using the ZS code. What you can do is also probe it via polarization when you can't measure motions. I was very surprised when I first made these images about the kind of polarization asymmetry which you see. Why should you see it? Because when you go towards a cloud which you're ionizing, which the jet is sort of ionizing, shock heating some of the material being entrained. So that will lead to a greater amount of thermal material over there, which is going to depolarize the emission compared to the other low. So I would expect a greater degree of polarization, asymmetry in these sources. And Neeraj Gupta and I, after I made these maps, we had a careful look, and you can see that for CSS sources, this is the kind of distribution you see, and this is for quasars, by the way. If you do galaxies, the lower as a control sample to put us at a disadvantage, and you can see a hugely significant difference between compact steep spectrum and larger sources.
Sykes, 2 more minutes, please.
Yeah, here's the other object which I showed you. Here again, you can see that the low which is sitting it is completely depolarized. So that provides, polarization provides another evidence of clouds ricocheting off dense gas clouds, which are perhaps in some cases maybe triggering the supply as well. You can go deeper and probe the nuclear regions of these galaxies by measuring the rotation measure as well. And we have done a major project using the very large long baseline array. And there's a wide kind of phenomena which you can see. Here is a jet in 3C43, which has been bent sharply, and there is a region of very high rotation measure over here. Here, there are no sharp bends in the jet as such, minor bends, but there is a high rotation measure all along. So there are cases where there is material untrained as it propagates, giving rise to high rotation measures, besides sort of a screen in front. But there are also many, many clear examples where we see evidence of it from the rotation measure, sometimes tens of thousands of radians per meter squared, which affect the flow of the jets. But you can see even after ricocheting off, it is reasonably well collimated. So when it recollimates, when it doesn't, this is just another example I've shown you, 3C147. I'll just end in another minute or two with just a summary of future work. The core nucleus over here, this is slightly larger scale. So we could do this experiment with a very large array. And you can see again over here, this is 2 8 gigahertz frequencies, slightly separated. This is at 15 gigahertz. And you can see the rotation of of the vectors, these are electric vectors, compared to the one where it has a smoother path through the magnetoionic medium. And in the rest frame, the radians, the rotation measure for the one which is interacting is about 3000 radians per meter squared, compared to about 600 for the northern component. So it is going through a turbulent medium. Now, I'll just close in a couple of minutes with just some suggestions for future work, which I think are important to understand, both from an observational point of view, as well as from a theoretical point of view. What collimates jet propagation? What keeps it collimated after an interaction? What conditions sometimes completely disrupt a jet, and what conditions it does not? What role does magnetic field play? Can we link these clouds to the fueling of the black hole itself? Do these jets trigger star formation? We have examples where the famous Minkowski's object, plus there's several other examples, where we have clear populations of very young stellar population when a jet strikes it. And we also have the alignment effect, where the radio sources tend to be aligned with the UV radiation, which is presumably a significant amount of it is due to hot young stars. And this is seen in compact T spectrum sources on all scales where we have been able to see it, as well as in larger sources at larger redshifts. So we have jet-induced star formation, and we also know that when we heat up the gas, it is going to inhibit star formation. What are the conditions which favors one over the other? We need to measure molecular mass and star formation rates for a large sample to understand some of these effects, and also effects of gas on the propagation of the jets itself. Very preliminary work which Chris and I did, we showed that when there is more molecular mass, the jet velocities are lower, but we need to do greater samples and do it more carefully. And if radio jets are driving shocks, can we find evidence of this from X-ray observations, which will also constrain impact of the jets on the host galaxies. We can also look at AGN feedback, as these aspects are called, by H1 outflows with telescopes such as the JMRT as well. But we also need inputs towards understanding the physics of it from numerical simulations as well as analytical models, which put in more of the physics into it than we have been able to do till now. And these aspects are formed in all kinds of radio galaxies, whether it be high ionization, high excitation radio galaxies, low excitation radio galaxies, Vanneroff-Reilly class 2, class 1. So I think there's a lot to be learned, including for the narrow line Seyfert ones, as we just heard about, and also the new class of galaxies called FR0s, which have the nuclear component but no extended features, which Ranieri Baldi and his collaborators have highlighted to us. So there's a lot of things to be understood, although with inputs from both the observation and theoretical fronts, we have made significant progress. Thank you very much.
Thank you very much, Sykes. We are open for a few questions.
Sure.
I will wait for some students to ask questions.
Sure. Actually, a lot of this covered in this recent review, which Chris and I had written, which has just come out last month. So you could look it up for further details on these young radio sources.
Thank you very much. I can't find any students. So I have a couple of questions, if you don't mind. So this is about, you mentioned about this non-radial motion. Can that be also because of some sort of instability is developing in the jet? I mean, if that is the case, that can make a non-radial displacement, and that is there any way to constrain that the absence of such say Kelvin-Helmholtz instability or something like that?
Actually, the thing is that if one probably got more detailed measurements, that the signatures of the Kelvin-Helmholtz instability along the flow of the jet, which you'd expect, you might be able to make that out. Right now, what we have been able to measure are just the hotspot motions. And they often seem to be along the same direction when there are multiple kind of hotspots. So I think one cannot completely rule it out, but one would like to, but the general systematics of motion tend to suggest that probably it is due to interaction with the cloud. And also the fact that you have secondary hotspots, which you see moving away from a primary hotspot, showing that, the structure is different, is usually less compact than the primary one, also suggests that the primary hotspot has been inhibited, and people have built up models where there's a D-level model, nozzle built up in the cloud, and then, is further channelized. So that seems to work for at least some sources on large as well as small scales.
Okay, thank you. And another one is, so these sources are not very far away, right? In the sense that,
they can be.
Okay. Do they emit in high frequencies like, 3, 4, 5 gigahertz and things like that? No, right? These are all L-band observation. Or
no, there are some of these are high frequency observations as well, because the rotation measurements, which I said, they fall at 8 and 15 gigahertz generally.
Okay.
Proper motion measurements are also at usually between 5 and 15 gigahertz, because you need the resolution, and with the higher frequencies, shorter wavelengths, your resolution is better for the same array. And many of these high frequency peakers or the peaked spectrum sources have been picked up from high frequency surveys, because at low frequencies, they would often be below the detection limits.
Oh, okay, cool. So the reason why this is and some of the transition you are talking about, whether the jet is kinematically driven rather than the magnetic, those will be taken up by, there will be the next generation EHT.
Absolutely. Yeah.
And that will be the place, it's not going to be just MIT7 or the Galactic Center or J287 or 3C279. There will be, lots of sources where the aim will be to look for, cases where they can actually probe where this transition occurs. And so the nearby sources, that will be very useful.
Sure, absolutely. I mean, there are nearby ones as well, but it sort of covers a large redshift range.
Sure. Okay, thank you very much, Sykes, for a fantastic talk. And we will move on to the next one. So big applause to Sykes. Can you de-share the screen if you don't mind? Yeah, thank you very much. Okay, we have the next speaker, Vineet Hoja, again from Aries. The speaker is around. I'm sorry, I can't really find.
Yes, I am around. Can you hear me?
Very vague. Can you share the screen, please?
Okay.
You may want to come closer to the mic. To me, it's very weak. So very faint voice.
Okay, I try.
So, Vineet is going to talk about comparative intra-night optical variability of radio narrow line Seyfert-1 galaxies with and without radio jets. So, I presume you will be following Vaidehi Palia's topic. So, please go ahead.
Can you see my screen?
We can't see your screen for the time being.
Wait a minute. Okay.
What about others? I have no idea. I can't see. That's all I can say.
Okay.
Okay. It's coming now.
Now it is visible.
Yes, it is. So please go ahead.
Okay.
And I will, I will give you a reminder around 12 minutes or so.
Okay. So this is Vineet Hoja from Aries. So going to discuss his work, comparative intra-night optical variability, study of radio loud narrow line Seyfert-1 galaxies. So the motivation of this work is simple. Flux variability from minute to hour lifetime scale in an AGN is termed as intra-night optical variability, and this tool is sometimes alternatively used to verify the presence of jet in an AGN, because it is observationally well established that the radio loud jet dominated sources such as blazar exhibit a stronger INOV both in terms of INOV amplitude and duty cycle. So what is duty cycle? Duty cycle is the fractional time for which an AGN is found to show variability. But however, this tool is established based upon the known jetted object, that is blazar, because other part of it hasn't explored, because non-jetted blazar doesn't exist. So therefore, till now, the comparative INOV study hasn't explored in such subclasses of AGN that consisting of jet and non-jet. So the question is, in which subclass of AGN such study is feasible? So the answer is narrow line Seyfert-1 galaxy, because this class of AGN consists of jetted and non-jetted objects. So these AGN are characterized by the narrow width of Brammer emission line with FWHM of H beta less than 2000 km per second, a small flux ratio of O3 by H beta less than 3, and its optical spectrum consisting of strong iron emission line in their spectra. So another thing is narrow line C41 galaxy are high accreting AGN. Therefore, dilution of its non-thermal optical emission by comparatively much steadier optical emission contributed by its accretion disk is quite likely, because the time scale of variability of jet and accretion disks are different. Therefore, sometimes micro variation are harder to detect in such class of AGN. So if we get a positive correlation, that is jetted narrow line C41 galaxy are found to show more INOB, then this result would be valid in other subclasses of AGN in which dilution of non-thermal optical emission is less likely to affected by the optical emission contributed by the accretion disk. So next task is to collect a sample of narrow line C41 galaxy for which jetted and non-jetted information were available. So, another thing, because the confirmation of jet in its radio image depends upon its radio resolution. Therefore, we have collected the observation of VLBI that currently having the best resolution. So after doing the literature search, we have found 23 such radio loud narrow line C41 galaxy, and VLBI observation are capable of confirming jet in 15 radio loud narrow line C41 galaxy and non-jet in remaining 8 radio loud narrow line C41 galaxy. So we have done the observation, INOV observation in 3 night session using the 4 Indian telescope, 3 from ARIES and 1 from the IIA. So data reduction of this internet session was done following the standard task in the IRF and DIFOD. Since we are interested in the INOB in this source, therefore differential photometric technique was used and produced a differential light curve of each sessions. So this is the sample differential light curve for jetted narrow line, jetted radio loud narrow line C41 galaxy for the 2 sources, and this is for the non-jetted radio loud narrow line C41 for the 2 sources. So from the differential light curve, it can be seen that the jetted radio loud narrow line C41 galaxy are more amenable to variable compared to non-jetted radio loud narrow line C41 galaxies. Furthermore, for testing the INOV statistically, we have applied the 2 different flavors of F-test on their differential light curve, which are standard F-test defined by this expression. Here sigma square is the variance of differential instrumental magnitude of source and comparison star, and this is the photometric error of the same. And second test that applied in this study is the power enhanced F-test defined by this expression. Here S square QSO is the differential instrumental variance of differential instrumental magnitude of source and reference star, and S square C is the stacking variance of reference star and comparison star. So a source is considered as variable if F-test value is found to be greater than its critical value and 99% confidence level, and probable is this value is found to be between 95 and 99. And non-variable if this value is found to be less than 0.95% confidence level. So furthermore, we have estimated the duty cycle, which I have already explained, which is defined by this expression. Here delta T I is the actual duration of ith monitoring session corrected for its redshift, and Ni is taken to be 1 if INOV is detected, otherwise Ni is taken to be 0. So based upon, so we have estimated the duty cycle for these 2 subsets of radio loud narrow line C41 galaxy for both the test, and after estimating the duty cycle, we have found the jetted radio loud narrow line C41 galaxy. So duty cycle almost 2 times of the duty cycle of non-jetted radio loud narrow line C41 galaxy. So furthermore, we have also sub-classified jetted radio loud narrow line C41 galaxy into jetted gamma ray detected radio loud narrow line C41 galaxy and jetted non-gamma ray detected radio loud narrow line C41 galaxy, because this class of AGN consists of gamma ray detected and non-gamma ray detected jetted radio loud narrow line C41 galaxy. So after estimating duty cycle, we have found a very contrast difference between these 2 subclasses. So jetted gamma ray radio loud narrow line C41 galaxy has shown almost very much high duty cycle compared to the jetted non-gamma ray detected radio loud neuron Synchrotron galaxy. So we have searched the reason behind this contrast difference in duty cycle. So one reason could be the presence of relativistic jet in case of jetted gamma ray detected aeroline Synchrotron galaxy, because detection of gamma ray emission from the agent suggests the presence of relativistic jet in them. So furthermore, in the literature, we have searched the jetted speed of jetted gamma ray radio loud aeroline Synchrotron galaxy, and after doing the literature search, we have found out of 8 sources, 6 sources, jetted speed of 6 sources. So this table represents the jetted speed of 6 gamma ray detected RL NLS Y1s along with the output of our INOV observation. So based upon this result, we conclude first that the jetted AGN are more amenable to show INOV compared to non-jetted radio loud neural Synchrotron galaxy, because jetted radio loud neural Synchrotron galaxy has shown the duty cycle almost 2 times, which is 41%, compared to 20% of non-jetted radio loud neural Synchrotron galaxy duty cycle. So therefore, based upon this result, we conclude that the INOV detection with higher INOV duty cycle can be used as indirect evidence of presence of jet, even also in the case of low luminous, high accreting AGNs such as narrow line Synchrotron galaxy, in which dilution of AGN non-thermal optical emission by its much steadier optical emission contributed by its accretion disk is quite likely. In this study, we have also found a correlated INOV detection with the supernovae motion in the radio date, except for these sources, for which we haven't detected any INOV detection in its 2 monitoring session. So however, this source has shown INOV detection in its 6 monitoring session.
Hello. I seem to have lost the speaker. Is that true for others or is just for me?
Hello. Can you hear me?
Now we can hear you. In between
Okay. So in this study, we have also found a correlated correlate INOV detection with the speed of jet, except for this source, for which we haven't found any INOV detection in its 2 monitoring session in our study. So however, this source has shown INOV in its 6 monitoring session by Palia et al. During in 2016. Therefore, we conclude that this non-detection in our study may be due to undergo into the quiescent gamma ray phase of this source. So furthermore, we have found a very interesting result in this source, which is non-jetted radio loud neural Synchrotron galaxy, which is not expected to show flare kind of activity, but during its 3-hour monitoring session, one can see that at 22.37 UT, there is a sharp change in its differential flux between 2 consecutive points of 14% within 6 minutes. So first we suspect that whether this is due to host galaxy or intrinsic. So for which we have seen its seeing disk variation, which was found to be constant during its 3 hours of monitoring session. Another thing we checked that whether it is at low redshift or high redshift. So its redshift was 0.49. So based upon high redshift of its source and seeing constant seeing variation during its monitoring session, we conclude that this variation seems to be genuine and not associated with the host galaxy. Furthermore, we noticed that this sharp change was accommodated by just 2 points, which is always susceptible. So therefore, we have reproduced its light curve using its 100-second sampling time. In this light curve, the sampling time is 300 seconds. So we, after reproducing the 100-second sampling time, we found that this sharp variation is accommodated by 4 points rather than 2 points. So based upon this reproduced light curve, we conclude that this sharp variation or flare is genuine and not associated with the instrumental effect and host galaxy. For
2 more minutes, please. Yeah.
Just last slide. So for this sharp variation, we have estimated the flux doubling time using our conservative assumption that equal contribution is coming from the accretion disk and synchrotron jet, and found its flux doubling time to be minute-like. So the exceptional variation and these minute-like flux doubling time support the jet-based origin in this non-jetted radio narrow line C41 galaxy. However, non-detection of jet in its VLBA observation might be either due to the quiescent state of this source during its VLBA observation performed in 2013 and are due to limiting sensitivity, because we have detected flare in 2018. So there was a five-year gap. And another reason could be non-detection of jet in its VLBA observation could be due to its lower black hole mass, which is 10^7, and lower radio luminosity, which is 10^41 erg per second, which indirectly implies to harbor less powerful jet, hence not capable to escape from the confines of host galaxy. And last reason could be non-detection of radio jet in its VLBI observation could be either through synchrotron self-absorption as it occurs in gigahertz peak sources, or probably via free absorption, because the observation was taken in gigahertz frequency during its VLBI observation in 2013. So thank you.
Thank you very much, Vineet, and I will open the floor for questions and comments. Oh, that's a beautiful picture. I've never been there. So
this is
okay.
Picture.
Questions and comments, please. So Vineet, so the question of intraday variability, or what you call intranet variability,
Yes.
but if it's it can be problematic if you have say something like a 6-hour variability.
Yes.
Then within a night, talking about a variability will be problematic, right? So is that I mean, are there in the field, you follow it with a bunch of telescopes so that we can confirm it very confident that indeed it is showing intraday or intraday variability?
Actually, intranight variability is a minute-like variability less than a day.
Oh, okay.
So we have observed during a in a night. So during a night, if we see if we found any variability, then we call it intranight optical variability. So we observed,
and these are not persistent, right?
Yes. So we observed it with a single telescope and in a single night. So what you are talking about is long-term variability. So if we
no, not long-term. What I'm saying is that if the intranight variability, as you're talking about, is going to be persistent, then it's sort of a bunch of telescopes can make because then you will have data. Of course, it's only for in an hour or two, it's fine. But if it's for say several hours, then one night may not be sufficient to establish from the spectrum analysis that what you are seeing is a variability. You know what I'm saying?
Right. You are absolutely right. So for the confirmation of variability, we generally take minimum 2 two sessions for a source to confirm its variability. So generally we take 3, but if the night is not available or sampling time is very less, in such a situation we minimum take 2 internight session for a source.
Okay. Thank you very much. Yes, do we have any announcement? Is it a question or an announcement?
No, I have a question. I have a question.
Yeah, please go ahead.
Yeah, Vineet, I just wanted to see the light curve again, and you showed that some data points are taken from 3.6 meter.
Yeah, whole data point for this source, peculiar source, had taken from 3.6 meter imager.
Oh, okay. So what is the magnitude that you have covered?
So the is 19.1, and the sampling time was 100 seconds. So to get the enough SNR, we have stacked that image to make 300 sampling time. So this is 300 second sample right curve, and this is 100 second sample right curve.
Okay, very good. So what is the error bar in 100 seconds? You are getting 0.01 magnitude or less?
Less than 0.01, less than 0.1, I think. Yes.
0.01. Yeah.
0.01.
Okay. So it's a kind of credible detection as far as variability.
Yes, because we expect variability or flare in jetted object, but we have detected the flare in non-jetted object. So that is very important result that we achieved from the 3.6 meter telescope.
Okay, very good. Thanks.
Okay.
If you have no further questions, okay, there are more questions, I presume. Go ahead.
Yeah. So Vineet, hello.
Can you identify?
Yes.
Yeah. So for the non-jetted sources where you detected the intra-day variability,
yes.
So have you checked the high sensitive, high resolution VLA observations?
Actually, while making the sample, this was the doubt in our group that non-detection of jet is related to the resolution, right?
Okay.
So while making the sample, we have taken the observation of those sources, available observation of those sources for which VLBI observation were available. So these are sources were confirmed non-jetted sources based upon its VLBI observation, which have currently best resolution in the world.
Okay, so it's just a suggestion. Why don't you try to observe a good sensitive VLB observation for these sources?
Okay, that can be doable, because if we do the very sensitive observation with the VLBA, then
Yes.
it may resulted jet for this source, because what were the currently available in the literature, that has resulted non-jet for this source.
Okay.
So that's why we have given this number of region for non-detection of jet in its VLBI observation. One may be because of its sensitivity or quotient phase. Another would be its black hole mass and low radioluminosity. So there may be jet, but because its power is very low, that's why it is not coming out of its host galaxy. So we can't resolve it.
If you are planning to observe with VLBA, so it's good. Yeah.
Okay. If you have no further questions and comments, and the rest can be taken into, in the Slack channel. So we will break for the, coffee and tea, and we will reconvene in around 20 minutes or so, 25 minutes or so. So around 4:45 for the next 3 talks. So thank you very much, and a big applause to all the speakers of the session. Are there any announcement from the LOC?
Professor Gopakumar, for your consistent support. So let's gather again after tea break, and it's a joint tea break / poster session.
Okay, thank you.
No,
Good evening. I'm trying to get ready for the next session. Do we have all the speakers here? Pranjapriya, Suventu, and Sumana?
Yes, I'm here.
Okay, excellent. So I will kind of beep you around 12 minutes. You got 15, so.
All right. Yeah.
Can you share your screen if you don't mind?
Yeah, sure.
Excellent. Thank you.
Yeah.
Maybe you can see there is this. You can use a full, full window mode if you don't.
Yes, I'll try for that.
Yeah, that's better. So.
Okay.
Excellent. We can begin if there are sufficient parts. So yeah, we are getting around 40 people are coming in. So.
Okay, sure. Shall I start?
Yeah, please do that. Thank you.
Okay, thank you. So good evening. I'm Pranjapriya Goswami, research scholar from Tejpur University. So I'll be talking about our work where we develop a synchrotron emission model to interpret the extra emission in high energy peak blazars. So this work is in collaboration with Dr. Sahainathan, Professor Mishra, Dr. Atrisana, Dr. Rupjiti Kokoi. So I'll be talking about the curved exospectral features, our approach to interpret the spectral curvature, then the correlation analysis the detailed interpretation. So as for the blazars, these are the jetted AGNs and they emit in a wide range of energy band from radio to TV. So origin of emission in different energy bands could be due to separate or probably the same electron or particle population. So concerning the emission mechanisms, so there are two viable mechanisms. One is synchrotron mechanism and inverse counting mechanisms. So in a very simplistic scenario, the double peak acidity of the blazar that we see can be interpreted in terms of synchrotron self-contained model, where the first peak is attributed to the synchrotron process and the high energy peak is attributed to the inverse counting process, where the required state photons are contributed from the synchrotron process itself. So here in the double peak acidity, the UV2 extra part is very important as it covers the synchrotron peak as well as the valley part. These two regions are very important to constrain the broadband acidity. So now, other important feature is that in this energy band, we see the spectra is smoothly curved. So this curvature we see around the peak as well as in the falling part, and this curvature cannot really explain with a simple power law model, and at times power law with exponential cutoff or a broken power law fails. So this curvature is also seen in the GV to TV in the high energy part peak as well. So to explain this curvature, there is this log parabola distribution where this functional forms are shown here on the left hand side. And here this distribution can be approximated as an energy dependent acceleration probability mechanism. And here the model parameters are a spectral index at a particular pivot energy, and then the curvature around the peak is beat up by the beta parameter. So this model has been successfully implemented in a large number of IHVL sources. And this analysis showed various correlation trends, like the correlation between the model parameters, then correlation between the acidity peak energy and the acidity high, then correlation between the peak energy with the curvature. Although this the first correlation that is between the model parameters is largely inconclusive, shown by many authors. So even though this log parabola distribution is capable to reproduce this synchrotron acidity very well, there's one problem there is this, the model parameter, we cannot directly connect them with the source parameters. So this is the motivation where we try to model or interpret the observed spectral curvature in terms of some physical parameter that can have, so that we can have a better insight into the particle acceleration and ionization mechanism, so that is responsible for the extra emission and the jet. So here is our approach. We adopt a steady-state two-zone model under electronic scenario. So here, what we consider a monoenergetic particle injection into the acceleration zone, where the particles are accelerating in a shock font. And then here on the first equation, we have various particle. On the left-hand side, we have terms corresponds to particle acceleration, then radiative term, then particle diffusion term. And on the right-hand side, we have the monoenergetic particle injection term, which is a delta function. So here we have separate acceleration and cooling or emission regions. So in the cooling regions, so we have the terms on left-hand side is radiative term, and on the right-hand side, we have the particle diffusion term. So here we consider that the particle diffusion is energy dependent. So with this assumption that for a constant acceleration timescale, the energy escape timescale is energy dependent, and we estimated the emitting particle distribution, the equation shown on the right-hand side. So then eventually we estimate the observed synchrotron flux, and that flux is in terms of the parameter kappa. So here kappa is, we can see the energy dependent index of the escape timescale. And this is one of our model parameter, which actually represents the intrinsic curvature, that is the curvature of the particle spectrum. So now with this model, we also derive a nice correlation between this model parameters, and we show that these model parameters are related to the source parameters, that is the source magnetic field and the jet Doppler factor. So other model predictions are, one thing is we show the relation between the spectral curvature with this our kappa parameter, and also we show that this curvature or this kappa parameter is related to the acidic peak energy. So this model suggests a positive correlation between this acidic peak as well as the curvature. So other very important information can be drawn from this model is that the effect of turbulent index. So as for the stochastic acceleration, as we know, the particle acceleration due to magnetic turbulence, where this particle diffusion is governed by the scattering of the magnetic turbulence. So here, if you want to estimate the escape timescale, due to particle diffusion, it is given by e to the power q minus 2, where q is the power law index of the turbulent energy spectrum. So here q varies between 1 and 2, and these different values of q represents different type of diffusion. So the lower limit is the Bohm limit, which shows this particle mean free path scales as the gyro radius. Then comes Krasner and Kolmogorov, and this two provides a very hard spectrum. Then comes hard sphere at q equals to 2, and the hard sphere, this particle mean free path, is independent of energy. So now we can actually compare this time-dependent escape timescale with our EDT model, and we find that this our kappa parameter varies as 0 to 1, representing various type of spatial diffusion. So to test this model, EDT model, we used the source marker 1421 observed here in 2012 to 2017 using 24 new star observation and 16 combined XRD plus new star observation observed within 3 hours time gap. So this observation includes the observation from a very big X-ray flare observed in April 2013. So here the EDT model we use, used the EDT model as a local model in XPAC, and then we perform the spectral fitting. And we see that all the spectra can be nicely fitted with this EDT model, and I have shown the correlation plots here. And on the left-hand side, we see on the lower panel, we see a very nice linear correlation between the model parameters, and on the upper panel, we see the correlation between the spectral curvature with the observed flux. This is 2 to 10 keV observed flux. So we see that this curvature is increasing with the increasing flux. And on the right-hand side, we have the correlation plot between the curvature with the synchrotron peak energy. So we all this for the EDT model, the correlation is shown by the blue points. And here we can say that this all these analysis results, the correlation results nicely matching with our model predictions. And here, the interesting results we have here is, if we look at this various kappa values, So as we know, this kappa values, various kappa values represents various type of spectral diffusion. So we see that this kappa values during high flux state shifts from Kolmogorov-Krasnoyan type to bomb limit. And here we have a few points around and above the bomb limits. These points corresponds to the flaring state or observations. So, and interestingly, we do not see any points near the Hawk sphere. So for the Hawk sphere, our kappa value is 0. That means it is independent of energy, or we shouldn't see any curvature there. So all the spectra were significantly curved and cannot fit with the power law. So of course, we shouldn't expect any points here. So yeah. So next is we show the estimation of the product of delta and P with this EDD model. So this parameter, the product of these parameters can be estimated in terms of the model parameter and their linear relation. Also, the acidic peak informations are required. So we also provide an alternate expression for the product of delta B. So this is derived from the Synchrotron self-content theory. This is only based on the acidic peak values. We use this information just to verify our estimations from the EDD model, because estimations from the Synchrotron self-content is independent of our EDD model. So what information we do not have here is the content peak. So to estimate this content peak, we rely on the correlation obtained from the acidic peak. So for this correlation, we obtain the various synchrotron peak values using an EP-Loper model, and the corresponding IC values were extracted from the previous works. So we use this relation to extract various IC values for our 16 different XRT plus Newster observations. So we show the estimations here in this plot. So on the x-axis, we show the estimations with the EDD model, and on the y-axis, we show the delta B estimations with the Synchrotron self-content model that is independent of the EDD. So here, with these blue points for the EDD model, we see that this different estimations, one with EDD and one with independent of EDD, nicely matching, closely matching. So they are falling near this identity line. But here, the only problem is this extreme values of delta B, we get around 1100 Gauss, so which is a bit high. So this may either reflect the extreme variable behavior of the source, since the source underwent extreme flare during that observation epochs, and also that may be due to the inaccurate estimation of the acidic peak energies. So with this, I conclude that, so we observe the spectral curvature in case of extra spectrum in HBS, and we can see that that can be an outcome of the energy dependent electron diffusion. And then we use the source marker 421 to test the model, and from our analysis we show that there is a very nice correlation between the acidic peak energy with the curvature. And also we probe the turbulent energy index, and we showed that during high flux state, the turbulent index shifts from Kolmogorov-Krasnoyan type to bomb limit. And also with this model, we show the estimation of product of delta and B in terms of acidic peak energies. So in conclusion, I'd like to say that this model has some limitations, because here we see some points beyond bomb limit, which is unphysical. And also here, this estimation, we can see these values are too high, the delta B values are too high. So that all during the high flaring activities, extra flaring activities. So for that, we may need a realistic explanation, which includes the time-dependent evolution of particles, especially during these high flux activities. But that would again may increase the number of fit parameters, and performing statistical fit will be very difficult then. So with this, I stop. Thank you all for attending.
Thank you very much. We have time for a few questions. Yeah. You can unmute and ask if you, yeah. Amit, please go ahead.
Thank you. A very good talk. I just wondering, you have shown this this magnetic, the range of magnetic fields which you have obtained. So you have almost 3 order of magnetic fields. So do you see any cooling in your light curve? So basically, once you have a very strong magnetic field, your cooling time scales goes very fast. And so do you see any signature of such cooling in the light curves? of the same observation, same X-ray observations?
Well, so far we haven't studied the light curve. So,
because if whatever you have proposing here, that suggests that for some of the cases you will see very fast, rapid cooling of a synchrotron emission. So there might be a very fast decay in your observed flare in time series or in time domain. So I'll be glad if you look at it, your time series data also, and see if it fits well.
Right, yeah, that could be interesting, yes.
Sure.
We'll surely look into it.
Okay, Pankaj, please go ahead.
So Panjupriya, you showed that in the high extreme flaring, this turbulence index goes to Bohm limit, right?
Yes.
Beyond.
Right.
So I believe this is problematic for when we consider or when we have in mind the first order diffusive shock acceleration, or is it a problem in all other cases like even magnetic reconnections and other?
Well, we are yet to investigate that, why there are a few points beyond Bohm limit. So we may need to refine our model, because you see, our model is a very simplistic one. So here, what we are considering constant acceleration timescale, and also for a monoenergetic injection.
No, that
so
is
we
okay.
may in that case.
Yeah. Go ahead.
So yeah, in that case, we may probably need an energy-dependent injection or something like that.
No, agree. What I wanted to ask is, like, when you are saying that, okay, probably it is going to beyond Bohm limit, which you should not expect or you are not expecting. So I am considering that you have particular particle acceleration mechanism, like let's say first order Fermi acceleration in mind, because typically people use Bohm limit there, but does this same Bohm limit apply even if, let's say, the particle acceleration is different, like magnetic reconnection as well? That's what I wanted to ask.
Yeah, maybe.
Okay. No problem. Yeah, thanks.
Okay, if you have no further questions, let's thank the speaker, and we will move to the next talk. Panchupriya, you can actually, de-share the screen. Thank you. So next speaker is Suventu Rakshit from ARIES, and he's going to talk about identification of the furthest gamma ray detected narrow line Seyfert-1 galaxy. The floor is yours. I will give you a call around 12 minutes. Is that okay? Hello, can you hear me?
Okay, my microphone was muted.
Okay, so yeah, I will kind of bust you around 12 minutes, okay?
Yeah, sure.
You can start now, thank you.
Good evening, everyone. So I thank the organizer for giving me this opportunity to talk about our recent discovery of the farthest gamma-detected narrow line Seyfert-1 galaxy. The name is TXS1206 plus 549. And this work has been recently been accepted for publication in MNRS later. So what are the narrow line Seyfert-1 galaxies? So we know the Seyfert galaxies are broadly classified in two categories, Seyfert-1 and Seyfert-2. In the case of Seyfert-1, you see the broad lines as well as the narrow lines. In the case, Seyfert-1, you see the broad lines as well as narrow lines, and for Seyfert-2, you see only the narrow lines, okay? However, in 1985, Osterberg and Poge noted that some galaxies of Seyfert-1 type, but they have some unusual characteristic. So these objects are defined by the width of the H-beta emission line, so which is less than 2000 km per second, and the O3 to H-beta flux ratio is less than 3. And these objects are narrow line Seyfert-1 galaxies. So why there is a different class, narrow line Seyfert-1 galaxies? So far, we now know around 11,000 or more narrow line Seyfert-1 galaxies, and they are limited to redshift 0.8. So here you see the Fe2 strength along y-axis and the black hole mass along x-axis. So narrow lines and broad lines are plotted here. So these are basically the density contours for 63 percentile and 95% density contour. So what we see is the NLS1s are having a high, strong, they are stronger Fe2 emitter, and they have low black hole mass. However, if you see it in the right panel, you see that they are NLS1s are high accreting objects. So about 16 of these NLS1s have been detected in high energy gamma rays. So this suggests that they have powerful radio jets. And interestingly, they are hosted in spiral galaxies in contrast to the blazars, which are hosted in elliptical galaxies. So we have no clear understanding of how these low mass black holes hosted in spiral galaxies are able to launch the powerful jets. And the thing is that only 5% of these NLS1s have been detected in radio. So their radio detection is very low. And all of these NLS1s are redshift below 1. And only 2 of them have detected at 0.8 to 1 redshift. So are there gamma detected narrow-line Separt1s at redshift beyond 1? Or are they similar to their low jet counterpart, or more similar to the blazar sources? Because if you go to the high redshift, you will see the high luminous object. So is there any chance of detecting the NLS1s? So, but to detect the NLS1s at high redshift, you need an alternative technique, because H beta is redshifted out of the spectral coverage of ground-based survey. So if you go further redshift, H beta will be outside of your spectral coverage, mostly in the ground-based survey, or you need an infrared survey. So we can have an alternative definition. So how we can get that? So the MG2 line is a strong emission lines, which is available in the optical spectrum for high redshift 0.4 to 2 redshift quasars. And SDSS gives you an opportunity to look at them. So here we studied the correlation between H beta and MG2 lines to find out that can we have an alternative definition rather than the H beta based definition for narrow line Supernovae galaxies. So here we plotted the FWHM of MG2 along y-axis and FWHM of H beta on x-axis. This plot contains 25,000 quasars from SDSS in the redshift range of 0.35 to 0.8, where you have both emission lines in the spectrum. And here also we saw the luminosity plot, MG2 and H beta, and there is a Fe2 strength plot in the UV Fe2 as a function of optical Fe2. So in two cases, in the case of, we see a strong correlation with spare band rank correlation coefficient of 0.7 between the width of the two emission lines. We have a strong correlation in the line flux, line luminosity of these two different lines. However, the UV strength do not correlate with optical Fe2 strength. So if we just rely on the definition of NLS1s that is based on the H beta, we can have we can select the sources at a high redshift candidate NLS1 based on the MG2 lines, because if we have FWHM MG2 less than 2,500 kilometers per second, so they would satisfy the conditions of high jet candidate NLS1s. So is it true that those sources can be NLS1s, high jet NLS1s? And how many of them are gamma detected NLS1s? So to find the gamma ray detected NLS1s at high G, we cross-match SDSS DR14 quasar spectral catalog, which contains around 500,000 quasars with Fermi-Lac 4 lakh catalog. So this gives us, then we put two conditions, FWHM MG2 less than 2,500 kilometers per second, and the presence of UV Fe2. So, and this gives us 7 high G gamma NLS1s candidates. So they are in the redshift range of 0.86 to 1.8. So, but to confirm their nature, we need infrared spectroscopy, and these objects are faint, so we need to have a large telescope. So here I am in the left panel, I'm showing you the SDSS spectrum, which covers the MG2 emission lines. And so we decompose the MG2 emission lines into the broad and narrow component, as well as the UV MG2, UV Fe2. So this is shown in the blue part. And as MG2 is doublet, so we fitted both the doublet component using a single Gaussian or a single Lorentzian. And we found that both Gaussian and Lorentzian gives them equal result, equal amount of fitting, good fitting. So once we, so in the case, so from the SDSS spectrum, we get the FWHM MG2 is around 2000 kilometer per second. And then to confirm this, we need to do the infrared observations. And for that, we looked at Subaru-Morris observation. So we obtained spectra using Subaru-Morris spectrograph. And we catch the red-shifted H-beta emission line. So here H-beta emission line is shown, and O3 doublets are also shown. So the signal to noise ratio of this emission line is not so high. So we could only fit using a single component to represent the whole H-beta profile. And by doing that, we got FWHM of H-beta is around 1200 kilometer per second. O3 by H-beta ratio is 0.7, which is less than 3. And the black hole mass is less than solar mass. So all these characteristics suggest that these objects is a genuine narrow line separated galaxy. And so far, our result, these objects is the most highest redshift in this one, at redshift 1.34. So we checked the multi-band properties of these sources. Of this sort, and we looked at the first survey, and there's a first image is shown here. The object is very compact, and it is a highly radio loud with radio loudness parameter of 1300, and it has a flat radio spectral index. And then we looked at the archival light curve. So this is upper panel shows the CRTS optical light curve. And the lower panel shows the WISE infrared light curve in W1 and W2 band. And the source shows significant variations in both in optical and in the infrared. And the variability amplitude is found to be 0.7 in W1 band in WISE infrared. And in CRTS also we found a 0.5 magnitude variation. Also in the case of infrared, we found that inter-day variability in short time scale in some epoch. This suggests that the variability is not only due to the accretion, but it's also coming from the contribution. It is due to jet also. So the contribution of relativity jets also affect the variation, because this variability is similar to the low jet gamma ray narrow line separated galaxy variability, and also the blazar category of sources. Usually narrow NLS ones are low varying sources, so they do not show radio quiet sources, radio quiet narrow line support one do not show such variation. So we here the multi-band ACD is shown. So the ACD has a typical double hump structure, and which can be explained by electronic radiative modeling. And the low energy peak is synchrotron, and high energy peak is due to external Compton. And this is similar to other gamma radiated narrow line separated galaxies, and also it closely follow the blazar sources also. So we estimated the disk luminosity of these sources, of this source, and also the black hole mass that I also already mentioned. Here I'm showing you the disk luminosity as a function of black hole mass. This is a plot that earlier by they showed. Only in addition, there is an object here, the TXS1206. And this object is following exactly the same correlation. And here we see that it is close to the upper part of the gamma radiated narrow line separated galaxies, and also the lower part of blazar sources. And it is highly accreting, and with an accretion rate of more than 10% of its internal rate. So I will conclude here. We detected, discovered the farthest gamma radiated narrow line separated galaxies at redshift z equal to 1.34, and it was possible through infrared spectroscopic observation using Subaru telescope. And the source shows similarities with the low jet gamma radiated NLS ones, as well as the blazar sources. And this also established that FWHM of MG2 less than 2,500 kilometers can be used as an alternative definition to select high jet NLS1's candidate. We also have a list of 6 other high G NLS1's candidate from our previous sample. And we are excited our recent upcoming observation using 10 spec, which will allow us to observe some bright sources and catch the red-shifted H beta and H alpha emission lines. So this will be helpful for further classification of these sources. And for fainter sources, we submitted proposal to Keynote 8.2 telescope. So thank you. I will finish here.
Thank you very much. You have plenty of time for questions and comments. Please unmute yourself and ask. Amit, you have a question?
No, sorry, I just forgot to lower that.
Sure. Okay, sure, no problem. Okay, I'm waiting. Okay, if you are no further, Vineet, you have a question. Please go ahead.
Yes, I have a question.
Please go ahead.
So Bindu, how did you select a single source out of 11,000 narrow line Synchrotron galaxy for this high redshift detection?
This is 11,000 is only low jet sample. It's not included in the low jet sample. High jet sample is a different one. So there are the source selection was done, as I told, that there was a 500,000 quasars included in the DR14 quasar catalog. And I recently published this catalog of quasar spectral properties. So I have all the 5,000 quasars spectral properties information. And then I cross-match this source with the Fermi-Lat 4-Lac AGN catalog. Okay. And then you get a list of 6-7 sources. 7 sources they are included. So one source we observed so far, and other 6 are yet to be observed. And April 10 spec observation, we are hopeful to observe some other sources. So this is basically from DR14 quasar catalog, high jet catalog. It's not included in my previous 2017 NLS1 catalog.
Okay. So this was a high jet quasar catalog. You have cross correlated with the Fermi-Lat, yes. And after that you search whether this source is narrow line Synchrotron galaxy or not, right?
Yes, that's correct.
Okay. So it may be, it may not be a narrow line Synchrotron galaxy after doing such exercise.
That's correct.
Because
yeah. So there's the classical definition that we follow for selecting the NLS1s are beta less than 2,000 kilometers per second.
Right.
Yes. So many of the sources which are already known as FSRQs and those they are high luminous sources. So basically. Yes. So basically, we follow the definitions which are now in separate ones. Everybody follows all the 11,000 sources that are included that in our previous catalog also. So there are many sources that are also high luminous. So we say luminosity is higher than quasars, right? So
okay.
Magnitude.
Okay. Thank you.
Okay, if there are no further questions, let's thank the speaker for a very nice talk, and we will move to the next speaker.
Thank you.
Okay, the next speaker is Sumana Nandi from NCRA TIFR. She's going to talk about study of processing jets in a radio galaxy with GMRT and VLBI. Sumana, the floor is yours. I will ping you around 12 minutes. Okay.
Okay. Can you hear me?
Oh yeah, loud and clear.
Yeah.
You can also see your slides.
Yeah. Okay. Thank you. So today I'm going to present a study of a processing jet in a radio galaxy J1328 plus 2752 with GMRT and VLBI. So outline of my talk is something like this. I'll give a short introduction and then I'll discuss the parsec scale to kiloparsec scale structure of this particular radio galaxy, then the physical mechanisms for driving the jet precession, and we applied kinematic jet precession model for this source, and then I'll discuss then I'll give my conclusion and future plan. So here in this picture, we can see different stage of galaxy merging. Galaxies are believed to evolve through merging process. And in the primary phase, two galaxies come close together through dynamical friction. And then as they come closer, if they have supermassive black holes at their center, these black holes will sink into the central potential and they will form a binary pair of supermassive black holes. And ultimately, with time, they will collapse, and this collapse will emit a giant burst of gravitational wave emission, and those signals will be detected through future gravitational wave experiment like LISA. Now, the question is how we can detect this binary supermassive black hole system. So to detect these systems, we need multiple signatures through multi-wavelength data. We can use optical, radio, as well as X-ray observations. But one primary need is high resolution observations of all these wave bands. Now, VLBI is an excellent technique through which we can detect binary black hole systems, which has very small separations, and VLBI provides milli-arcsecond resolutions. Now, in the figure, in the left panel, we can see one such example, which is actually a ULUG, ultraluminous infrared galaxy, which is supposed to be gas-rich merger remnants, and that the binary black hole system was detected through X-ray observations. In the middle panel, it is a radio galaxy, and it was actually detected as a binary system through VLBI. Here, this C1 and C2 are two positions which are separated by 7 parsecs scale length. And in the right-hand side, we can see again a binary black hole system, which is recently identified in a nearby Seyfert galaxy. And again, the separation of these two binary black hole holes is very less than 1 parsec, and that is also resolved through VLBI experiment. Now, confirmed binary black hole systems with with tens of parsec is separation is very less. It is less than 10 still now. Now, there are other methods through which we can identify binary black hole systems. Those are like indirect method, which can give, suppose if radio jets have helical jet pattern, or sometimes X-shaped, jet-shaped radio galaxy may host binary black hole system. And here in the left panel, we can see such example. This is an X-shaped radio galaxy, and we can see this helical jet pattern in this AGN jet. Now, another is double peak emission lines, which is also an indicator of binary black hole system. The actual idea is if two binary black hole is moving with their own characteristics velocities, they can produce such split, which is shown in the right hand side panel, and that can emit this double peak emission lines. Now, double radio galaxies, these are not discussed so much in context of a binary black hole system, but I'll give some force on it because my next slides will be on this double radio galaxies. Now, this is also, I want to mention this seldom does a single source show all these characteristics together. Now, what are the double radio sources? Double radio galaxies are actually episodic radio sources where we can see the outer jets and the inner jets from a common AGN at the center, and generally all the inner jets are following in the same previous jet directions. So here in this picture, we can see all these double radio sources, which we have recently identified, confirmed through GMRT. But if we see the right-hand panel, right side lower panel galaxy, we can see there is a jet rotation of new episode, and the jet rotation is almost 30 degrees for this source. So then we started to study this source in detail. Now here we can see that we can see the multi-frequency image of this particular source. Actually, this galaxy, this radio galaxy, is a subclass of double radio source, we can say, because it has a misalignment between two epochs. So we call them misaligned double radio galaxies. So these are not only give irregular jet outflow, but there is a irregularity in the direction of jet flow axis. Again, there are some discussion in the literature that these kind of AGN, the source can emerge from AGN axis precession, or due to the influence of nearby galaxy, this kind of jet rotation may happen. Now, in this figure, we can see left panel, the BLE image, in the middle panel, second panel, GMRT 610, then 325, and this is LOFAR at 150 megahertz image. We also observed these source at LOFAR, and we can see all these low frequency images are picked up nicely, very diffuse emission. But we can also see that the jet is, there is a turn in the jet, and it shows some kind of S-shaped structure. So we studied its host galaxy, and we can see through SDSS spectra that all lines, here I have presented 8 emission lines, and all lines are actually double picked. The left blue and the right red Gaussians may represent two merging components here. And we also estimated the separation, the two component separation velocity between two components from this spectra. Now, to distinguish the different class of ionization, we use repeated diagnostic diagram. Here we can see two components are actually maybe AGN. Now, but here one thing I want to mention, that these double peak emission lines can also be produced through narrow line gas kinematics or jet outflows or interaction jet, medium interactions. So this can be happen. This can also generate double peak emission lines, but not only the binary black hole system. But here we can see the strength of the lines are not similar. So it may come from two different systems. And another thing is that if it is jet cloud interaction, then it can generate double peak emission line in one or two emission lines, double peak in one or two emission lines. But here for all emission lines, we can see this double peak. So possibility of a binary black hole system is high for this source. We also did the host galaxy and bulge disk decomposition of this particular source, and we can see the Sarsic and exponential profiles are required to fit the host properties, and the disk component dominates beyond 2.5, and we can say that the extended disk-like substructure indicates a gas-rich unequal mass merger. Now, since it has a lot of evidence of binary black hole system, we started VLBI observation of this source. Here in the left panel, we have overplotted GMRT image on the optical. Here we can see the core is exactly situated on the optical host galaxy, and the core through VLBI core is resolved in two components, A and B. have again two subcomponents. We estimated the brightness temperature, that is very high, and it indicates it is a non-thermal emission. And also we estimated the projected separation between A and B, that is 6%. Now, emission line peak separation suggests a distance between two putative supermassive black hole is 6 parsecs, and the corresponding orbital period is 1.7 mega year, which is again exactly matching with VLBI observations. So then we tried to put some model for this system, and then the physical mechanism which is driving jet precession is our model is dependent on the binary black hole system. So it may come from a binary black hole model, or it may come from a single binary, supermassive black hole. But in the left panel, we have shown the first mechanism, which is a binary black hole model. Here, actually, this primary binary black hole, the accretion disk is affected by the torque of the secondary black hole, which is rotating in a non-coplanar orbit. And that's why it's giving a jet precession in the jet precession in this cone. Again, there is a possibility of getting jet precession, but without need of any second system. A misalignment of binary spin with supermassive black hole spin with the accretion disk angular momentum also leads this jet precession. So our model is based on the first binary black hole model, and we used actually kinematic jet precession model by Capirani et al. 2006, and this model was applied for different binary black hole systems, and it basically assumes that this model basically assumes that the jets are formed by jet and counterjet are formed by plasma elements, and these plasma elements are moving with a constant speed. And as from the center, due to the precession, the elements emerge from the center, and it goes a different direction along the cone surface, and the cone axis also make an angle with line of sight of the observer. Now, if a jet after one precession in the observer frame of reference frame, what we can see that the jet will move, jet will point out in the same initial direction, and the successive emission of the emitting elements will make a helical path on the cone surface. Now, this helical path, which was generated from this kinematic jet precession model, we overplotted on our kiloparsec scale radio images, and all are exactly very nicely well matched with the kiloparsec scale structure of this particular radio galaxy. The jet precession model gives the period is roughly, jet precession period is roughly between 1.5 to 52 mega year. The precession cone semi-aperture angle is 3 to 30 degree, and the inclination angle is between 7 to 68 degree. Now, we also, in my conclusion, we have noted that this source is exactly similar with the previously reported binary black hole radio galaxy 0402. And it has same kind of black hole separation, and as well as the same orbital period. And there is also some suggestions about double radio sources like Camusa et al. 2006, Liu et al. 2003 and 4. They suggested these DDRGs are actually remnant of merged binary black hole system. But in this case, these misaligned DDRGs are actually interacting systems. Here we can see optical lines, And so in this study, what we can say, these optical lines, radio structures, and kinematic model strengthen the feasibility of binary black hole scenario of this source. And since we didn't have any spectral index information, so to confirm this binary black hole nature, we again observed this source through, plan to observe this source through EVN, and we are in the current cycle, we are observing this source. Thanks very much.
Thank you very much. A very nice talk, and I am looking forward for questions, and please raise your hand and ask. I think already I have Vineet first. Or is it from the previous epoch?
Yes, is what previous ago.
Okay, then we'll go into Pankaj. Pankaj, you have a question or?
Yeah. Okay.
Yeah,
Sorry.
please go ahead.
So this is, so I am asking this question on behalf of Sundar Sahanathan. He is attending via YouTube, so he cannot ask the question. So his question is, did you explore the spectral index plot for this curved radio jets?
For the KPC scale, yes, we have done, but for the parsec scale VLBI image, we couldn't. Parsec for the inner structure, basically the core structure, we are planning to observe it through VLBI again. And we have already observed it actually. Yeah.
Okay. So he has one more query, whether do you see any pattern velocity in this system? I mean, the curved jet system that you presented.
Pattern velocity means what?
Okay, that's his question. Probably some pattern in velocity, like moving in some specific way. Probably, I think that's what he's.
But I mean, it's for optical light curve. We don't have any optical light curve of it.
No. So you measured like probably.
No, I think maybe because of the helical nature of some epochs.
Yeah.
Because you can have different Lorentz factors.
Mm-hmm.
And that may manifest as different luminosities that you have already seen. That's the claim, right? I haven't seen that very carefully, so yeah.
No, so what he means is like superluminal feature that you see. Yeah, probably exactly what Gopu said just.
Okay.
I mean, if you have a superluminal velocity, do you see any pattern of this motion? Okay.
No, that is.
Yeah. Okay. Thank you.
Any other questions by anyone? Otherwise, I will, it's not a, yeah. I have a couple of questions. Very nice talk, and this is of interest to us too. These are what kind of masses you are looking into here? These are million solar masses, or it's in the billion solar masses?
It's a 10⁸ solar mass of the central black hole.
Okay, so that will be most, this is also going to be, and these are not very far away sources, right?
Yes, it is Z is 0.09.
Okay, so which means there can be interest, I mean, such sources which are a bit more closer can be of interest to PTAs before the LISA. I mean, so LISA is much down the line. So the question, you said this cannot be spin flip. And you have this very nice cartoon from, the binary black hole with a tilted, the binary orbit is sort of tilted to the, accretion disk, right?
Yes.
But those are going to be, those that induces precision and all that. But then you have to be much closer for those interactions, right? This is still 0.1 mega year orbital period or something like that. So I'm a bit confused about that because you can argue, that any spin, even association of a binary will be difficult. That kind of, because there's no guarantee that this is a bound binary at that kind of separation. That
so
may be
that's
possible. That may be possible.
Yeah. So even this Biden-Peterson effect can also cause these.
No. Those are going to be, you have to really come closer, because the general relativistic effects cannot, they're too far away.
Yeah.
The other perturbations can be dominant. Here, what you're talking about is that the disk is getting perturbed by the, and for that you have to come closer. In the case of OJ287, it has to be essentially even no, it's not milliparsec, but it has to be a fraction of a parsec. You are talking about few parsec, and I will be very surprised that I haven't done this calculation, so I was just wondering, how can those effects can explain.
Okay.
And anyway, so that's I have to worry about. And what about the you talked about the helical jet feature in the in the images, right?
Yes.
So in order to support that, do we find additional luminosity along edges and other things? Because if it's in a helical motion, that can be expected. But of course, your inclination and other things are slightly bigger, so it may not be that. So the Lorentz boost can change, because of your orientation, and that can manifest as extra bright patches. We don't see that, is that?
No, we haven't actually.
Yeah, I think that may be because of the, your inclinations are large compared to what we expect in in this kind of collimated. Okay, very nice. And do we have other questions here? If not, let's thank the speaker for a nice talk, and let's
Thanks very much.
Thank you. Let's thank all the speakers of this session, and okay, now we are in time. We are just off by 10 minutes. That's good enough. So we have plenty of time for a discussion and all that. And I haven't thought about any specific topic, but if one of the participants want to discuss something interesting, they are welcome to do that. If not, we can disperse because it's been fairly long.
Yeah, Professor Gopakumar, I think it's already evening time and people are rushing to go back to their homes.
I can imagine. Yeah, we are all tired. I mean,
and it's a COVID situation also. But
agree. I fully agree. I think we should wrap up in that case, because there can be curfews here and there and all that. Yeah, Amit, you have some comments to make. Then
yes, very quick thing. So as most of you will be knowing that we are working for a CTA proposal. So if any one of you are interested in CTA proposal, writing to this proposal, or if you are interested to be part of CTA India consortium, I'll be glad to interact with the person, as well as we will also see whether you can also contribute to the consortium. And when we propose this proposal to the government, I'll be happy to invite everyone to participate. So if any one of you are interested, please let me know, me or any CTA India consortium member, or anyone who you know that is a part of CTA India consortium.
Thank you, Amit. Yes, that's an excellent idea. Those who are younger members of the audience should seriously think about it.
Yeah, and Professor Gopakumar, if you permit, I have a small announcement to make.
Yeah, please go ahead.
Yeah, so thanks all the speakers of the day and the 2 sessions, and it was a very nice, healthy discussion and good talks. So as we discussed that last half an hour would be kind of discussion. So I want to again insist upon and inform you that there is a separate Slack channel which have been opened, and a few posters are there, and it is open 24 hours. So interested people and students, if you have questions, just put your questions on Slack channel, and I would request senior faculties and researchers to kindly respond if you are part of the Slack channel. And I would encourage all of you to be part, so that I mean, due to COVID restrictions, a lot of things are there. We can't extend our discussions to late evening hours. So online Slack channel is always there. So please use that channel to continue discussions for all 5 days. Thank you very much again.
Excellent. So in that case, we can conclude for the time being, and let's thank our host for a wonderful day of discussion and talks, and hope to see you all tomorrow, sharp 9 o'clock.
Sure.
Sorry, 9:30. Okay. So bye. Have a safe way back home, and good night.
Thanks. Bye all.
Bye.